organizer. Di Verona. Maybe to some
yeah, much like me. And, the thing is that managing Kubernetes is small. Data into including
Z and correct. So
a quantum specialist worked start with the obligatory contribute to this at the same up and I it's WQS and FSCD and maybe so I hope interesting. Unfortunately, I mean, I guess a little bit, maybe so calculate because and give us some intuition. X is was originally used so out to show spiders and the X spiders in calculus. Hilbert spaces this actually correspond to identifying bases which is so different kinds of spiders. This has an maybe some of you have seen the that when functional. Okay, so fascinating. Back in, I was visiting Filippo Bonchi, who's my close colleague. We ended up doing is went so unitality, right? So this is just the multiplication or the equivalently the distribution multiplication. It's a think about it's a very the one hand, we have diagrams. So for you. Path count. And I let 0 the right. Well, you know, so this is right, and it's a very have patient with the system proceeds now. Two. We just in different colors. Consider and the idea why me it's one. I told you slide. Syntax. So this B, the standard, this is just by plus the algebra rules. Because any kind of limit ways in which each other. Okay, so type this original system that we drew. The key thing is that if this is the bottom category, what we called SV. What's a linear? What's a relation? First big side, like the system is linear. Sure. Yes. Yeah. Or traditional situations where in this the then I get a for already quite a do a lot of this trend. So I stopped his blog. I always thought this is so cool, right? But I'm just paper. I said to a So, so so it, and I can and I cut this syntax of Cartesian category functions natural that be the right thing. The thing that we prove, we have to go. I give you my relational theory, string diagrammatic theory. I look at all its models in REL, and if something's true in all something's true in all the models, if and only if I can prove it using this algebraic structure. So it's like a Gödel style completeness. And it turns out that this kind of idea then had legs, and there is this kind of a meta way of doing functorial semantics, right? So the important thing is you need to know this kind of algebraic structure. So I did some work on partial theories where you replace Cartesian categories with discrete Cartesian restriction categories. And the last thing I want to tell you about is how to do first order logic, and that is Cartesian categories with something called first order bicategories. So I've got 5 minutes. 10. Okay, good, excellent. Okay, I was speeding up. Okay, good. So in that case, let's take it easy. Because I really want to, this is something which I'm very excited about at the moment, because it's how to do first order logic with string diagrams. So the thing that this Gödel star theorem that I showed you, it's a nice way of saying that when you look at the structure of Cartesian bicategories, this really captures the existential conjunctive nature of first order logic, right? Because REL itself, the way we've defined REL, it captures the what's commonly known as regular logic, or in database theory conjunctive queries, because it's the fragments. You remember, like when you define composition in the category relations, you're using the existential quantification and conjunction, and it turns out that this really picks out logically the existential conjunctive fragment of first order logic. So REL is kind of a weird beast, right? Because there's somehow two RELs which are isomorphic but feel very different. So the usual category relations I'm going to from now on call REL white, but I'm going to talk about its strange cousin REL black. Okay, so it has the same objects, so they're still sets, and ours are still relations. But now, composition, instead of being there exists and, will be for all or. Okay, so I now compose relations. So X is related with Z in R composed S, if for all Y, X are Y or Y as Z. Now, to be honest, I've been doing this now for over a year, and I still don't really have a very good intuition for this, right? Right, I have a kind of a gut feeling for what usual relational composition is. I don't yet have it for this. And identities are just so before identity was, X is equal to, X is related to Y if and only if X is equal to Y. Now it's the opposite. Okay? Now when you think about it, so this as a category, these two guys are isomorphic, right? The isomorphism is just complement. So these are just De Morgan jewels. This is like the De Morgan jewel of REL. And in a sense, just like the usual category relations talks about the existential conjunctive fragment, this guy talks about the universal disjunctive fragment. And since we know since we know a very nice algebraic structure to capture the first part of the story, we also have a very nice algebraic structure for the second part of the story. It's just a co-Cartesian bicategory, and it's really the same structure, but the inequalities go the other way. Okay, so we have these two fragments of first order logic. The question is, what next? Okay, and we have a kind of a slight, we had to be a bit creative with our string diagrams, right? Because we're going to have string diagrams with two different kinds of backgrounds to emphasize which REL are we in at any particular moment, right? So this is the syntax of Cartesian bicategories of relations, which is going to be our syntax, for the usual REL. So whenever you have a white background, this is the usual category of relations. Identity is the identity relation. composition is the usual way of composing relations. But I can also do things with a black background. Okay, so in a black background, I'm working in the De Morgan jewel of rel, so rel's weird cousin. So the identity relation is now the inequality relation, and I compose things, you know, with this for all OR. And I know individually what the algebraic structures are. This is, you know, Cartesian bicategories, co-Cartesian bicategories. So what's missing? What's missing to get the full picture of first order logic? So it turns out not very much. And here, you just have to add more Frobenius. So essentially, there is this, first of all, you have to make sense of this thing, right? So you have to, we're now throwing in everything together. What does it mean? Well, we have a category or bicategory in which there are objects, there are arrows, but there are two different kinds of compositions and two different kinds of tensors. Right? There's the white composition white tensor and the black composition the black tensor. Now, category theorists have worked out situations like this, and they're called linear bicategories, right? So essentially, I'm just going to say, okay, from now on, I work in linear bicategories. So that's almost the whole story, apart from these four equations, right? So you need to specify that the Cartesian bicategory structure, so the multiplication and co-multiplication, are related together in this particular way, which are called linear adjoints, and also there is this kind of a Frobenius law. Okay, and it turns out that this is the complete story, and the story is going to be presented at LIX this year, and it's joint work with Filippo, Alessandro Di Giorgio, Nathan Hayden. So here's a little worked example. So this is a completely algebraic account of first order logic, right? So here's a diagram that corresponds to the formula there exists x for all y rxy. Here's the diagram that corresponds to the formula for all y there exists x rxy. Now in first order logic, this is kind of like, you know, a non-trivial example where you can prove using, let's say, you know, Gensen calculus or natural deduction that this implies this. So algebraically, what that means is using our algebraic theory, we should be able to prove that this is under this in the ordering. Okay, and it turns out, so this is the proof that we have in the paper, this kind of worked example. This is just string diagrammatic surgery in this setting, using you know, completely algebraic reasoning. Yeah, so this is because so we do have a kind of a deduction theorem, right? So the implication can be folded back into the syntax, right? But this less than equal to, you should read it, you should think about it as there exists a proof in natural deduction or in sequent calculus where I start with this as an assumption and I end up with this as the conclusion. That's really what this correspondence is. Yeah, it's very good. I'm coming to a conclusion. Okay, so I just want to end on the on what's kind of different from traditional first order logic when you do it this way. The interesting thing is negation is not a primitive. Negation is not a part of this language. Negation, you can derive it as an operation that takes syntax and gives you syntax, right? And it's just essentially color swap. Black goes to white, white goes to black. So for instance, you know, neg phi is syntactically equal as a diagram to neg phi, right? Because this is just an operation on syntax. And there's all kinds of, we have a, you know, completeness, we proved a completeness theorem in the style of Henkin. There's all kinds of really cool stuff that I don't have time to get into. And it's very closely related to this field of logic called deep inference, right? Because what we are doing is a completely algebraic way of dealing with first order logic, you know, equals replaces equals. We don't need to develop particular proof theories, it's just algebra. Okay, this is my last slide. I want to end on some philosophical ramblings, which I think as you get older, you get more and more allowed to do this, right? I tried to do this when I was young and people really hated it, so I'm still a bit nervous, but But, so I think in general, a big chunk of algebra can be understood as patterns where Frobenius and Hopf algebras or bialgebras interact in some way, and ZX is one important example. And I think that these two algebraic structures seem to be really fundamental building blocks of reality, and somehow at a higher level than we normally do maths. What I didn't talk about is probability theory. I think that's like there's a whole section of people who are now working on string diagrams for probability theory, where the underlying categories are Markov categories. And I think it's a really important topic that's going to see a lot of great stuff coming in the next few years. And finally, I want to kind of make this thing of string diagrams are the syntax for the 21st century. So why? They are resource sensitive out of the box, which is crucial for things like quantum, right? And moreover, they expose, and I've seen this time and time again in many different fields, once you do it properly with string diagrams, you see a lot of hackery and sometimes lack of rigor, implicit assumptions, and outright mistakes caused by the use of traditional syntax. But there is this one thing which I think is holding us back, so we need more tool support, diagrammatic editors, diagrammatic theorem provers, etc. That's it. That was my final slide. Thank you very much.
Sugar in your ZX approach, which I found really, really sweet. And then two trivial questions. First of all, can one then combine two white and black cousins and they would essentially equal out, or is that too trivial to think about? And the second question is, what are the implications of the recent Quantinuum paper, basically saying that ZX calculus is complete in what's the finite dimensional Hilbert spaces?
Yep. Okay, so I'll take the last question first. So the completeness, so that when people talk about completeness of ZX calculus, it's a slightly different kind of completeness, right? So when I talk about completeness in here, I mean completeness in the style of Gödel. So I have some kind of a syntax, and I have a way of giving models to the syntax, so giving semantics. And Gödel style completeness says that if something is true in all models, then I can prove it already at the level of my syntax using my algebraic theory or using my proof theory or whatever. So this is Gödel completeness. Now ZX completeness in this is something different. It's about capturing all of the structure, all of the relevant structure of Hilbert spaces using your calculus, right? So it's essentially can we express every matrix, every unitary using this approach, right? And so that becomes a very technical issue because you have to, because for example you have to, because in the end you have a finite language to express uncountably many things, right? So there's uncountably many complex numbers, right? So you have to state this carefully, and the proofs are very complex, right? So it's obviously very important because you want to know whether your language is. Because in ZX, you're only really interested in one model, right? There's not really other models that you're interested in. You're interested in the model that's relevant for quantum. So it's about being complete with respect to that. So it's more like, I guess it's something like more like Gödel's. It's a kind of a completeness that's more like in Gödel's incompleteness theorem, right? Because Gödel's incompleteness theorem is about really a particular model, which is the naturals, right? The integers. And the other question about collapsing rel white and rel black. This is kind of a really weird, like for a long time, this was a mental block for me, right? Because rel white and rel black are isomorphic, right? So once you know that two things are isomorphic, what more can you say? Like as a mathematician, that seems like the most strong thing you could say, and the question is over, right? But somehow they're isomorphic, but in order to get first order logic, you have to separate them and understand how they interact, right? So that's really where the meat comes.
Any other question? Yeah.
Last line, is this amenable to Coq proofs?
Is it amenable to Coq proofs? Yeah, I mean, so I think one can approach the question of what it means to be a diagrammatic theorem prover in different ways, right? So one, so clearly one way where one could start is just using the string diagrams as syntax, then translate down to terms and use coq as the back end. So that's certainly one future direction where I think we can make progress. Another way is just to have a completely diagrammatic backend where you actually do graph rewriting and matching given a particular theory, and maybe things like e-graphs then become interesting in this setting and so forth. I really feel like that this is where a lot of attention needs to be put for this stuff to become more interesting than just mere. I mean, there's also the problem, right? These things get kind of difficult to draw on paper with a pen, right? So even though they give you a lot of, I think they give you a lot of intuition after a while when you play with them, they're still kind of a pain to draw. So having tool support for applications like this would be amazing.
So following up on this, we already had two-dimensional software, notation in the beginning of the 20th century, and it was basically abandoned. And
you're talking about existential graphs?
No, Russell and Whitehead.
Yeah, sure. And also the original, by the way, the original paper by Frege on quantifiers.
Yes.
Was
So
diagrammatic, right?
there are a number of attempts actually of capturing semantic properties in syntax. So basically, you're capturing certain equational properties in the syntax itself, and so on. But when it comes to actually representing these things as data structures on computers, I mean, what you're suggesting is like, taking planar computers or special data structures. And here's the second question. It turns out actually, very often actually building in equations or equalities into the data structure is actually not a good decision. So for example, our coordinate-based approaches in physics, for example, they basically, the theories are coherent, but we're working with matrices, even though, you got coherence problems, and you're exploiting actually that you don't have to have a unique representation of the semantic object.
Yeah.
So, okay, can you speculate some more, please?
Sure. Sure. So first of all, I agree that one of the areas where we've made a lot of advances in the last 10 years is precisely to stop thinking to have because I've talked about these things as syntax. And I've talked about these things as algebraic structures. I haven't really talked about them as combinatorial structures, so something like an underlying data structure. So there is a story. There's a story that I didn't tell today. So we do have a very good understanding of string diagrams, at least a very wide class with what the data structure should be and how the algorithms should work. So there's a whole series of papers which I'm involved in called string diagram rewrite theory, where we really do rewrite. We really developed the theory of rewriting on this. And there has been some toy tools worked out using this methodology, but nothing sort of at the size of, let's say, a coq or a lean. Or now the other question was, is it actually a good idea to bake in a lot of these equality into the data structure? So I think it's certainly. I mean, so when you look at e-graphs, the success of e-graphs, I mean, that's precisely the idea in e-graphs, right? You bake in equality into the data structure. So I personally think that has legs, but yeah, again, this needs to, I think it's definitely worth trying and seeing what happens. But thanks for the question.
Any other question? Just a quick one, very, very short. These algebraic structures and their interactions are used to. Can you hear me? I don't know.
Yeah.
For describing circuits, right? For the purpose of optimization. So do they really? Are they able to capture entanglement? I don't see it.
Yes. So there is.
I mean, I couldn't say it, but maybe I missed it.
So I didn't talk about that. So unfortunately, this wasn't a ZX calculus talk, but yes. So they capture entanglement. They do things like quantum teleportation.
Okay.
And I'm told. I mean, again, I'm not a big expert, but I'm told that more and more ZX calculus is actually being used in industry or being used in industrial relevant applications for things like quantum error correction and things like this, right? So these are. It seems like people are finding this calculus very useful in the sort of quantum domain.
Okay. Yeah, thank you.
Thank you. Thanks. It was a pleasure.
And Let's move to the next talk. Is not here, so I will give the talk remotely. The next talk will be a remote talk. Is he online? Is there Razin online? Yes?
Yes, hello.
Hey, Razin.
Yeah, can you hear me?
Okay. Hello, Razin. We cannot see you. But
Oh, yeah, I'm working on it.
but I will give a talk, which is somehow a kind of continuation of Powell talk. And it will be about some continuous extension of the ZX calculus. And so as soon as
So should I,
available,
yeah.
tell us more about it. So unfortunately, Resin couldn't get the visa and
Okay, yeah, it
couldn't
happened
join
before.
us.
Okay. Okay, Razin, can you? Yeah, I think I know a fix. Okay, Razin, don't do anything yet. Can you see which
I see.
voice channel you're
This
in?
was a different, yeah, this was a different channel. Okay. Right, can you see my screen? Hello?
Okay, Razin, can you hear us?
Can you see my screen?
Okay, we're having trouble.
Yes, I can hear you. Can you see me?
Yes, yes.
Okay, so shall I start?
One moment. Okay. Oh. Okay, one more thing. After. Yeah, let me go on Discord and X. Okay, we can see your screen.
Okay, so yeah, let me know when I can start.
Yeah.
Yes, you can start, please.
All right. Yeah, hi everyone. I'm going to talk about the Octave ZX calculus, which is a graphical language for continuous variable quantum computing. Yeah, unfortunately, I couldn't be there in person because I didn't manage to get my visa in time. So this has to be online. This is joint work with Lia and Stefano Gogioso. And we recently put out the preprint on archive. So if you're interested, you can find more information there. So first I will introduce the graphical language for infinite dimensions, which is going to be a version of ZX calculus. And then I'll talk about how we can represent these simple gates that you encounter in continuous variable quantum computing as ZX diagrams. And then I will show that the calculus that I presented is already complete for the Gaussian fragment. And here the Gaussian fragment means the classical simulable part of CV. So like in analogy with Clifford plus T, this is like the Clifford part. And finally, I will describe two applications in quantum error correction and Gaussian boson sampling. So the qubit ZX calculus has two types of generators, the Z spider and the X spider. So here I'm using the green and the red instead of the white and the black notation, like the previous talk. So the Z spider, which is the green one here, it matches the computational basis state. So it has cat0 and cat1, and it will make sure that either all of the wires have either cat0 or all of them have cat1. And we can also have an extra phase. So that corresponds to the computational basis. whereas the X spider corresponds to the Fourier, the Hadamard basis. So to generalize the ZX calculus to infinite dimensions, we need to look at what kind of basis states that are available and and the ones that we care about. So in L2R, which is the Hilbert space for the continuous variable systems, the basis states that we care about are position, momentum, and Fock. So position are, so ket x would be any real number. So x is any real number, and we have ket x. And if you take the Fourier transform of the position, we get the momentum basis, which will represent with ket p. So both of these bases are continuous, but we can also have the Fock basis, which will be the discrete basis. So this would correspond to, instead of position and momentum, which is the phase space picture, the Fock basis would correspond to the number of photons that you have in the system. But there's also the relation between the continuous basis and the Fock basis that is given by Hermite polynomials. But yeah, we don't need to go into that. So we will try to define spiders based on these basis states. The first generator in the calculus is the Z spider. This Z spider corresponds to the position basis, and it will match the position basis states, ket x here. Now, we can also label a spider with a function f, and this function f is a function from real number to complex. So for every basis state, ket x, it will give a coefficient for that. Similarly, we can define the Fock spider, which is the discrete spider. So it will match the number basis, the Fock basis, and we can also label it with a function, which now goes from naturals to complex. And we will also allow for global scalar in our calculus, because it's just very convenient to have that. Now, using the Z spider and the Fock spider, we can define the X spider. So the Fock spider diagonalizes the Fourier transform gate. So this diagram gives us the Fourier transform. And so if I have minus I to the n, that's a Fourier transform. If I have I to the n, that's the inverse Fourier transform. So we can surround the Z spider with the Fourier and inverse Fourier transform to obtain the X spider. So we don't need to have this as an additional generator. It just can be a simple notation. We also omit the labels on the spider whenever it's labeled by a constant function 1. So some more notation, we can describe ket x, ket p, and ket n using these diagrams. We also have this multiplier. So multiplier labeled by m simply sends ket x to m times x. So it multiplies the basis state. Another notation is the W node. So some of you might have heard about the ZW calculus, which is like a generalization of ZX, or not generalization, a variant of ZX calculus. And it has this W node, which is very convenient for us, especially for running in the Fock basis. So this is how we can define it. The diagrams don't really matter, but what's important is that if I input the Fock basis N1 to Nk, so imagine I'm inputting N1 photon in the first wire and Nk photon in the last wire, it will put all those photons in a single wire in the outputs. It will sum over all of those photons. And we also have extra coefficient, which makes the interactions nice. So what are the rules of the calculus? So first we have fusion. This is the simple one. We also have the basis copy rule. So if I input a basis state in the corresponding spider, it gets copied. And we also get a coefficient based on the function. Next, we have the bialgebra. So yeah, most people are familiar with the ZX bialgebra, but there's also a bialgebra between the Fock spider and the W node, as well as 2 W nodes. And lastly, we can have the scalar rule, which says that if there's a global scalar outside, we can simply put it inside the Z spider, where it multiplies the function. Right. So this might be slightly unusual, but all this is saying is that if you have that spider labeled by a function, you can change it. So it has to be only one output Z spider, so just a state. You can change to an X spider by simply taking a Fourier transform of the function. And going from X to Z is the inverse Fourier transform. So in analogy with this, there's also a way to go between the Z spider and the Fox spider, and that's via the Hermite transform or the inverse Hermite transform. These are the rules of how multipliers interact. These are quite familiar from QDITs. And we also need to be able to remove a scalar one. We also have this Euler rule. So if you have a rotation gate, which is Fox spider label e to the I theta n, we can decompose it into Z, X, Z rotations. And here, this is just a rule saying there are two different forms of splitter, and they are equivalent. And finally, this is the most interesting rule, which is the triforce. So if you have three W nodes that are all connected to each other, it's same as the Z spider. And this also generalizes to arbitrary arity. So if you have W nodes that are more W nodes that are all connected to each other, that's same as Z spider as well. Okay, so this is a quick introduction to the calculus. Now you can see how gates are represented. So the first gates that we are interested in are the Gaussian gates. So the gates that are analogous to the Clifford gates on a single node. So for that, we have the displacement, which is simply shift in the X and shift in the put together. We also have squeezing, which simply corresponds to a multiplier. And finally, we have rotation, and there are two ways of writing this rotation based on the Euler rule. Next, we can look at the two-mode gates. So these are entangling gates, and these three are still Gaussian. So first, we have the control knot, so C-knot gate, and there's also an extra parameter that we can have, which is the S. And in the case where S is equal to 1, this would be like the this would be closer to the QDIT C-knot gate. There's also the control phase gate, and when again S is equals 1, this is the usual control Z gate. And finally, you have the beam splitter, and there are two ways of drawing this beam splitter. This beam can be implemented with linear optics, and usually it's very easy to do. Now, to enable universal quantum computation, we need at least one non-Gaussian gate. And usually that's the cubic phase gate. And it's called cubic because it's e to the I gamma x cube, and where it's a function of x. We also have different non-Gaussian gates, like there have been proposals to use Kerr gate, which can be represented as a Fox spider, or an entangling non-Gaussian gate, which is the cross Kerr, shown here. We can look at the completeness for this Gaussian fragment. And first of all, what's a Gaussian fragment? So we will say a Gaussian fragment of our calculus corresponds to diagrams that are generated by these three diagrams. So we have a Z spider, where we can have e to the I pi, a linear part and a quadratic part. So ax plus bx squared. And we will also have the X spider, where we can have ap plus bp squared. So just linear and quadratic part. Along with this Z and X, we also need to give we also need to allow for vacuum state, which is a Gaussian state. And any diagrams that are generated by this is universal for Gaussian fragment. And to prove completeness, we rely on another calculus, which is the graphical symplectic algebra, which was mentioned in the previous talk as well. So this is a recent work by Booth, Carrett, and Comfort, where they showed that you can give these generators and give their semantics in terms of relations instead of linear maps. And they proved that these set of rules are complete for Gaussian quantum computing. So to prove completeness, we show that there is a translation between our Gaussian fragment and their calculus, which is invertible. And we can derive all of their rules using axioms of our calculus. And there's also more subtleties that I'm not talking about right now, but yeah, this is the main idea. And using this, we have the completeness. It says that if there are any two diagrams that are Gaussian, and they correspond to the same linear map, then there is a proof in our calculus using the rules that I presented before that allow you to go from one diagram to the other. Okay, now let's look at two applications. So first is quantum error correction. So in quantum error correction, what you usually want to do is you want to represent your logical qubit in some physical system. So one way of doing this is with the GKP code. And in GKP code, you represent the ket0 as a sequence of Dirac delta that goes from -infinity to +infinity, and these Dirac deltas are separated by 2 square root of pi. And you combine all of these Dirac deltas, and that corresponds to your ket0 state. The ket1 state is the same thing, but it's shifted by square root of pi. So you can think of this as you're summing over all even locations, and some for ket0 and odd locations for ket1. So representing the logical states in our calculus is quite straightforward, because we allow any arbitrary functions on the labels, which means we can simply label ket0 and ket1 as with these functions, which are sum of Dirac deltas. But in practice, these Dirac deltas are not physical, and neither is summing from -infinity to infinity. So in practice, what people use are these states with finite squeezing. So you approximate Dirac deltas with Gaussians, which have very small width. And moreover, instead of going from -infinity to infinity, you also have a Gaussian envelope, which kind of tapers off the Gaussians that are further away. Now, if you write this in the ZX calculus, we have a very compelling picture that we can derive, which shows that these GKP states with finite squeezing correspond to the ideal ones. So look at the Z0L, which is the finite squeezing approximation. So that's same as the ideal one, but you have somewhat injected some Gaussian noise into the into the ideal state. So you can derive this very compelling diagram for finite squeezing. And we can also reason about error correction. So you can also think about the syndrome measurement. So the circuit for syndrome measurement corresponds to this, where you have a zero logical, and you perform Control Z and you measure. And by applying some rewrites, you can derive this to be the diagram here. And we have projection at the end, which simply projects onto the code space. And to correct for the errors, we need to apply for a shift of -n mod square root of pi. So if our Gaussian, if our GKP is slightly shifted, slightly displaced, we can correct it by applying this correction at the end. But if it has shifted too far, then applying the correction would result in logical error.
You should,
yeah,
if possible, come to an end soon. So we have 5 minutes left for questions.
Okay. All right. So I'll quickly talk about Gaussian boson sampling, which is very important for proving quantum advantage experimentally. So it corresponds to a circuit like this, and the reason why it's difficult is because it corresponds to calculating this quantity called the Hafnian, which corresponds to the perfect matchings of the graph. And in ZX, we have in our calculus, we have a very nice description of this Hafnian, which says that if you have an adjacency matrix for the graph, which describes the connections between all the W nodes, and if you measure ket1 on the output, that corresponds to the Hafnian. So all we need to do is show that any Gaussian boson sampling circuit like this can be written to a form that's shown before. So you prove that this is the normal form for that. And finally, to get the Hafnian, we need to simply measure, and measuring that gives us the Hafnian, which corresponds to the amplitude. And we can do all of these rewriting diagrammatically. Yeah, that's all I had to say. Thank you.
Is there any question?
Hey, great talk. I have two questions. What's the distance of the code that you showed, and how many physical qubits does it take to encode a logical qubit?
So for the GKP code, I mean you're using one quantum harmonic oscillator, so one continuous variable system to represent one logical system. But there's also a way to represent one logical into multiple continuous multiple wires or multiple continuous variable systems. I think so. The idea of code distance, I'm not sure how it generalizes to talking about the GKP code, because the errors here are continuous, and you're correcting for continuous error. And usually, what we do in like bosonic codes is you convert these continuous errors to logical errors. So whenever it shifts too much, it will be converted to logical error. And usually, in all of the proposals, you also have a second layer of error correction on top of this GKP code encoding, and that would correct for those errors. But I'm not sure exactly what the notion of code distance is.
I have a different question. So what is this Gaussian fragment of quantum computing that you talk about? What is the key restriction from that Gaussian quantum computing is?
The Gaussian corresponds to the classically simulable part. Oh, do you mean like what is this whole continuous variable quantum computation thing?
So I understand the definition of quantum computing, but you keep talking about the Gaussian fragment of quantum computing. What is that?
Oh, so in the continuous variable quantum computing, you have the Gaussian part, and so think of the Clifford plus T circuits. So Clifford plus T circuits in the qubit case, the Clifford is the easy part. Something that can, if you have a circuit which only includes Clifford path, you can completely simulate it easily, classically. But if you add the T gate, which could be like a resource, then it makes the quantum computing universal for in qubits. So similarly, if you only restrict these Gaussian gates, which are like these ones, then stuff that can be simulated. But if you add at least one non-Gaussian gate, which is shown here, for example, any one of these, then you obtain universal continuous variable quantum computation, approximately universal. So that's the idea.
Okay, any more question? No? So we go to the coffee break, and we come back here in 20 to 11.
I would think we should resume and start session number 2. And I think that there's still people missing, but they will eventually drop in here, I'm pretty sure. So it's my pleasure to announce the next session and the next speaker, Bettina Heim. She's from NVIDIA and going to talk about, well, the quantum application development. I'm interested to hear what NVIDIA is doing, basically. I mean, this is a long story, I guess, right? We've been working on this topic for many years now. So the stage is yours. Thank you.
Thank you very much for the introduction and for having me, of course, here. So I did go also a similar path preparing slides, saying what is it really that I'm passionate about? And of course, I'm passionate about all of my work, especially work that I do at NVIDIA. There's lots of exciting things going on. But in part also, I'm really passionate about unsolved problems, because they are so much more interesting than just talk about all the great things that we have. So there are a couple of slides towards the end also that illustrate a little bit better what we have today, what cool things you can do with it. Hopefully that will make you curious and make you look. But a good part of my presentation, especially at the beginning, is really motivating where I think quantum computing needs to focus its efforts on today, what's kind of happening in that direction. And I hope there's something new for you to take away from that in today's presentation. All right, so with that, let's get started. Now, NVIDIA, HPC, and quantum computing. There is a lot happening here in Europe around integrating quantum hardware into HPC centers, which was really nice to see. Not quite as much in US, lots of hardware manufacturers, lots of cool hardware there, but a little bit less HPC integration. Here, more interest there, which is nice. But I want to drill down a little bit more into that as we go. By and large, of course, we do expect that ultimately quantum hardware will be available as part of centers. For one, of course, it's just not something you have in your basement. Usually qubits are fragile, need to be cool, need their own nice space, so not something we have at home generally. And then we do also, of course, expect that on one hand, quantum computing is very useful for a lot of the applications and use cases that are dealt with there. Think AI, think, chemistry, all of these things. But conversely, also there's just a lot of classical compute that is required to actually have a functioning quantum processor. So we do also need other accelerators like GPUs, for example, to really make use of a quantum processor. So if you've been in one of the NVIDIA presentations lately, you probably have seen a diagram, something like this here on the right side. Now, I promised I would drill down a little bit further today into the actual more interesting pieces. It's still pretty high level, but there are a couple of things I really want to call out. So let's look at this. On one hand, of course, we've got some sort of front-end service, programming language, whatever. I'll skip that part a little bit. But then we've got the whole infrastructure connecting the actual quantum hardware with the rest of the system. And here's where the interesting pieces happen, right? Because I'm already going to start out here with this little box around the quantum hardware, basically, that says error correction layer. Yes, I'm going to be talking about how does this really need to look like to actually have a processor and also is error corrected, connect successfully with the rest of the system, other classical accelerators, and so on. So once you have that, you definitely do have some amount of classical compute close by. Maybe that's a lot of electronics, maybe lots of ASICs. We already have that today. There's a lot of electronics needed to interact with the quantum processor. But to a degree, it's also reasonable to expect that probably there's some software there in the mix, especially during early development. Today, a lot of that happens on FPGAs because they're programmable. We don't necessarily have full confidence yet on what exactly error correction code is going to be like, what the exact decoder is. So there's always a lot of value in not yet having dedicated hardware built, even if you know eventually this is all going to get burnt into hardware. Then that whole system talks, of course, to the runtime. And the runtime, basically, that can have any code in it. That can have, you know, the standard parallel code. It can interact with GPUs, CUDA kernels, all of that, right? And then there's this moment when it calls into the quantum kernel. At that time, it's going to have to do basically a JIT compilation to finish compiling the actual instructions for the quantum device and push that down at some point, literally into a fridge. So when you see this, first takeaway should be, I mean, clearly, yes, in the end, quantum applications aren't just about the quantum part. There's a lot more to them. There's a lot of getting data in, getting data out, and all of that. Now, we're at NVIDIA are really focused here on the system development and the exchange between processors, because this is also what brought me to NVIDIA. There's just so much experience actually having done that with GPUs, and GPUs are to a degree somewhat similar as quantum processors. They have some of the same strengths, of course some differences, but there's a lot that can be learned from that integration, and so we want to apply that to actually build a system. Now, we do want to be focused that we're not specialized to a hardware. That's another thing that I really, really like about it. Most bigger companies that have an investment in quantum computing have taken a bet on a particular qubit architecture, so to speak. But, I mean, it can be nice. It makes it a little bit easier, maybe, to think about the problem and solve it, because you can specialize for that hardware. But personally, I think trying to generalize is a good start, because it really forces you to think at the conceptual level. See what are the similarities, what are the right structure of this problem, this compilation stack to think about. And this is why I really like to test this version in my head against reality, so to speak, and really see, does it work with different kinds of qubit? Does it hold up? So I do think it's a strength and an asset, and that's exactly what we do here. All right, and of course, we do want to enable low latency scenarios. So, second piece to call out, I really want you to take away from this presentation today, is this accelerator process. I already said, of course, we've got the things that actually happen on the quantum hardware. Some fields apply to it, quantum state changes, but there's real-time computations that go with that. And the important part is, when you do go to other talks about quantum computing, especially the ones that are a little bit more focused at the surface level, at the here's what you can do with the things that we built, they're going to tell you about hybrid system and integrating quantum hardware into HPC system. Now, in I think pretty much all cases where I've heard that, they're talking about host process and the quantum computing part, these two together. No real-time computations in between. No real-time computations for application code. Of course, there's some classical processing happening, again, to make the quantum processor work, but that is not available for use in your application. And that's the very, very big difference. There's hybrid and there's hybrid, all right? There's hybrid and there's tightly integrated. We're going for tightly integrated. That's the part that I'm personally passionate about and I've been pushing for, trying to work towards, and it's very hard to get working, but a lot of fun. So that's the second big takeaway for you. Do ask what hybrid means, you know, and we want something more than just basically a one-shot communication. If you just have host process and the quantum computation, what that means is that when I call from my classical application code into a quantum processor, I send code down at that time, that code runs, I get answers back up, and then all the quantum resources are deallocated, basically. Your state doesn't live past that. You can't come back later on and ask it now to do something on top of that. When I'm talking about real-time compute, what that means is that I get to talk back and forth. I get to get responses from the quantum device compute an angle, depending on some measurement results, and then tell the quantum processor to continue its computation with new input now. And that's the part that's going to unlock a whole different set of applications if we can make that work. And there are some companies who do have support for that, by the way. This is not all hypothetical. This is reality. It's just not necessarily very carefully distinguished. It's kind of harder to promote, maybe. You know, HPC integration sounds great. This one requires explaining, but be careful about that. All right, summarizing what I said here, basically, important distinction is, you know, if we do have a separate process, basically, for each call into the accelerator, there's exactly just this one-time communication between the host and the accelerator process. And what we do want to have is really persistent, basically, classical and quantum memory across the different processors. So, now I said it's very important. Let me at least give a couple of examples on why it's important. It's always good to explain sort of where the take is coming from. So for one, clearly, we need that for control flow. And since error correction today is mostly treated like an application code, it's basically needed for error correction. You know, if you do want to do real-time error correction, you do run your error correction code like an application code. At the end, you measure some syndromes, you get data back, you do some processing of those, and that tells you what correction to apply. Now here too, a lot of error correction research today really just looks at having quantum memory. It doesn't actually run application code on top of the error correction layer. It's just having qubits sit there and measuring how long they can sit there and stay in the state that they're supposed to be in, right? If you do that, you can do it all offline, basically. You can just gather all your output from the error correction code that you gathered for a certain duration, and then take a month to process it. Doesn't matter how long it takes. Get the answer and check at the end, oh, was I able eventually to correct correctly? But as soon as you have application code that runs on top of your error correction layer, then there are certain things in the application that will force you to apply the correction, because you basically can't permute the next instruction with the correction that you need to apply. So that means now you need to be fast with processing on one end, and also you need the quantum state to remain coherent while you prepare the input that tells it what correction to apply, right? So clearly we do need control flow eventually for error correction. And here too, the first demonstration of that has already happened. Quantinum, for example, very nice hardware, very nice company, lots of that is exactly building on what I'm talking about. We're working with them before, I've been working with them before getting to NVIDIA. So, you know, again, this is something that exists. It's not all just on paper. Now, the other reason though why real-time compute is important is that basically, you know, there are workarounds today. People are creative. Of course, you get things to run, and as long as your application has 10 qubits that require 10 angles, that's kind of fine. And 5 iterations, all right. That's a very tiny lookup table, really, to say, okay, let me just evaluate anything classical in my code ahead of time, store it somewhere, and then I don't need to do any real-time computation. But as we scale this up, keep in mind, real quantum applications claim will have arbitrary control flow structures, much like classical code has. Just look at how other accelerators are used. GPUs are used, how FPGAs are used, and so on. You see how complex these applications eventually need to become. And then it's really infeasible to really have this gigantic table to look up all the values that you're ever going to need. I should also say, once we're talking about error-corrected device, you do need to synthesize rotations. So today you just apply a rotation gate, less directly with a pulse usually, kind of close enough, or at least not noisier than anything else on the device. But once you have error correction, what you need to do is have an actual finite set of instructions that you translate everything else into. So when you see something like rotation by pi over 4, you got to have to approximate this with some h and t's and so on, right? And here too, if your angle depends on measurement results, it is somehow need to retrieve that sequence in real time. You can't even compute the table for that, so you need a better approach. Then last but not least, if you actually run on quantum hardware today, you will find the code size is one of the limiting factors. You very quickly can end up trying to submit a code that doesn't use too many qubits, isn't even too deep or too long, but just code blows up. Because inlining everything, unrolling everything, yeah, it gets a little bit large, right? And not necessarily efficient. So if we can preserve the right kind of abstractions and do some amount of real-time compute that enables that, everything just overall will get much more efficient. All right, so bottom line is we do want real-time compute because workarounds are ultimately going to be too expensive to do and not realistic. And if we can get there, there's a whole universe of new applications. We've barely scratched the surface in terms of what quantum applications can really be, because everybody has been focused on, what if I just have a giant unitary? There's a lot more than that. There's heuristics. Look at all the heuristics and what you could do with it. Now, how do we make this happen? So on one hand, even for hardware that doesn't have support for real-time computations today, clearly we already leverage a lot of infrastructure. So for example, a lot of the hardware providers do have GPUs for one reason or another. One being that, if you look at error correction, of course, and you want to do something fancier maybe than just a tiny min-way perfect matching, maybe you go with AI and machine learning, kind of cater to the noise model to get a better decoding, then we're exactly in the world where just GPUs are really fast at doing that kind of work, so it pays off to have it. Similar things also hold for optimal control, where just leading methods are generally GPU accelerated. And then also calibration, very important ultimately. There's been a lot of work to cut down the time to actually basically boot up your system and get it into a functional state. And all that is very compute intensive. So it's not like the hardware isn't there. The hardware very much is there. And in fact, we've seen kind of Grace Hopper devices being very widely used. Oh, okay. I think I'm good. Thanks. So, there's good processors there that have GPU, CPU very tightly connected. They could, in principle, be used to put the runtime on it, have all the chip compilation happen there, and maybe even directly connect effectively to a quantum processor so that GPU and QPU can talk directly, for example, for the purpose of error correction. But it's not so easy to use that. This connection is kind of tricky. Again, whole fridges around it, so there's always custom work needed. And the custom work, unfortunately, is for every different qubit architecture, there's a slightly different kind of work to do. So the only thing we can do here is to actually take it step by step and be part of that development and help people with it, right? So I have no intent to just sit there and wait for somebody to tell me that I can hook up the QPU now like I do the GPU. We actually do want to help figuring this out. And so at the very high level, let's talk about that. So we need a vision for the future. Vision is good to have because somebody today is building what we're all going to be using in 5 years. I'm making no claims. I'll let you be your own judge on whether we are that entity or not. But somebody is. And if everybody just thinks about the needs of today, then 5 years from now, we're still going to be stuck with what we had today, basically. So it is important to see where this whole thing is going. Now, it's a nice visualization there, of building a car. Maybe also not quite optimal in that way, because we also need to be a little bit practical about this whole thing, right? So a better sort of graphic that you see, if you've looked at sort of development processes and so on, is that rather than starting with a wheel and then 10 years, we basically come back and say, yay, finally, our quantum computer is done. We do have a sort of something that works kind of, like a skateboard today, and then that evolves. It doesn't stay exactly the same for the entire duration, but we do try to roughly incrementally get where we want to be while keeping it somewhat functional in the process. Now, The risk with that is overfitting, basically, right? At different stages in the process, you know, it makes honestly sense to build different software. And I think this is exactly what we're seeing today. For a very, very long time, all the quantum computers could do is unitary, measure all qubits. That's it. For that, honestly, a custom abstraction and a custom compiler basically makes perfect sense because it's so ridiculously simple. It's mathematical, probably just formal verification tools are most suited to do that kind of work. But once we progress beyond that, where we have control flow, mid-circuits measurements, and so on, now we're starting to talk about really building a compiler, much like the classical compilers. And I'd argue now we're past the crossover point where any sort of Python library that is a custom compiler makes sense. We really do need to build state-of-the-art compiler tools, which is why quantum computing as a community, I think, has moved to LLVM, just like we have. Very happy about that. 2 years ago, I was the one very much pushing for that and launching that effort, and now I think we are there. And a lot of the major frameworks have either done that or are in the process of doing that, so that's great, right? So we do want to adjust for what we need today and kind of meet the need, but also if we're perfectly meeting it today, then chances are that we're not actually heading exactly where we want to be. And last but not least, a lot of this just is still requiring more research, requiring ideas, requiring smart people to solve the problem. And I have no illusion that I have all the answers. I do not. NVIDIA doesn't have all the answers. Nobody has all the answers, which is exactly why we need to be comfortable with the notion different people will bring different expertise, and what we do need is some formalization, standardization. It's not a bad word. 2 years ago, this was a bad word. In quantum computing, now again, I think we're starting to be better about that, so that in the end, we can each build the pieces we have the expertise for and everything fit together. So I said, it was a couple of years ago, that I'd been advocating for that. This was what the QIR Alliance was launched to do, literally, on one hand, to get everybody to actually use state-of-the-art compiler tools, and to make a first step at really a commitment to develop the interfaces basically together so that everybody can build bits and pieces and still guarantee that it fits together. I'll very quickly say the main goals there at that point that still hold today, of course, are allow for incremental progress. It's not hard to define what the future should look like. It's not hard to see what the today looks like, but to get from today to the future, that's the hard part, right? Because I can't just go to a quantum hardware provider and ask, yeah, I now need vectors of floating point numbers. When can I have them? It's not gonna happen. It's a lot of conversation. Integer support has been great. I've had so many conversations about whether 18 bits are okay to have, or does it really need to be 32, and things like that. We have left shift, but not right shift sometimes, and things like that. So it does need to be incremental, opt in, opt out. So at the same time, of course, a lot of software efforts, especially if they need to support a range of hardware providers, software providers, what they ultimately end up going for is the least common denominator, right? Because the thing that works across platforms is the thing that every platform supports. It makes life a lot easier, but it's also holding us back from actually taking advantage from real cutting-edge features that some hardware providers can make work. So we're not doing that. Makes it a lot harder to provide a good user experience. So if you ever run into a place where compilation just rejects the code and is not very nice about their message, bear with me. At least I'm trying to get you the features that are actually, unique for each platform. Then we do, of course, want to make sure that we can integrate this with other existing tools, in classical HPC and so on. And we want to stand on the shoulders of giants, right? There's decades of compiler research. Quantum folks are not going to reinvent it. We're just going to extend it, so to speak. All right, so back to Q to Q. Now, at the front, let me quickly walk you through a little bit the representations here. So we do support both C++ and Python as a front-end language, so much like CUDA that is basically expressed in C++. CUDA-Q also just supports effectively a subset of C++ and of Python. We are not a language extension, so intentionally we didn't make up our own custom syntax. We just basically say, yeah, annotate your kernel, mark it as a quantum kernel, and then everything that's in there is going to be extracted and piped through our own custom compilation pipeline. In principle, this could be all of C++. Realistically, we need to handle every single construct in a custom manner. So there are more restrictive rules, so to speak. You can't call arbitrary libraries from within a quantum kernel, since we have no way of getting that library down into a fridge and run there. All right. So I'll omit a larger discussion on exactly how do we do any sort of design time feedback to make your life as a developer easier. That's a whole other topic I can give a separate presentation about. If somebody has a workshop on that, for today, I'll skip it. Because we do translate basically then the language-specific AST. So we use the language tooling to get an AST. It's not something we custom write, Clang or Python interpreter. But we do then translate that into our own internal dialects. These are built on top of MLIR. MLIR is kind of giving us a nice tool set to just define the abstractions that we care about. It's kind of a level higher, so to speak, than QIR. We do pretty much all of our ahead-of-time compilation and also just-in-time compilation to an extent still on MLIR. By the time that's done, by the time we fully compiled a kernel, it's basically at the LLVM level then at that point. And specifically, the classical code is compiled to LLVM-IR, the GPU code to NVVM-IR, and the quantum code to QIR, the quantum intermediate representation. Now, QIR and NVVM-IR have the same approach. They're basically saying, well, it's LLVM with a more restrictive subset and special rules, right? Because again, LLVM is just huge. And so you do agree in the community on what subset of that to use and how to represent specific constructs that are needed for your specific processors, right? So we have a very, very similar approach here. And then below that, we see that basically, all right, I put assembly as the classical sort of equivalent of PTX there, because it didn't feel quite accurate to call it machine code, even though Clang usually directly goes to machine code. The IR for GPUs is ultimately first compiled to PTX, which here, interestingly enough, is still GPU architecture independent. Then that gets compiled to machine code and runs on the GPU. For QIR here now, there's the interesting part, because Quantum hasn't really talked about that format, about that equivalent of PTX. And that's the part, I think that's the next evolution that ultimately needs to happen. Because what this is effectively an instruction stream. So QIR, if you've ever looked at LLVM or MLR, you should be very familiar. It's very imperative, you know, still have sort of one expression per line or statement per line, so to speak, but very much sequential, you know, do a plus between these numbers, do a plus between these numbers, and so on. So if you use that for quantum, you still see H on qubit 1, H on qubit 2, and so on. It's not very vectorized, and it's certainly not actually having scheduling and timing information in the IR at that point. It's not scheduled, it's not resource bound, that IR. And so what I called here freely quantum very long instruction word format that is not existing today, to be very clear, but needs to come to life at some point, is a representation that basically says what does each logical qubit do for the next cycle. And then you push these cycles down into a buffer where a quantum processor can retrieve them and execute them, right? But this would then be a fully scheduled representation. So any sort of coordination still remains basically in the runtime. When the runtime generates these streams with data that it pushes down, basically, it makes sure that by the time it gets responses backed up, which are buffers of measurements, really, it knows where to put them, so to speak. but it really at this point has made all the decisions regarding what part of the chip are used for which computations, so to speak. All right? Now the reason that this is still at the logical level is again just bandwidth. Because if this is all in a fridge, pushing down physical pulses, it's not going to happen as we scale up. It's my claim. All right. So because somebody will always ask, where's my pulse layer? Here, below that. All right, under the error correction. So once it gets down into the fridge at some point there, you're probably going to have something like an ASIC ultimately that takes care of that. All right, let me quickly break here. Any questions so far? All right, that's a lot. All right, let's go order round.
Yes, thank you for the talk so far. You said that for your Python interface, you analyze the abstract syntax tree and then basically bind the instructions to a more low-level interface. Is it also possible to call this low-level interface from a user perspective, or basically do you shield your users and the only way to access it is through this AST analysis?
Yeah, I mean, MLIR has a nice existing infrastructure basically for generating Python bindings for its dialects. So what we convert to are the dialects, right? And of course, you can basically in-memory build, you know, the IR directly, so to speak. That's not usually very user-friendly, but you can do that if you want. So from that perspective, it is exposed via the Python bindings that MLIR gives you, and you could directly interface with that. Beyond that, we haven't simplified that in any way or made it more convenient at this time. We do have only few compiler APIs exposed. We're adding a couple of more. If you do want to do something like that, file an issue on GitHub, and we roughly know. The issue that we don't expose more is more stability, right? Our own internals are still evolving, and you know, we're not entirely ready to expose everything for stability.
All right, thank you.
In the picture, it seems like 100% of the decision about what goes on the quantum computer and what goes on the classical computer is made by the compiler. Is there anything left for the programmer in that decision, or is it really all going to be the compiler from back-end agnostic downwards?
We do rely on programmer annotations for what fundamentally are quantum kernels, right? So that we see very clearly where's this interface where we launch a new process basically on the quantum computer. Now the real-time compute, of course, just because you write your classical addition in there doesn't mean it happens in there. We do very aggressive constant folding and things like that. Our chit compilation takes the call arguments into account, for example. So it's a combination, I think, of both.
I have two questions. So Oak Ridge obviously is another company that is very invested in the sort of embedded hybrid systems for acceleration. And one of the things that they've been commonly bringing up in their papers is the fact that HPC inherently deals with very large amount of data. And one, we don't have quantum machines that are able to sort of even represent that data. And two, even if one day we get there, the initialization process for that large scale of data will be the bottleneck. And they've been sort of speculating of like this sort of multi-processor distributed systems for HPC acceleration. I'm curious if there's something going on in NVIDIA regarding that problem. And the second question is, I'm also curious about to what level you're actually backend agnostic, because there's very significant differences between digital and analog quantum computers, something like D-Wave machines. They're programmed very differently, and if you could speak to that a little bit.
Well, all right, let me start with the second question first, and coming back to the question on data input-output. So yes, I've not introduced any sort of distinction between kind of annealing devices and gate-based devices and so on. We do, of course, at the application level, so to speak, you can all bundle that up nicely in one holistic framework, so to speak. It's just libraries under the hood, and then, you know, you have very high-level solvers, so to speak, that says, time evolve, please, this Hamiltonian, and that's it. And we do try to we are in the process, in fact, on defining how these interfaces look like, to just define Hamiltonians, you know, have some sort of evolution and so on, that kind of fit in. We usually combine that with gate-based, probably less so, and within the compiler, of course, how this gets translated is very differently. So the answer is, of course, we do need to make custom investments ultimately for each backend. Also in terms of, you know, whether we compile for superconducting or compile for ions, compilation is slightly different, right? So it's not that automatically, if you come up with a new qubit architecture tomorrow, it will just work. But from a user perspective, that's, you know, we invest basically making that happen.
Follow-up question, sorry. On the PTX is basically shielding, you know, not only users but also developers from actually being able to access the GPUs. But does this also mean then, on the quantum side, that CUDA and in this case NVIDIA will control internally the development of drivers, which are very complex and evolving and very different to quantum processing units?
So you'll see CUDA-Q maybe having some differences in terms of how it's rolled out and positioned already compared to what CUDA was at the time. One difference is that explicitly we're not manufacturing quantum hardware, right? By the time CUDA came out, it was very different. NVIDIA very much was actually manufacturing the hardware for it. CUDA-Q is fully open source also, so not the proprietary software that you're used to from CUDA. And as you've seen at the QIR Alliance, now our focus is to work with people to help define that. But our goal is to be a facilitator, really, that also has the liberty to look at all the different architectures and try to identify what makes sense without any stake towards any particular kind of architecture. But we're definitely not dictating anything here. It's also not per se intended to shield, though I do think there's a lot of value in a separation of concerns in the stack, right? And encapsulation, so that's going to happen. Yeah. All right. If you don't mind, I'll take the Oak Ridge question offline and we'll proceed a little bit because I do have a time heads up here. Okay, so now I'll skip more details on MLIR, LLVM. I think the audience here, you're all very familiar. It's a great framework. It's open source, lots of research happening there. That's all the reason why we use it. And of course, there's a lot happening during compilation. Here too, for this talk, I don't want to talk about the detailed pipelines, and please don't take a screenshot and here's exactly how it's going to be compiled. No, and this is not even how we compile. There's a lot of loops in there, generally. It's not quite that simple. But main outline for compilation is that we do have a split compilation model. As I said, basically we do have at the source level potentially everything in one file, quantum kernel, surrounding code, calling out to other libraries and GPUs. But then we actually grab the relevant bits and pieces and feed it into our own pipeline and have a patch up basically at the end. This again is very similar ultimately to how also CUDA compiler tool chain works. And it allows us to make our own decisions really for when to compile what. So what we do in check as part of this process is on one hand, of course, the necessary infrastructure for data exchange between different processors. That's the idea, to automatically handle that to a good degree, but also just the infrastructure to actually have JIT compilation invoked when it's needed and so on, right? And what this gives us is that at the source level, you know, our source code still has MPI. I can use in there OpenMP, all the standard tools used for parallelization, and that's all handled via the runtime that we have. So back to our original high-level slide, CUDA-Q as a tool chain makes it available in popular tools, makes popular tools and libraries available, C++ and Python currently. If somebody wants Rust, I really want people to upvote having Rust in there. Right now I don't have enough demand for that. We do support a diverse range of QPU architectures. Often hardware providers actually contribute the basic integration. Right now that's a very not tightly coupled integration, but we do have ongoing projects. For example, with Quantum Machine is the one that was announced. We do have some other ongoing projects for tight integration, and hopefully next time round at the workshop, I'll be able to tell more about those. We do want to make sure that we can seamlessly transition to a large-scale system, and we're compatible with all the modern tools. And we also want to make sure that we can actually make this advanced functionality available. So our kernels are not a builder model where you just attach gates to your quantum kernel. There are actually kernels with classical compute in there. If we can run it on the quantum hardware, we'll run it on the quantum hardware. If we can't, we'll compile it away as much as possible. If it's entirely impossible to compile it away, then you'll basically get a compilation error when you try to target a backend that doesn't support it. Hopefully that should give a cohesive enough user experience and provide the necessary flexibility also to do further research and development with the stack. All right, so check out GitHub. This is mostly all open source. Couple of nice things that we have in there and some graphs in terms of performance benchmarks. Our language model does have quantum specific things in there like sampling, observe, just common patterns that people use in quantum computing. And under the hood, we specifically invest into optimizing those. A recent plot between 0.6 to 0.8. 6 was January, 0.8 is this summer, is that we have optimized a lot of under the hood handling, coordination, processing. That will give us a good factor of speed up here. Then we do also have quantum specific data structures like spin operators, means to define a Hamiltonian, and to a degree we do use OpenMP, for example, under the hood to parallelize when it's reasonable to do that, right? So processing times are very much cut short, only the quantum time remains. Then generally, a lot of what we have is multi-threaded, amenable to parallelization. If you have multiple kernels, of course, you can use MPI to distribute them across a range of processors. You can also do that across other arguments. So if you have this Hamiltonian with a lot of terms, for example, you can parallelize across terms. And then as you scale up and use more virtual QPUs, so to speak, you can really see how much this would accelerate your application. Since most systems don't actually have more than one QPU right now, we do have simulators to mock up the QPUs if you don't have 5 of them concurrently available to you. Our simulators are very fast. There's different slide set on that. We do have state vector-based simulators, tensor network-based simulators. We're working on support for really fast trajectory-based noisy simulation coming out sometime towards the end of the year. So for those that work on that, that should be interesting. And last but not least, we do actually started to expose a little bit of APIs to configure a platform definition that says, oh, I've got a platform with 5 QPUs and 3 GPUs. How would it look like now to work with those, right? So this is kind of where we want to go, what kind of work we want to see ultimately with the platform. And if all of that sounded interesting to you, then you should definitely check out CUDA Quantum on GitHub, PyPy, NGC, which is Docker images. You can also use the images with any other container runtime. And for those of you that now are worried that these tools would be awesome if they just had GPUs, there's also NVIDIA Quantum Cloud for those who don't have GPUs. All right, thank you very much.
Thank you very much. So I suggest that we set up for the next talk. And in the meantime, we have one short question. Yes.
Okay, yeah, I have more interfacing questions. The MLIR dialect you talked about, is it something that you made up, or is it an existing dialect? And follow-up question, if I submit an MLIR file, is there an easy way to compile it down to QIR using your infrastructure?
So if you have your own custom dialects, right, you need to define your own basically lowering to LLVM for that dialect. We do use some of the existing passes, structure control flow, for example, function dialects to represent callables. We do also have our own dialect, Quake, for the quantum specific things that basically defines qubits and things like that. So it's a combination of the two. Now, at the beginning when we started QIR Alliance, it was kind of a topic like where do we go, MLIR, LLVM, where's sort of the right layer. And reason for us to stick with LLVM is that it's just for standardization, right? MLIR has the strength to be customizable. But that also means it's usually custom. So we don't try to standardize basically our MLIR dialect with anybody else. We have ours evolve even, you know, between a year from now, our dialects are going to look slightly differently because we adjust to basically new needs. Hopefully all of that should be additive. So we should probably still have what we have today in the dialects, but maybe some additional abstractions. But if you do want a stable, basically, format, then yeah, this QIR is what the standardization is on, right?
Okay, thank you.
So thank you very much, Bettina. Okay, I think we can switch over. So yes, so this is from the TU München, and we're talking about the Cubo maker, as I see, right? Yeah. So converting some path problem to a Cubo and then compile it into the quantum computer, so to speak, right? Okay. So then the stage is all yours, and thank you very much for being here.
No? Okay, all right. So yeah, thanks for having me. My name is Damian. I'm from the Technical University of Munich, from the Chair for Design Automation. And today I would like to talk to you about how we plan to support end users in realizing quantum computing applications. And in that, we want to look at some problems that we have found that many end users occur, and our solutions that we have provided for these problems. So many of you might be familiar with the general process of how to solve some problem using quantum computing. Typically, when you start with a problem, you find some algorithm that might be suitable for the problem, and then you encode the problem into some format that the algorithm can work with, and you translate all of this into a quantum circuit. The quantum circuit, you run it on some device, for instance, and you end up with a histogram. And this histogram you decode to get your actual solutions. Now, for people who are already into the field of quantum computing, this sounds like a very simple task. But actually, if you're someone coming from the outside, then there's a lot of places where things can go wrong or where things can become more difficult. Actually, already in the very first step of encoding, there are areas that require quite a lot of expertise in quantum computing. For instance, what does it even mean to find an algorithm that is suitable for my problem? I would need to know how the algorithms work, which algorithm works best for me, and so on. And then how do I translate this problem into a format that the algorithm can work with? And even if we can answer these questions, there's further problems, like during execution, where we have to work with compilation, and you have the questions of how do we actually want to compile our problem? And we have to think about physical considerations, like what devices are actually best used for our specific problem. So all in all, it's very clear that there are many places where end users can face problems. This is especially the case when people are not really experts in quantum computing. And as quantum computing becomes more and more popular, many people from the outside are coming in. And they definitely need something like tool support. They need software that can help them in the field of quantum computing. And for that, we have come up with the Munich Quantum Toolkit, the MQT, which is just a selection of open source Python software and also C++ software that users can employ to solve different problems all around the quantum computing stack. In fact, for us, that includes the application layer, but it also includes layers such as simulation, compilation, verification, error correction, even some hardware design. And we have some common data structures in the background that you can use to actually represent your quantum states and stuff like that. But in this presentation, we're going to look just at the application layer, which is the layer that most end users are actually going to interact with. Now, going back to this workflow diagram, as mentioned earlier, there are a lot of steps that can be quite difficult here. But also, there are areas that are quite error-prone. Imagine if you're working on a very big algorithm, then it can happen really fast that some mistake happens somewhere inside the circuit, And once you have a big circuit, it's very, very difficult to actually find this error. So one would think, wouldn't it be nice to have some sort of framework that goes around all of this workflow, that giving some problem formulation and some quantum algorithm automatically does all the encoding and running for us, and we just need to call this framework. Well, we're trying to come up with something like this, and for that we have split the workflow into two domains, the classical domain and the quantum domain. In the classical domain, the end user selects some problem specification and some algorithm, and then the tool automatically transforms this into a quantum circuit, runs the circuit, decodes the results, and finally translates the results back into the classical domain. And there the end user can access them again. The long-term vision for this is to support a very large variety of different problem classes. And we also want to provide the same interface that end users might already know from existing classical solvers. And a very cool thing about this idea is that the end user is completely shielded from all required quantum computing knowledge, because everything related to quantum happens in the backend. They do not need to interact with it at all. And this tool is what we call the MQT problem solver, and it's available on GitHub. And as a starting implementation, we support just a few different problem specifications, but we are working on actually improving this further. Now, going back to this workflow diagram, looking more specifically at the execution and decoding part, nowadays, there's really two ways that one can actually run a quantum circuit. Either you use some existing quantum device for it, or you simulate it. But in both cases, we face a similar problem. If we want to run some algorithm that requires, let's say, 2,000 qubits, then this is not going to work, because neither quantum devices nor simulators provide so many qubits. That's why nowadays an alternative approach is becoming popular that's called resource estimation. In resource estimation, we don't actually run the circuit, but instead we get some estimate on required numbers of qubits and required runtime and so on. Now this way we do not get the actual results of the circuit, but we get some sort of estimate on what we can expect from the circuit. Like when can we actually expect the circuit to be executable on real hardware by comparing it with vendor roadmaps. Going back once again to this workflow, there's more specific areas that actually could also help with, could also require some help for end users. For instance, the encoding part. Now, if we have some problem and some quantum algorithm, and we want to create a quantum circuit for this, this can be hard or difficult, but also easy, depending on what exact problem you're looking at. Let's say, for instance, we're looking at a max-cut problem. We already have a lot of literature on how to create quantum circuits for max-cut problems, so we will definitely be able to somehow create a circuit for this. On the other hand, like what if we look at a traveling salesperson problem? Once again, there's existing literature, there's existing tools. It's not going to be such a big problem to create circuits for these. But what happens if we look at something just slightly more complex? Maybe the same max-cut or traveling salesperson problem with some additional constraints. Well, it happens very fast that this simple process can become a very big question mark. And the big problem here is that actually if you're some end user coming from the industry, then usually you don't have to look at some pure max-cut or some pure traveling salesperson problem, but you have your very specific constraints, and you somehow need to create a quantum algorithm for this. And for that, we have created MQT Cubo Maker. And let's look at this with an example. Here we have a circuit, and let's imagine we're some logistics company that needs to deliver objects to different locations, marked by these vertices from 1 to 10. Now, we have some specific constraints. For instance, we want to visit vertices 1 to 8 exactly once, but 9 and 10, we want to visit them twice. Maybe because 9 and 10 have some locations that need multiple deliveries a day. Also, we don't want to visit vertex 2 before vertex 3. Maybe we need to pick up something from location 3 and bring to location 2. Also, we don't want to take the edge from vertex 5 to vertex 6. Maybe we know that there's construction work going on that street, so we don't want to risk getting into a traffic jam. And also, we want to enter the starting vertex so that we can leave the car there overnight, for instance. Now, there are existing quantum algorithms for this. For instance, the quantum approximate optimization algorithm, QAOA. And the thing is that these algorithms usually require some sort of format. In the case of QAOA, this is the Kuber formulation. But the problem is, it's not quite easy to create a Kuber formulation for some problem instance if it's complex like this. In fact, if you have never used quantum computing before, then most likely this is going to be almost impossible for you. And if you have experience with quantum computing, even then it's going to take a very, very long time. And you end up with like a big formula and have no way of knowing, maybe I've made a mistake somewhere in the middle there. And for that we use MQT Maker now. And once again, it's open source and available on GitHub. And it's a tool that can create Cuba formulations for some specific problems instances. In particular, it can create a Cuba formulations for all sorts of pathfinding problems in directed graphs, as long as they can be translated into a set of constraints like these here. And for that, we also have a graphical user interface so that you can actually use it without writing any code at all, where you can just select the constraints that you're interested in. And then by clicking just a single button, you can generate a Cuba formulation. And another cool thing about this is that you can also change encodings. So typically Cuba formulations are given in some sort of encoding, such as one-hot encoding or binary encoding. And if you want to change your encoding, then you have to start all over from scratch if you're doing all of this manually. Now with this tool, you just press a single button and change from one-hot to binary, and you get the new Cuba formulation immediately. Now, what does it mean to get a Cuba formulation? Well, the MQT Cuba Maker supports multiple different output formats. We have a Cuba matrix, but we also support a Cuba cost function that might be a bit easier to read. And we also support generating directly a quantum circuit for your problem. This way, if you have no experience with quantum computing at all, you get the circuit immediately, and you're once again effectively shielded from everything that requires quantum knowledge. Now, returning once again to the workflow, there's another area where end users might need support, and that's in executing a quantum circuit. Yeah, so that's in executing a quantum circuit. Typically, you can't just run a quantum circuit, you need to compile it first. And that begs the question, how can we actually optimally compile a quantum circuit? That's actually a quite difficult question that many have looked at. But in our case, we split this task into two individual steps. The first step is device selection. Let's imagine we have a set of different quantum computing devices, and we want to select which device is actually the best one for our specific circuit. The second then once we have the quantum device, the second step is the actual compilation. Each device supports a set of native gates that we need to translate our circuit to, and then we also need to map our circuit to the topology of this device. Now, putting these things together, we get a tool that we call the MQT predictor. The MQT predictor is an automated tool that does the device selection and compilation for us based on different machine learning models. For device selection, we use a classifier that decides the optimal device based on some characteristics of the circuit, such as the gates that we want to use and similar things. For compilation, we use a reinforcement learning model. In this reinforcement learning model, we train it using a large set of different circuits for different quantum devices using some figure of merit. In our case, we use as a figure of merit the expected fidelity. And after training, we end up with a reinforcement learning model that can compile for this specific device a large number of different circuits. And putting these things together, we end up with MQT predictor. It's an easy-to-use tool. Once again, it's a black box model. You do not need any quantum computing expertise to run it. And another cool thing is that the figure of merit that you can use is customizable. So if we ever decide that maybe the expected fidelity is not really what we want to look at, then we can easily change it. Now, one thing I've talked a lot about is using different software to help end users. But any software can only ever be as good as the tests we run it on. That's why we've also come up with MQT Bench. MQT Bench is a benchmark suite that contains more than 70,000 different quantum circuits on different abstraction levels that one can use to test their software. So you can imagine if we, for instance, write two different compilers, we can use the circuits in this benchmark suite to compare them and evaluate them. MQT Bench is available as an online tool. We have a web interface where you can actually select the circuits that you are interested in, the types of algorithms you're interested in, and also the abstraction level you want. Maybe you want the circuits already compiled to a very specific device. Maybe you want them compiled or just translated to a set of native gates. And yeah, with that, we've come to the end. Once again, to repeat it quickly, it's a very important goal for us to support end users by providing different tools. And tools like Problem Solver to hide the entire quantum workflow, tools like the Cubo Maker that can help with very specific problems, and tools like the Predictor that can handle the circuit compilation for you. But there's also many areas that still need further support. And for this, we provide tools such as MQT Bench to actually test any software you want to write. Now, as quantum computing becomes better and better, as I mentioned earlier, for sure there will be people coming in from the outside. And we are running the risk that at one point, the quantum hardware might be really good, but the tools we have is not good enough at all. And that's why I think it should be our main goal to make quantum computing accessible to all using tools like these. Thanks a lot, and I'm open to any questions.
Indeed, thank you very much. Here goes our first question and the second one.
Thank you for the presentation and the work you do at TUM. So I have actually two short questions. The first one, am I understanding correctly, like there's no code snippets that you could provide because it's like an online interface for the user to just click and drag and solve the problems? And the second question is, it came into my mind because recently a colleague from a different group at Focus published a Cubo Solver benchmark where he also uses the minisync approach. And how is your Cubo problem solver maker different from like the minisync approach is also kind of a staple in the Cubo industry? Thank you.
Good questions. The thing about the Cubo Maker is that it's not actually meant to be a solver. It's meant to be a tool that helps you actually create the formulations of the problems. So also this online tool that I showed you before, it doesn't give you the exact results of the Cubo question. It just gives you the Cubo formulation. So because of that, you still need to use some code later on if you actually want to solve it, or you use one of the other tools that I've talked about to actually input it there. But yeah, it doesn't give you the exact results, so you do still need some sort of computation. And I think the same question also replies to the other question, since yeah, we do not really do the solving.
I have a question about the resource estimation.
Yes, of course.
As a user, can your tool help me understand how big of a problem instance I need before quantum computing will be faster than classical computing?
Admittedly, the resource estimation part is still like pretty much work in progress. I do not think that we have some sort of estimation like this, but I think this is actually something that's definitely on our roadmap because it seems like it's a quite reasonable goal and it shouldn't be too hard to implement, but currently cannot do that.
Yes, first of all, let me answer your question. There has been 2 papers on that, one from Microsoft and one from Google, and they basically estimate after crunching all the numbers like magic state distillation, everything, that if you've a quadratic speed up, you need a problem that runs at least for 2 weeks. So quadratic is most likely not where it's at. They say quartic is more realistic. And yes, now my question for the Cubo Maker, and how do you handle the constraints? Like you need to have this penalty factors, which can turn out quite of a mess if you automate their determination, because like if you do them too big, then the quantum computer can't resolve the actual problem anymore. If you do them too small, then the constraints might be violated. How do you solve that?
Yeah, going back to the slide. Yeah, so here you see like a set of different constraints that we support. For all of these constraints, we have pre-computed how they interact with each other. So that means we have some general penalty factors for these sorts of interactions that we already have, that we already know. So the Cubo Maker just uses them. So none of these constraints interact in a way that's so complex that we cannot use these pre-computed constraints. But also, admittedly, we haven't done any evaluation on how well these specific constraints perform exactly. So, sorry, these specific penalty factors perform. So that means that we could still do some sort of testing to see if the penalty factors that we're using actually work well, specifically with existing quantum devices. But yeah, currently all of these are pre-computed.
Okay, so I would suggest that we set up the next talk, and if there is one more in the meantime, so who's the next one? Data flow based optimization? No? Not today? Oh, it's online? Oh, that is interesting. Okay, good. Then it's already almost set up, right? So one more question maybe, or is everything fine so far? Okay, then let's thank you, Damien, again. Yeah.
Hello, Junji.
Yes.
Yeah. You can get ready.
Okay, so I turn on the camera.
Okay,
Yes, camera and the slides.
So we don't see yet, but welcome. I think you can hear us. So next talk is about something that is Bettina just already started to talk about, the QIR. So we're gonna hear a little bit more on this. As soon as we're ready, you can start.
Data flow-based optimization for the QRR programs. My presentation is in 4 parts, and in the first part, I will introduce the QRR. The name of QRR is the intermediate representation developed by the Microsoft, and it is an intermediate representation for the quantum program language. It's also a memory-based semantic IR, which means that it represents the qubits with the pointer to the registers, and the qubit is the side effect of the function. We show this feature with an excerpt of the code convert from the Q-sharp to the QIR. The Q-sharp code includes 2 functions. It first allocated a qubit array with 3 qubits, then perform an H-gate on the last qubit. Then we can see how these 2 functions convert to the QIR code. Similarly, it allocates a 3 qubits qubit array, but before performing the H-gate on the qubits, it first needs to get a pointer pointing to the qubit register. Then the H-gate is operated by the side effects of the QIR H function. In our presentation, we use the prefix ABBR to indicate that the instruction is represented by our simplified representation. Such a design leads to 2 problems in optimizing the QR code. The first is that it prevents LVM built-in optimizations from being used in QR code. Let's use a loop in the QIR code as an example. We can find that if first allocated a qubit array with 2 qubits, then the function array gets size return the array's length as a block jump statement at the end of the block 1. If the dot not, then jump to block 2, otherwise jump to the block 1. Use LVM's use-defined chain, we can trace that the dot not is obtained from the size of qubit array, the qubit dot I. However, since the size of the array is obtained from the function array size, and the implementation of this function is left to the backend hardware or the simulator. The LVM optimizer cannot obtain the value of the array length directly. For this reason, the LVM optimizer cannot perform the built-in loop lowering optimization. Another problem with the memory-based semantics IR is that it incurs the additional cost of the load data. We use a longer piece of code to demonstrate this. In this code, in addition to allocating a qubit array of length 3 and using a H-gate, a CNOT gate and a conjugate T gate are added. As described earlier, a pointer to that qubit needs to be obtained before performing a quantum gate operation. And we can find that the quantum 1 actually points to the same qubits as qubit 3 and qubit 4. And that qubit 3 and qubit 4 are aliases of the qubit 1. The presence of aliases result in additional qubit loading overhead, since obviously anywhere the qubit 3 and qubit 4 needed to be used can be replaced. Apart from that, in QRR, for quantum gates, it is necessary to generate a way to store the control qubit first. We denote this step as the ABBR array create. Redundancy is just as likely to occur in this process. For example, the quantum circuit shown in this figure, the QRR will generate 3 identical qubit arrays to represent the control qubits that stores the qubit like this. Also, we use a QRR program for the Hopefully gate decomposition as an example to introduce the realistic redundancy in QIR. This program consists of a total of 5 single synopses. So a total of 21 instructions to get the pointer of the qubit from the qubit array occur in the QIR code. Also, since there are 6 CNOT gates, so 6 control qubit arrays need to be created. That is, the ABBR array create instruction needs to be executed 6 times. In fact, only 3 ABBR get PTR instructions are actually needed to get the pointers to all the qubits in this program. Similarly, since there are only 2 control qubits array in the contain the QS0 and QS1, so only ABBR array create instructions are needed to get the control qubit array required by the program. That the QRs have significant potential for optimization. In our work, we present our members is mainly 2 parts. The first is that we refer to the semantics of the QRR instruction in the specification and perform some of the classical computations in the optimization process, thus providing the opportunity to apply the system optimization on the QRR code. The second one is that we try to eliminate the redundant instruction in QRR programs with the alias analysis. Those of optimizations which are classified in 2 types in optimization. Optimizations based on the QRR syntax include the QRR inline, QRR unroll, and QRR total elimination. And also the optimizations based on the alias and analysis, including QDFO load and QDFO create. We'll describe each of our optimizations next. The first optimization we introduce is QRR inline. We need this optimization is because in QRR, the function code may need to be executed by QRR-specific methods due to the provision of an automatic generation of the controlled or the adjoint version of the operations. Specifically, the QRR generates a function table and is callable, and then calls each function in the function table with the QRR to call some OP, it needs to call the function the callable invoke. In such a case, even though we can semantically analyze the function it invokes, the LVM optimizer can inline it with the function some OP. To solve this problem, in our method, we make it possible to inline at the stage of the QRR code by directly replacing the callable invoke with the function it actually calls. That allows all the operation into the optimizer to be applied to the QRR code. So for the loop unloading in QIR, we are concerned with the problem of the LVM optimizer cannot obtain the length of the array returned by the array get size function. In our approach, we utilize the LVM use define chain to find the instruction that allocated the qubit array. Based on this instruction, we can length of the array directly modify the use of this length to the corresponding int value. The obtained code can be unrolled directly use the LVM optimizer's loop unload method. And then we design two methods, the QD4 load and QD4 create, to optimize the redundancy problem of the load qubits and the qubits are separated with the existing qubits. As previously described, the qubits routing occurs in the QR code. In our method, we use a multi-dimensional vector to this problem. Specifically, we take each allocated array and collect the definition of the pointers to each loaded qubit. After that, for qubits, we replace the definition of the corresponding pointer. In this example, we use qubit 1 to replace the qubit 3 and qubit 4. After the replacement, we can eliminate the redundant instructions with the QIR DCE optimizations we designed. After some of the optimization, there may be some unneeded instruction that returns the qubit pointers or return the array length. To handle these instructions, we designed the QIR DCE optimization. Optimization removes the instructions whose current values are not used, as well as the remove mode does not affect the program behavior. Also, we designed the QDF create to eliminate the redundancy of the qubit arrays that are generated from the existing qubit. In our method, we adopt a similar strategy to QDF load by determining whether the qubits stored with each qubit array are identical, and replacing the pointers of the newly generated qubit array with corresponding pointer. In this example, we replace the control QS.I1 and control qubits.I2 with the control QS.I1 .I. So we plan a workflow for our optimizations. QIR inline and QIR loop unrolling in the preprocessing phase to unfold the code, which can provide more contextual information for the optimization. After that, execute the QFO load and QDFO create optimization to eliminate the redundant code. We use LVM's O3 optimization in our optimization process because some of the classical optimizations, such as the inline, the loop unroll, and DCE can be reused. So to validate the effectiveness of our approach, we conduct the experiment based on the IBM quantum dataset. We evaluate the effectiveness of our optimization by measuring the reduction of the instruction on the set. Before executing our design optimization method on the QIR program, we first perform an O3 optimization to exclude the effect of the classical optimization on the results. Results show that our method reduced the number of instructions as the number of quantum gates used in the program increased. We believe that there are two main reasons for the result. The first is that the increased proportion of quantum computation in the program provides more optimization opportunities for our method. The second is that as the number of quantum gates increase, the program generates redundant operation on the loading of qubits, and the general qubit arrays also increases. The result verify the importance and the effectiveness of our method, especially in large quantum programs with better performance. In addition to the experiment, also work on common quantum algorithms for case studies. With 5 qubits, our optimization method provides a total of 1 in 9 and 9 loop unroll opportunities, reducing 83 and 8 line of code by QDF flow load and QDF flow create methods, respectively. So, conclusion, in this work, we propose and implement the QRR data flow-based optimization algorithm, the QDFO, to optimize the QRR programs. Our optimization provides opportunities for reusing of the classical optimization, reducing some of the redundant operations in QRR. We verify the effectiveness of the methods by studying and optimizing a series of real-world QRR cases. Thank you for your attention.
Thank you very much, Janji. So, are there questions right now? Please. Is that
okay?
Yes.
Oh, for this IBM curve that you showed that sort of flattens out at 87%, could you say something about why that curve is what we should expect? Why that it has that shape?
In fact, it's not a curve because the it's a log n for the x allies, so it just looks so curves. But in fact, if we use the use the common way to express this feature, it will become a straight line of the result.
Okay, is there another?
Yes,
yeah, is that clear? Or do you have a follow-up?
No, I don't even know what to ask now.
No, thank you.
No, I think, can you give it another try with the answer?
No, maybe.
Okay, okay. No worries. Okay, then we'll keep it there. Okay, and another question. Yes, there's one more.
Yes, so do your transformations only affect the classical processing, such as array sizes, indexing, and loading, and so on? Or do they also change the gates executed by the circuit? For example, do they remove redundant X gates, things like that?
No, in fact, we do not perform any of the circuit, quantum circuit optimization or optimizations. Maybe it will be our future works.
Okay, that was also my question. Good, that has been answered. Any more? Okay, then let's thank the speaker one more time.
Oh, thank you very much.
So let's go to the next speaker. Now we shift gears, so to speak, a little bit more into the low-level realm. As I understand, we're talking about an open source framework for performing the quantum calibration and characterization. I think it is primarily about superconducting qubits or spin qubits, right? Superconducting. Okay, good. Then, if it is set up, I will give you the mic. Yeah, it's okay. It's gonna take just a second.
Okay. Okay. Thank you. Hi, I'm Edoardo Pedicillo, a PhD candidate at the University of Milan. and today I would like to introduce you the Kibo ecosystem. So Kibo is an open source project that is aimed to have a full stack approach on quantum computing. So as already said in the introduction, from the circuit level to the pulse levels. And it's developed by labs and national quantum hubs that are listed in this slide. This is a scheme of the whole Kibo ecosystem. I mean, don't be afraid, I will not speak about all of these in the slide. Let me just mention that the main core of the Kibo ecosystem is the Kibo API. So the API that we are using to deploy the quantum circuits and to simulate them on classical devices like CPUs, GPUs, or multi-GPUs. But today, I would like to speak more about the hardware, the quantum hardwares, in particular the KiboCal, the library that we are developing for calibration, characterization, and verification of quantum devices, and KiboLab, the other library to control the electronics in the lab. So let me jump directly into KiboLab. First of all, just for the context, I want to show you a picture of a quantum lab. This is a superconducting qubit lab that we have at the Technology Innovation Institute in Abu Dhabi. As you can see, there are some cryostats and where the qubits are placed at low temperatures. And then we have some control electronics and other instruments like oscilloscopes, and all together is wired. This is a scheme of the picture that we have seen before. And usually, when we want to perform an experiment in a quantum lab, we want to be able to connect through a host device to the control electronics in order to generate pulses and send them in specific lines, readout, drive, and flux line. And then at the end, collect back the output, that is another pulse. In KiboLab, we want to do it in a platform-agnostic way. This means that in our labs, we control several chips with electronics coming from different vendors. And this is thanks to the modularity and the abstraction of KiboLab itself. Mainly, the main concepts of the KiboLab API are the platform and the pulses. A platform consists of a specific chip that is controlled by a specific set of instruments. So, as you can see on my left, the platform class will contain a qubit map, where the qubit class contains all the information about the specific qubit, for example, the readout frequency, the drive frequency, but also the pulse sequence for generating specific native gates. And then we have the instruments. The instrument class contain all the low-level drivers in order to control that specific lab equipment. At the end, the platform class will also have specific methods like connect, disconnect the platform, and execute pulse sequence. The pulse class is just a representation of the physical pulses, so it will have attributes like the frequency, the amplitude, the pulse shape, and so on. And so at the end, in using just KiboLab, we can send easily, we can run easily specific pulse sequences. For example, here we have just to allocate the platform and then create the pulse sequence. In this case, it's just a measurement gate. And then just running the pulse sequence through the platform. So now that we can control a quantum lab, we are trying to calibrate also the quantum chips. Usually calibration is important because when we want to try to execute circuits on a quantum device, we cannot do it out of the box, but we have, first of all, perform a specific set of experiments in order to reduce as much as possible the noise and increase the qubit fidelities. I mean, these are some examples of what we call protocols. Usually the protocols are divided in three categories: the one improving the gates and the readouts, the one for benchmarking, so for checking the quality of the calibration, and the optimal control ones that are just, let's say, changing the shape of the pulses to reach specific goals. These are just some of the routines that Kibocal provides. In particular, we have routines for the calibration of single to qubit gates and the readout gate, and for the benchmarking. Also in Kibocal, we are trying to use a modular approach. And for this reason, a protocol is defined by a specific set of data structures and functions. So in this case, for each protocol, we have the parameters that are the inputs parameters of the experiment. Then we pass the parameters and the platform object, that is the platform of the Kibolab library, into the acquisition function. The acquisition function will generate the sequence for that specific experiment and then will run it directly on hardware. The results are, so the output, are collected in the data, and then the data are used in the fit function. The fit function is just a post-processing. We call it fit just because usually we try to fit the data with a theoretical model. And then we extract from this fitting some parameters that we use to update the platform, so to find a better lab configuration. So usually when we want to, let's say, run a specific calibration experiments, first of all, we have to understand what is the goal of the experiments, and so define the set of experiments that we want to run. For example, here the punch out, the qubit spectroscopy, and the RAPI. Yes. And we have to run. We have to write in Kibocal a rankard. The rankard is a YAML file collecting informations like which platform we want to run, in which specific qubits we want to run it, but also the list of the experiments with their IDs and their input parameters. Then with a command, QQauto, we are able to run the list of experiments sequentially on that platform and that qubits and update the platform. At the end of the calibration experiments, we are also able to generate a report. A report is a HTML page collecting all the results in plots and tables. Apart from the QQauto that we have already discussed, Kibocal also define other commands that are specific for the different actions of the protocols. So QQacquire will just acquire the data, QQfit will just take the data saved in a folder and post-processing it, and then the report generated the report. This is mainly done because we want to disentangle these actions and maybe run it in different times, in different moments. Sometimes, since we are using Kibocal to calibrate our quantum devices, we realize that for specific tasks, writing a YAML could be cumbersome, and sometimes we want also not to follow a linear set of instructions, but doing some if-else and so on. So for this reason, we are also developing Kibocal as just an API. So this means that to calibrate a chip, we have to run a Python script. And here, what we have just to do is define the set of parameters in a dictionary, define the executor, and then run, in this case, this experiment is the flipping, through the executor. Okay, So just at the end, let me show you what we can do with this, let's say, ecosystem. First of all, just using Kibocal and Kibolab, we can, I mean, we are developing a monitoring tool. So at a specific time intervals, we are running some experiments to collect some parameters. In this case, we have the T1, the T2, and the readout fidelity. In a specific case, for example, if the fidelity is too low, we want to trigger a job in order to calibrate the qubits and try to rise the fidelities. Also, just, I mean, another thing that we can do is benchmarking the different drivers. In this case, we have evaluated the execution times for different experiments and for different drivers. And as you can see, the black line is the ideal execution time, that is just the duration of the pulse sequence, and the other ones are the execution times of the different drivers. As you can see, the real time is higher than the ideal time because we have some overheads from the Kibo ecosystem, from the instruments, and the communication between the two. So, at the end, with the whole ecosystem, as said at the beginning, we could try to allocate a circuit with Kibo, like this one. Then, if we have access to a quantum device, we could calibrate it with Kibocal and run the circuit directly on the hardware. Kibolab itself will translate the native gates directly into pulses, as we have already seen, and then just run it and collect the results. So the main point of the whole Kibo ecosystem is the modularity, as we already seen with the protocols in Kibocal, with the platforms in Kibolab. Let me remind you that Kibo is an open source project, so if you want, you are invited to have a look at the documentation, to the website, and also to contribute. Thank you very much.
Thank you very much. Yes, excuse me. First question. Yeah, okay. First, second.
Okay, thank you for a report. And I'm rather curious about what the way you perform the calibration. And I want to know what kind of noise will you consider when performing calibration? And will you consider the physical properties of those noise, for example, crosstalk or leakage, or you just treat them as a black box and perform optimization just like the optimal control? Thank you.
Okay. So, but the first one, what do you mean? How do you perform the calibration? I mean, could be a long answer or a short one. It depends on what do you want to know exactly. I mean,
okay,
if you want, I can.
Okay, I can. Okay, you can explain some details if you wish. Okay.
I mean, what we usually do is, as I already said, just writing the run cards and run it sequentially. And we have protocols that we are using. If we really don't know the properties of the chips, we start with the resonator spectroscopy at high power, low power. So we have the punch-out, qubit spectroscopy, Rabi, Ramsey, and so on. So I don't know if it's enough. And about the noise, I mean, we have specific routines that are measuring the specific source of noises, like leakage and crosstalks. For the moment, we
yeah, that was from the microphone in the room. Okay, so Nekun, you can do the slide camera again.
And
so,
I mean, we have specific routines that are trying to measure these sort of noises. And for the moment, I mean, the optimization.
There are no talks going on right now. This is a break time.
In specific routines. For example, I don't know,
So,
the OLT
is it fine?
RAM saying that are taking just a particular property and
Okay,
optimize
perfect.
it, but we don't have
All right. So, okay.
Oh,
So
you just mentioned Arctic.
you can just
I have a question about related work. So when I think of qubit labs
leave your Discord
inevitably either use
in this
LabRAM or
channel,
Arctic for
then
the kind of things you're doing. What's your main selling point compared to those?
like a 10-minute
we are not
for a
selling
presentation.
anything.
Can
We're
well
I
get your
mean, for the
how
moment,
the
this is
sound.
just a small project.
Okay.
We're
So
still
is it fine
developing it,
if I
so
turn
we
off my
are
computer
not
now and
Yes.
maybe move forward?
Yeah, you can turn off your screen share and your
also
camera.
the number of chips that we are calibrating.
We'll let you know when the time to present and the
It's
low
on the
spec.
order of 5 or 10, so it's completely different from the others of Google.
If I
No, I'm not talking
computer,
about Google. I'm talking about university
Oh,
partners.
I
Visited, I think,
or you'd rather me to
okay.
stay here?
7 of the qubit labs in
Uh,
the University of California. So they're very
yeah,
much in the boat.
it's
They have a rooms that look exactly
it's
like the picture that you showed
not
at first,
too
except they
difficult
use
for
different
you.
qubit
Then
technologies. The point is, for the
yes, we
middleware that
prefer
you have,
to you to
use
leave your
Arctic, for example,
camera
as
so
a
you
very
can
compared.
stay
So
in
what I'd like to
this
know is,
voice.
what is the advantage that
Okay.
they would get by
Okay,
switching
sure.
to your stuff
Yeah,
instead of
yeah.
using
Thank you.
Arctic?
Thanks. Thanks.
I mean,
Bye
I
bye.
don't know the.
Yeah.
I mean, I don't know really
So
how to answer
I'll
this
be back
question.
in like
So I have to. Yeah. Okay.
so I'll be back in
So
right?
Arctic was
Yeah, you can come
initially
back in an
developed
hour.
for ion technology, and I see these examples with superconducting qubits. So that's the
Do
difference. Also,
disconnect
Arctic
or
provides
just to stay here?
the actual hardware,
You
whereas I
can mute.
believe
Yeah,
Kibo
you
is
can
just
mute
software,
your
or if we want to call
microphone.
it middleware.
Yep, that's right.
And
Okay.
and some of these projects
You're good.
also
Okay, see
in
ya.
California is like Cubic and Kik. These are also integrated with Kibo. So there's this Kibo SOC integration that integrates the Kibo.
Yes.
Kibo SOC integrates Kibo high level with a Kik FPGA based control hardware. So I would say at some point they will be integrated or integrable at least.
Okay. Good.
I just visited the lab in Bicocca where they told me
Yeah, indeed.
what's going on. One of the part of the ecosystem.
Yes.
One more questions? Yeah. No? Maybe. Okay. Well, thank you very much again.
Thank you very much.
So we will go to lunch break now, and we will be back at 1:40 p.m. Okay, enjoy.
we start?
Here, yeah, sure. I'll introduce you quickly. So our keynote speaker for this
Thank you very
session
much.
on verification is going to be Nankun Yu of Stony Brook University, and he'll be talking about quantum programming, program verification, and testing. So take it away, Nankun.
Thank you very much. I really appreciate the organizers, Alexandra and Mingshen, for inviting us and inviting me. So I feel very sorry I cannot come in person because of my visa issue. So let's get started. So my talk will be quantum program verification and testing. Okay, I will mainly focus on program logic, and it's just focusing more on quantum Hall logic. So back to 1947, so like John von Neumann initialized the question of classical program analysis, and before that, of course, he's a pioneer of quantum mechanics. So he asked the question of how to test large programs, and then in 1967, so Hall proposed the Hall logic and introduced the Hall triple PS2. And sure, the quantum computing become hot, and people start to think about like quantum program verification, and there are a lot of works. So notably, from my point of view, so we will start from Mingshen's quantum Hall logic, and then there are quantum applied Hall logic, which is a simplified version of Mingshen's quantum Hall logic, and also we have like quantum relational Hall logic, quantum separation logic, and incorrect logic. So let's first review classical Hall logic. So the motivation is that for program verification, it's easy to make errors when coding, and when the program is large, the problem becomes very complicated, and also the failures of programs are very dangerous. So program verification is a task of to prove the correctness of properties of programs. There are lots of approaches. Right? So the deductive proof system, the model checking, type system, abstract interpretation. So a simple classical language is based on like basic expression, Boolean expression, and classical programs. So classical programs consist of like assignment, consequence, and branching, and the while loop. So operational semantics is as this. So we have assertion of predicates as a set of states, and we have Boolean satisfaction, and we write it as sigma satisfy p, so sigma p. So the basic expression, we can understand that if it's an expression, so and also the sequence is first S1, S2 sigma, first apply S1 and execute S1, and then try to execute S2. And the case is when the system, the current state satisfies the Boolean variable B, then we go to the first branch C1, otherwise we go to the second branch C2. And the while loop is that whenever the Boolean, the loop guard is satisfied, we go to the loop body. And if it's not, then we jump over the loop. So the validity of the Hall triple is consists of two definitions. First is called partial correctness, which is defined as partial PCQ. So C is the program. So it holds if for any sigma, the current state in input state sigma satisfy P, then after the execution, the output will satisfy Q, or the program will abort. And total correctness is denoted by total PCQ. So it holds if for any sigma, if sigma satisfies P, then output will satisfy Q. So it guarantees, the difference is it guarantees the termination. So our goal, or the goal of Hall triple, is to check the validity for any given Hall triple PQ. So this was done by deductive reference rules rather than semantics. So this is the very famous inference rules. We have like axiom, sequence, consequence, case, and loop. So the Hall logic is very powerful because it's sound and complete. For sound, we mean that for any derivable triple is valid. And the completeness is that
any valid triple is divisible. So this motivates us to consider what is Hall logic for quantum programs, how to understand quantum program states and assertions, how to define syntax, semantics, how to explain the validity of quantum Hall triple, and how to design a sound and complete proof system. So this part will review the mission's paper, Floyd Hall logic for quantum programs. So different from classical quantum states considering qubits rather than bits, and the initialization or the assignment is not assigned a variable to a value, but assigned to a quantum state. And operation of quantum states is no longer plus, minus, multiplication, and this arithmetic operations, but instead it become like unitary and quantum measurement. So in Minshen's quantum Hall logic, the quantum assertion is given as a operator, unobservable, where all eigenvalues lies in the interval 0 and 1. So the satisfaction is denoted as trace M row, denoted the degree of to which the state row satisfy M. So it's continuous, it's not Boolean. So different. So for you can see the table. So deterministically, the state is X, the predicate is P, and satisfaction is S, satisfaction. For probabilistic, our state is a distribution, and our predicate is a measurable functions, and the expected value is the integration. And for quantum, we focus on density matrices as states, and our predicates as observables, and satisfaction we consider as quantum expectation value. We can also consider the syntax of quantum programs or quantum while programs. So we have like initialization. We initial the quantum register Q into 0, and we apply U on this quantum register and perform measurement. And a slightly different part is the if. So if in classical is that for any given state, you only have like it satisfy B or not satisfy B. Right? It's Boolean, and also as well as Y. But for quantum, we actually in imaginary we apply a measurement M, and measurement not return a distribution, but return a Boolean value which a base distribution defined by quantum mechanics. So does the Y. Then based on the outcome, we become that is a Boolean or integer or classical value. We go to different branches or loop body. So the operational semantics is as this. So the basic expression, if we initialize Q into 0 and row, then we initialize the register of Q into 0, but leave the rest registers in row untouched. We apply unitary, so we apply U row U star. This is because of the positivity of quantum mechanics. So if we only care about pure state, then we only need to apply U state. We don't need to consider that. And the case is also similar. Expect after the measurement they will collapse. We also have the loop version. So just remember, at any time if we perform a measurement, then the measurement will collapse the state into different states. And the denotational semantics is like for any program S and any state row. So the execution of S on row returns out the value as the summation of the multiset of all possible outcomes. This is a well-defined semantics because trace row is smaller than 1, then all the output, the trace of S row is always no bigger than 1. Okay, let's take a very simple example. So well-known quantum teleportation circuits. So what do we mean by teleportation? So suppose we have a Q0 state. Let's say is from New York, and we want to send the state to someone in Copenhagen, and the communication is very noisy. So what we do, the teleportation is that if Copenhagen and New York shares the maximum entangled state, let's denote as beta 00, then from my side, I can perform a measurement and just send classical information to Copenhagen to recover the state. So program is like this. And so S1 is like we apply Q0, Q1 in the C0, and then S2 is like we apply Q1 an H gate and we perform measurement. Okay, so operational semantics, when this psi is 0, so the execution we get that the other state Q2 at Copenhagen becomes 0. And if the state Q0 is 1, so after the execution, the state in Q2 is also will also become 1. So the validity of quantum Hall triple we defined Ming-Shen defined as follows. So the first correctness is P row less than trace Q S row. So comparing with the classical horology formula, so if the input satisfies P, the output S satisfies Q. Okay. And for partial correctness, we denoted as also denoted as partial PSQ. So which is holds if for any row trace P row more than trace QS row plus trace row minus trace S row. So you can see the last part, the trace row minus trace S row, is just to denote the probability of non-terminating row. And we can so Ming-Shen develops the quantum Hall proof system. So which we have like initialization and we have unitary operation. And also the sequence rule, the consequence rule. And here we use Loeffner order operators because we are semi-definite Hermitian matrix with positive eigenvalue. We call P prime smaller than P if P minus P prime is positive. So this is a case rule. It's very similar to classical, but slightly different in the sense that we have to take into account that after for the case rule and the while rule, we have to perform measurement for program branching. But when we perform measurements, they will collapse. So here we have like the precondition of the right hand side. You can see it will be normalization M over M dagger PM M. So this denotes as after the measurement. And the loop rule is more complicated. So you can see classical loop rule is B and P on C1 after C1 satisfy Q, and negation of B and P after C2 satisfy Q. Then we have P while Q. But for the quantum loop rule, we have to change a lot of things. In the sense, first is like a probabilistic combination, and also we have like a class collapse of state after measurement. So the condition will become like a P M0 star Q M0 plus M1 star P M1 after the while loop will satisfy Q. And this is for partial correctness. If we want to total correctness, Ming-Shen introduced the bound function. Okay, so the proof system is perfect in the sense that it's sound and complete. But observable are kind of counterintuitive. And actually for classical mind of our classical mind of program analysis. So we familiar much more with the Boolean variables or God or K as Boolean function. So then we talk about like projective quantum predictors. in the sense that this is easier. And also we observe that the general measurement and the projective measurements have the same expressive as long as we introduce ancillary system. And also for application purpose, most existing quantum algorithms are related to pure space. So for projections, the satisfaction is a Boolean function, and we can define projection-based assertion, and which has simplified proof rules. Okay, so we know that for any quantum program or quantum one program, the termination space, which means that considering every projection corresponds to a space. So this is very natural. And we have some rules for projection, and we have the logical operations. Very simple classical Boolean variables. The only thing that we as the span of P and Q for two subspace, two projections P and Q. And this also very similar, and the total correctness very similar as the logic. And further, we have the relation with quantum. So here we denote as A. A means that is applied quantum Hall logic. So we have the lifting. So if for program, so if applied quantum Hall triple is valid, then the corresponding quantum Hall triple is valid, and vice versa, as long as P and Q are projections. And we also have the reduction. So this is comparably, we have a much simplified rules, because you can see here from the left-hand side, we come from summation of dagger PM. We went to like the Boolean operators, the measure and the projections. Okay. And we can also use the bound function. So for this applied quantum Hall logic, we also have like sound and completeness rule. So we can use this to verify HHL. There are many follow-up and corresponding works of quantum logics. So you can use the incomplete of the first part, the follow-up work of quantum Hall logic, and first several are not. So these are the references we have now. So then I want to talk about the quantum incorrectness logic, because the verification purpose is to notify errors. Right? So this was based on the incorrectness logic and my work on quantum. So what is this in quantum programs? So there are lots of examples, and to make the absence of bugs in quantum programs, there are lots of efforts. So how to find bugs if there is one, or they are there already? So let's consider for classically Peter O'Haron introduced the classical incorrectness. And in my Opsla 20 paper, we have a dynamic assertions. I'll talk later. And in Huang and Martinozzi, for statistic assertions. And Chen has a tree. So we want to introduce bug finding ahead of runtime. So the first is classical, but for the second, it does not is a testing. And for statistic version, 19 paper, it's not we did not find a soundness or uncompleteness argument. And for the automata, we don't have a proof system. So for my expertise, we want to extend Peter O'Haron's paper from classical incorrectness to quantum incorrectness. So let's first recall the classical incorrectness logic. Otherwise, you have approximation and and the incrementalist logic is the approximation. So in some sense, they satisfy a duality relations. So for so the logic is defined as PSQ. So every state is in Q is reachable from some states in P. And so we have to define a quantum program correctness. We have to extend we have to extend In's quantum Hall logic to add errors and assert statement. So for simplicity, we consider assert as a projection. So for instance, if rho satisfies P, then we assert Q, P will pass a certainty without collapsing rho. And if rho is not in P, so assert Q, P will turn rho into P rho Q or abort abnormally. Okay. So we add one semantic error rho, error, then we will abort. Okay. So whenever we find an error, so we abort. So we can define similarly as a denotational semantics. And we have this similar. So if rho C is 0, rho E is 1, and rho is 0, 0 plus 1, 1, so we know that rho C satisfies PC. But no predicate QE such that rho satisfies QE without bringing false positive. So the solution is we provide an under approximation relation. So we say like this. So if rho bigger than P in the sense that the support of rho contains P. So we have further examples to say we assert Q is 1. It has most has two output, like 0, 0, 1, 1 in a sense. So the state under approximation by Q is like all rho such that rho can be written as P0, 0 plus 1 minus P1, 1 for any P is greater than 0. So we can also provide a solution as a mixture of reachable states. In the sense that if it achieves P, the mixture of states S achieves Q. Okay? And achieve Q means that it's possible to enter the false range. So we can put the solution 1, 2 together. We define the assertion as a Boolean assertion. And with no false positive and with quantum reachability. And the validity is that for any program, the correctness form of PS Q holds if for any rho that P summation, so the output of S rho Q for if is okay or error. Okay, so here this output is just the semantics. Okay, we can find the duality between this formula and the applied quantum Hall logic, and we introduce the proof rules. And this is a branching structure, and this is a assertion. So OK is support RP R dagger, and Q error is support R perp, meaning that also complement of R P R perp dagger. Okay, so then we denote that the P assert Q bar R is OK Q OK or Q error, in the sense that because we imaginary apply the when we do the assertion we apply the measurement. So if we return OK, the state will collapse to Q OK. If we return to error, the state will collapse to Q error. So we prove boundness and completeness. And also we can bound the iterations of the loops for completeness. And this is an application to of our logic. Okay? We still do it for application. Okay, these are further reasons for quantum bugs. Okay. In this part, I will talk about quantum relational Hall logic. This is based on the work in POP20 and CAVE24. So relational Hall logic is introduced to verify the relational property. So suppose two programs C1 and C2. So input C1 is sigma 1, input of C2 is sigma 2, which the jointly they satisfy property, let's say phi. Then we want to say that the output will satisfy psi. So we have applications in crypto proofs and differential privacy and expected sensitivity. So probabilistically, we have to work on probabilistic coupling, and we can also have probabilistic lifting. And the correctness of the relational Hall logic is that if for all sigma 1 and sigma 2, sigma 1 phi sigma 2, meaning that the input jointly phi sigma 1 sigma 2 satisfy phi, then the output will be able to lift to satisfy psi. Okay. So to define quantum coupling, so we move from probabilistic distributions to density matrix, and the binary to Hermitian trace, marginal distribution to partial trace. Okay, so partial trace is very common in quantum mechanics. So we give two density states, rho 1 and rho 2, so we can define a coupling of rho 1 and rho 2 on the joint space is like if trace 1 rho equals rho 2 and trace 2 rho equals rho 1. And we can define things, so if rho 1 rho is density matrix and rho over H1 tensor H witness of the lifting. And the correspond to a subspace is like support rho lies in the subspace X. Okay. So we can have like identity relation, symmetric subspace. This is a slightly different classical because identity is like just the A. The equivalent is the can use it to talk about U1 equals U2 or ρ1 equals ρ2. Okay. So the validity for projective predicates we can define this way. So ρ1 A star ρ2 can introduce us to S1 ρ1 S2 ρ2 and to B. And we can also have like for Hermitian predicts. Okay. So this is the extension of quantum Hall logic rule to relational rule. And we also need to have the measurement to synchronize the execution. Skip this part. And we do use the circuit for quantum prediction to see, yeah, it's correct. And then we introduce the approximate quantum coupling. So for two given density states, ρ1 and ρ2, so we say ρ is a delta coupling. So if the difference between the partial trace and ρ of ρ and ρ1, ρ2 are very small. We can also define the approximate lifting. And there's an approximate equivalent saying that if ρ1 and ρ2 are approximately equal with parameter delta, then the distance between sigma ρ1 and ρ2 is smaller than 2 delta. And we can define the validity for approximate quantum relational Hall logic judgment. So ρ1 A star ρ2. So we insist that the input will be perfect, right? And the output is like can have like a delta difference. And we also need to introduce approximate measurement conditions. So we have some modified simple rules. You can see we take the example of the first one. So if S1 and S2 one relation from A to R, S1 prime 2 are relative with R to B. So S1 composite with S1 prime is delta 1 plus delta 2 S1 relation S2 S prime. So this is the multi-dimension rules. So we use approximate quantum relation Hall logic to reason about approximate quantum Fourier transform. So these are further readings of the quantum Hall logic. So now I come to the last part. It's called quantum quantum program test. So mostly from my work on Uppsala 20 and this ASM paper. Very short. Okay. So we talked about verification. So verification was for understand the program is correct without executing in a real quantum computer, because the quantum computer is very noisy. So, but usually verification can maybe provide a trade-off. So if we want to run applied quantum Hall logic or even mean quantum Hall logic, we need relatively large computational power in classical computer. So although verification is able to guarantee the correctness, it's very expensive. Testing is cheaper in the sense that it can remove many assumption errors, although not guarantee correctness. So in particular, current quantum machine, so it's very noisy. So and would be encounter lots of errors. So testing will be able to help us to recover lots of errors. While verification will always generally give you like it's not correct. So as we discussed, so we talk about times and times. So you can see here we use projections to test quantum state. So first, it has strong expressive power. In that we are not saying that this state exists. Or yeah, I can see it. We want to add some level of information, and introduce efficient checking, because the predicates satisfactory can be checked with not of many executions. So you can see this diagram. So you can see here. Suppose your state is at rho, and your correct subspace is at P. And if we perform a measurement, in the sense that testing, we run it on a quantum machine. So in case we obtain result P, that is in the correct subspace, right? And the state collapse to 0. Okay. And also, there's a possibility it will collapse to a wrong subspace, also subspace of P, and the state will collapse to P per rho P per, as our incorrect logic denoted. So what's the good news is that if your state is very far from lies in the subspace P, my measurement will, with very high probability, get you to make a mistake. Otherwise, you will go to the correct subspace. So what's the good of this? So after my execution of this command, let's say like a while loop or a branching statement, whatever the current state is, as long as it collapses to the correct state, in the sense I did not find any error, and in the next round I find an error, I can guarantee that the next round of program must test me, because you can see, as long as I pass the current test, my state already satisfies the things I want. So it will help to locate the error. Of course, so for testing, many executions without seeing errors does not mean correctness. It's just that we just not to observe. It's just to say that this, let's say we see the sun is rising today does not mean that it will rise tomorrow, because but we're able to claim it with it will rise tomorrow with some high confidence, right? So in the sense that we have to deal with quantum program testing, we have to deal with statistics, just like quantum mechanics. So these are the further result. For me, there are many interesting papers of quantum program analysis recently, and yeah, I list a very incomplete list. And thank you. So I'm happy to answer any question and see your comments.
Thank you, Nankun. You forget that we're in Copenhagen in the summer, so the sun doesn't seem to rise inside at all. We started a bit late, so we have a few minutes for questions. I'm going to take the first one.
Sure.
On an early slide, you referenced you don't have to go back to it, but the quantum predicates that Ming-Cheng Ying used in his first quantum horologic paper are based on what are called are based on expectations, right? And that was based on a work by Elie de Haan and Godin that argued that those are really the right way to think about quantum predicates as these Hermitian operators that correspond to the to expectations, in the same way that Dexter-Kozin argued something like 30 years earlier in the early 1980s that you needed expectations to reason about probabilistic programs. So, and he seems to have been borne out right in the probabilistic domain. So I just wanted to ask, kind of like, there seems to be there are a bunch of papers going back and forth on that, and from my perspective, it seems like, you know, Shor's algorithm, Grover's algorithm, a lot of these are probabilistic, and I'm kind of inclined to believe that Ming-Cheng was right to begin with. So can you say a little bit about the practicality of the two different approaches in the quantum setting?
So it's the difference between those and projections, right?
Yes.
Yeah. So exactly. So observables. Oh, sorry. Let me go back to that. So observables enable us to understand the acceptance probability of the of an algorithm, and the projections advantage is easier. So yeah. So you're absolutely right in the sense that yes, observables enable us to track groove search and also track Shor's algorithm. But if you can see, if you I read Ming-Cheng's paper many times and find that for simpler use, theoretically, of course, observable is fantastic. But for application use, Ming-Cheng's example was Grover search with which will terminate with certainty. So simplification will help to for further applications. I mean, programming. So on the other hand, although like Shor's algorithm is probabilistic, but some part of it is actually deterministic. For instance, quantum Fourier transform, you can actually reason with projections because it's totally unitary. And you can even simplify your reasoning by considering the structure of quantum Fourier transform. So I'm not saying that projection can replace observables, but it can simplify lots of steps in the middle. So possibly at some point we want to reason about some quantum program at some place, or multiple places, I'm just using projections, which is strong enough for me to get enough important information. And then at some point, I leave it, relaxing it to observable to be reason about the general acceptance probability. This is one thing. The second thing is that, sure, we want to reason about probability, but general quantum programs or general quantum algorithm, we don't intend to understand a probability distribution of the output. We only want to get the right result. In the sense that we only require that the output will satisfy some property with high probability. This provides some relaxation of using projections. So if we use a projection, and we can introduce a noisy parameter, just like the approximate quantum relational horologic I did. So as long as I can reason that, yeah, I don't know the algorithm, I'm not sure whether the algorithm will accept with probably, let's say, 99%. But I know that the acceptance probability is greater than, let's say, 98%. So I can bound the error probability to like 2%, and that's enough for me generally. I hope that.
Yeah, thanks for the very clear answer. So one more question from Jensen.
Hello. I wonder where you are with the mechanization of these logics. I mean, one of the reasons for the success of horologic is that we now have the tools for mechanizing it, the classical one, I say. So where are you with mechanizing the proofs?
I suppose you're talking about tools, right, for implementing the horologics, right?
That was a yes.
Hello? Oh, the mission has a paper in Cape, I think 2 years ago, which support implemented the tools for the quantum logic. So there is so it's automated.
Thank you. All right. So our next speaker.
Thank you very much. Let me share.
The next speaker is it Nicola? Who's speaking? Okay. So our next speaker is Nicola, talking about aesthetic analysis for high-level quantum programming languages. So feel free to take it away.
Hi to everyone, I'm Nicola Solini and I come from University of Verona, and in this talk I will talk about static analysis for high-level quantum programming languages with a focus on dealing temporary variables. So working with quantum computing is something great, I think that we all agree, but when we put together the program languages with quantum computing, we introduce some new challenges due to the feature of quantum computation. We say that in general, we can say that these challenges are related to the no-cloning theorem and the implicit measurement principle with the entanglement. The first one implies that we cannot copy a variable in general, and the second one forces us to pay attention when we want to discard a variable. In fact, if we don't do it in the proper way, we cause some implicit measurement that can lead to side effects due to the entanglement. So the POP solution to these two problems are using linear types. In fact, if we use a linear types, we need to use a variable exactly once. So basically, we use variable at most once, so we cannot introduce implicit copy, and we must use all variable. This means that when we discard a variable, we must do it explicitly. So since we explicitly discard variable, we basically are sure that every time we discard a variable, we say to the compiler, make the computation of this variable, of these resources. And in particular, in this talk, we focus on this feature of these solutions, so the discarding of variable. With the linear types, when we have a program like this one that use some local variable. So in this case, we have the variable a that is defined inside a function, and then it's not returned. You can see that we redefined this variable multiple times, but the last time, at line 5, we define the variable a, but we don't return it. This means that this program introduces an implicit discarding of this variable. So in fact, if we treat the type qubit linearly, the type checker will return an error like this. And if we want to make this program well typed, we need to explicitly discard the variable. So we will add a function, a discard function, depending which program we are using, which language we are using. So in this case, we have used all variable, also the last definition of a it used. And in this version of the program, we are sure that this variable will be properly handled by the compiler, since we have discarded it. You see that when we use linear types, the duty of insert discarding in the language, in the program, is left to the programmer. In fact, the programmer must explicitly discard all the variable or temporary variable in a program. And this can make the use of the quantum program languages harder, because it's something that the programmer must care about. So we want to define a more easy approach to this problem. And in particular, we define a static analysis that collects all the information about variable used, and then we can use this information to take a program that uses variable at most once, so a program that respects a more weak constraint, respects the constraint of linear types, and then we can transform it in a program that is variable exactly once. How we do that? We do that adding the discard function where it is needed. So in this case, returning to previous example, with our approach, instead of returning an error like this, we do not return an error. Instead, we analyze the program, and we automatically add the discard function. Okay, we can see our approach on a more complex example. This is a program in which there are 3 implicit discarding. In particular, this is the variable r, that is a parameter of the function, and it is used only in the if branch. So when the computation goes to the other branch, we do not use this variable, and when we arrive to the return, there is an implicit discarding. Similarly, there is the same with z, that is used only in this branch and not in the other branch. And finally, there is the variable c, that is redefined at line 9, but is not used. So a type checker will return an error on these 3 variables. Instead, with our approach, we analyze this program. In particular, first we build a control flow graph, then we perform the analysis, and finally we use information from the analysis to insert the discard. So first we build a control flow graph. We see that we represent the program with a graph. A control flow graph is basically a graph in which each node corresponds to a program point. The edge indicates the flow of the computation that go from a program point to the other, and on the edge we put the label that correspond to the statement that are executed when we go from a point to another. You see that we add 2 special labels. In particular, this label indicates which variable are passed are parameters, and these 2 labels are used to indicate which is the true branch and the false branch when there is a branch. And we ignore the classical variable, since the discard only it is need only with quantum variables, so we can just ignore the classical part of a program. So after we have defined the control flow graph, we need to perform an analysis. In particular, our analysis starts from classical live analysis. So we first recall the concept of liveness. When we have a program that could be modeled by a control flow graph, we say that a variable x, it is live in the node u if it has been defined before in the program, and it will be used. So in this case, the variable x is live from this node, I mean just after the edge, until this node. So in this part. And in particular, we define 2 types of liveness because we need a more accurate information. We define the safe liveness, so we say that a variable is safe live in a node if it will be used in all paths from that node. So in this case, the variable exit used in both paths, so it is safe life in U, and we define another type that is unsafe liveness, that is when a variable is used only in one path. I mean, it's not used in all paths. So in this case, it is used only in one path and not in the other, so the variable is unsafe live here. Of course, this variable is safe live in this path, because there is no branching. So so to compute our analysis, we need to determine for each node which variable are safe live and which variable are unsafe live. To do that, we define a pair of set, the set S that refer to safe live variable, the set U that refer to unsafe live variable, and we compute this pair of set for each node of the control flow graph. So as the liveness analysis, our analysis backward, so we need to start from the exit node and go backward in the sense of computation. So we start from the exit node, we initialize the pair of set to empty, since there is no live variable at the end of the program. And then we compute all the other pair in the other node. So first, in node 6, we add the U to S because return U use the variable U. Similarly, in node 5, we add the variable C because here we are using variable C. In node 3, we remove C because C is defined, so it's no more live, so it's no more safe. And we add variable R because it's used by HR, I add R. Similarly, we do the same in node 4. And then we arrive to node 2 where there is a join. And in particular, here is when the other set is used. In fact, you see that the variable U is safe in node 4 and in node 3. So it's used in both paths. So in this case, we can put the variable U in S also in node 2, because since it is safe in both nodes, it will be safe also in the join. Instead, you see that the variable R, it is safe only in node 3, but not in node 4. This means that it's used only in this path. So we move R from S to U, and we do the same with Z, because it's not safe here. So basically, when we have a join, we make an intersection between the two S nodes, a union between the U, because in this case are void, and then the part of S that are outside the intersection, we move the variable, the extra variable, we can say, from S to U. And then we can go on the analysis. In node 1, we remove U because it's defined, and we do the same in the start node. Now that we have all the information about the variable use, we need to add the discard. In particular, we need to discard two types of variables. The variables that are never used, so the variables that are never live, and the variables that are partially used, so the variables that are in U. We start with the first case. To find a variable that is not live, so not used, we need to check all the definition in the code and look if the variable that has just been defined, it is live just after the definition. In this case, you see that here we define Z and R, and they are live, so it's okay. U is live after the definition, so it will be used. The same with the first and second definition of C, but the last definition of C defines C, but C is not live just after the definition. This means that this C is not will be used. And in this case, we can add the discard just after the definition. Then there is the other case that is more complicated, when a variable is in U. In particular, in this case, there are R and Z that are in some U. We start from R. When a variable is in U, this means that there is some path that do not use that. And this is the reason for which, the reason that caused that the variable end in the U. So we need to find that not using path, basically. How we do that? We look for each node U, the successor of that node. You see that, for example, in node 1, the variable is in U, but it is live in the successor, so it's okay. Instead, in node 2, the variable R is in U, and if you look to the successor, in one successor, the variable R, it is live. So this means that this path will use R, so we cannot insert the discard. But there is another path that do not use R. In fact, in this node, the variable is not alive. So this means that the path that cause the unsafeness, so the path that do not use R, is this path. So in this case, we add the discard at the beginning of that path. And then we do the same with Z. In fact, it's unsafe here and unsafe here. After node 1, it always used. After node 2, it used only in node 4, so we discard in the other part. So we are starting from this code, and without that requires some discard function because there are some implicit discarding, and without recurring to program, without programmer intervention, we add all all the discards that are needed. So basically, with our approach, we can relax the type system of a quantum program language, so in general, a language that need linear types, and automatically handle the part of discarding variable, so we can make the use of quantum languages, so in general language, more easier, since the constraints that are required, the constraints that the programmer must follow are more easier. And we can conclude. In conclusion, we implemented this analysis for Guppy language, a new language that Quantinuum are developing. And in fact, all the examples that you have seen before are a fragment of a simplified version of Guppy code. And we test also this analysis in some simple code. And as a future work, we aim to give a more, to integrate this analysis in the Guppy compiler, maybe with the help of Quantinuum if they want. And moreover, we think that we can improve this analysis. In fact, it's not always the computation, so we can say a safe discard is not always needed. For example, if a quantum variable is always a classical value, or it is not entangled with other variables, we can simply drop it without an intervention. So we think that we want to improve our pipeline by adding other analysis, for example, entanglement analysis, to understand the group of entangled variable, and also other classical analysis like constant propagation or an interval analysis, maybe to understand to better model the control flow. So for example, if there is a for loop and we can understand that the for loop will be always be executed, we can then do a better representation of the control flow, so gain a more precision with our analysis. And yeah, that's all.
Thanks, Nicola. We have time for a few questions. Jens?
You mentioned entanglement here right at the end. Yes. Is it actually safe to discard a variable that's entangled with another variable?
I mean, it's not safe to discard a variable that is entangled with other variable. It's safe to discard a variable that is not entangled with other variable, because the fact of discarding is that if I discard a variable, it means that I cause an immeasurement, so I can cause some side effect. But if I measure some variable that is not entangled with other variable, it will be not.
Does your analysis handle?
No, now my analysis does not handle the entanglement part. We just find for temporary variable, basically. So we find that for variable that are like in this example, we discard all the variable that are not that in the computation are not used from a point. So for example, in this case, the variable R and Z are not fully used, so we discard them. But we can improve this pipeline adding an entanglement analysis. So for example, if R it is not entangled with other variable, this discard is
But isn't it true that you may, in this example here, if the variables are entangled, you may be discarding too early in your example here? An entanglement would mean that you should wait and discard later.
I mean, okay, it's depend. It's depend of not. It's depend in this case. No, I mean, not always. I mean, there are some cases in which we cannot uncompute a variable due to entanglement, but I mean, this is not the problem, because in theory, we simply say discard. Like, in Guppy, you write a program like this. the fact that this variable is uncomputing now or uncomputing after is something that will handle the copy compiler. We are just saying discard. But in the entanglement analysis is something that work more with the compiler. So we can say this variable is used, make this uncomputation is useless because there is no side effect, for example. Or make this uncomputation is danger. So you have to wait,
Thank you for the talk, first of all. Also, maybe to add a comment to your question, I mean, there's this automation called Uncom. We already discussed this earlier. And within Uncom, this disentangling would be possible. I think in this particular case, it would not be possible because your particular program has a feature that is, it's not queue-free. In Uncom, there's this property called queue-free, and it's caused by the H gate on the Z, and then C.
Okay. Yes. In this case, the variable C. Okay, yes, not queue-free. Yes.
Yes. So I mean, it would probably still be possible to disentangle it by reversing the last C0 gate, like flipping the inputs. That would probably disentangle it, but it wouldn't be possible to perform this in an automated manner. You need to know as a programmer that it is this kind of structure. But yeah, I mean, this was actually my question: is there also some kind of disentangling automation behind it? So I think you already answered it.
Yeah. Okay. Yes, because we are considered the different side of the problem. So we are just saying discard. What the discard do is something that is related of the program that we are analyzing. So for example, this is guppy. I mean, you just add the type of the function, and this is a guppy code. And in guppy, you just say discard. So in the guppy compiler that I think that actually does not completely exist yet, in theory, we should handle the fact, like in this case, or maybe, I don't know, it will be do something about the not possibility of computing, for example, or the not free fact.
All right, let's thank Nicola. And next up, Qifan Wang will present efficient formal verification of quantum error correcting programs.
Wait for a while. Okay, I'm sorry. My computer is a little bit slow, so I have to. That's done. But where is it? I didn't find the corresponding buttons. What happens? Okay, I find it. But okay, but the computer is not so. Oh shit. Oh, I got stuck with my computer because I want to find the screen sharing. Huh? Okay, I directly. Okay, I'll directly. Okay. The red button. The red one's the big one. Yeah, it's the red one. Okay. Do you want this tool here or just? Okay, I want this tool. Oh, okay. So let's.
No, okay, that was not
okay.
a good idea.
Okay, it's not a good idea. So let's begin with the. Okay, how? So, dear audiences, my name is Qifan Huang, and I'm from Institute of Software, Chinese Academy of Sciences. So it's my honor to be here to present our recent work, efficient formal verification of quantum error correcting programs. Okay, it's a joint work with Li Zhou, Wang Fang, and Ming Shen from University of Institute of Software or University of Technology, Sydney. Okay, so So there have been years beyond the Niski era, and for torrent quantum computation has become an indispensable step towards scalable quantum computers. And quantum error correcting codes played a crucial role in suppressing noise and implementing fault-tolerant quantum computation. And there has been experiments on real quantum hardwares that illustrates the implementation of quantum error correcting codes. For example, Google's surface code experiments and QEra's recent progress on their neutral atom quantum computers. Okay, so since those quantum error correction protocols have become increasingly complex, verification tools have become significant for validating those error correction protocols before deploying them in real quantum hardware. So there are several categories of verification techniques for QEC programs, and numerical simulation is one of the most widely studied techniques. It characterizes the programs by calculating the outputs, but suffers from the exponential increase in state space. And symbolic execution is another emerging method. Okay, but today we are going to focus on the program logic, which is another peeling verification technique. It is scalable and can handle a class of instances simultaneously because it can express rich specifications in a mathematical way. So at first glance, okay, we are concerned about the following questions. So what modifications should be applied to series of already existed quantum Hall logic, for example, QY language for QEC programs? And there are two works. There starts the direction of using the Hall-style program logic for error correction programs, and the answer they gave is to exploit the power stabilizers. Okay, the series of Ren's works exploits a Heisenberg representation for quantum operators and use stabilizers as the predicates. And another work done by Anbang Wu studied the syntax and semantics of QEC programs, and they treat stabilizers as first-class objects. And in their recent work, they implemented a automatic verifier, which enables the verification of surface code with distance up to equals 71. Okay, but without any errors injected, just verifying the correctness of logical operations or the error correction procedures. Okay, so previous works targeted verifying the correctness of logical operations or just the QEC procedures. Okay, but with fixed errors and initial conditions. So we think the potential of automation and efficiency can be explored further. So therefore, our work attempts to answer the following question. Given the error models in a QEC program, how to identify and efficiently verify the types of errors, okay, that the QEC program is capable of correcting. Okay, for example, the maximum number of correctable errors. Okay, so let's take a look about our design decisions. Okay, there are mainly two ideas that played a crucial role in our verification framework. First, to improve the efficiency, we incorporate classical variables into our design to describe those classical probabilities, those classical properties of the QEC programs. Okay, and this way we could avoid the enumeration of cases. Further, we provided the interface for SMT solvers to check the satisfiability of those classical logical formulas generated by our method. Second, we adopt the quantum logic to enhance the expressive powers, which interpret atomic propositions as subspaces. And we further employ the Birkhoff-Newman quantum logic to interpret those subspaces formed by the logical connectives. We also use backward reasoning because we wanted to infer and identify the error conditions, even in a case without prior knowledge. And in this case, subspaces are the desired semantics. Okay, here's just a toy example showing the expressive power of quantum logic. We will find that the precondition, let's say that for any quantum state that is stabilized by x1, after the measurement and the correction, the final state will be stabilized by x1, and x1 intersects with z2. Okay. we derive the program and we'll get the derived precondition is A1 or A2, where A1 or A2 is as follows. Okay, to prove that this triple, we require X1 entails A1 or A2. So it depends on the semantics of the A1 or A2. Okay, so we find that using classical logic, we cannot get this proved. But when we use the quantum logic, okay, things are correct. So let's start to take a look about our assertion logic design and the program logic. So we assume arithmetic and Boolean expressions over those classical variables. And further, we introduce the Pauli expressions to describe those the stabilizer variables in our programs. And in this direction, you can see that PR is an elementary Pauli, and with an R indicating its location. And we add phases before the stabilizer P, which is -1 to the B. And further, we lift the Pauli expressions onto the entire Hilbert space like this to make the semantics of those expressions. And the assertion syntax is defined as follows. We use Boolean and Pauli expressions as atomic propositions, and further employ logical connectives. And the semantics of assertion can be interpreted as a map from the set of classical state sigma to the set of subspaces in the Hilbert space we consider. Okay. For atomic propositions, we give the corresponding semantics here. Okay. And further, we use a point-wise extension of Birkhoff-Newman quantum logic to interpret the semantics of logic connectives. For example, neg is interpreted as also complement, and the OR is defined as the closest subspace of the span of the union. Okay, it's a little bit complicated. Okay, previous works we defined a classical quantum state, which is a map from classical states to partial density operators. So also combined with the quantum version, the rho satisfies X for subspace X in the quantum state. We can do a point-wise lifting to the classical quantum state mu and the classical quantum hybrid classical quantum assertion A. Okay, we can also define the relationship of two assertions P and P prime. Okay, then let's come to the program logics. Okay, to describe QEC programs, the program syntax is defined as follows. And there are some syntax sugars specially designed for QEC programs that deserves notice. First, for conditional unitaries, okay, we define such a syntactic sugar to avoid the enumeration of the branches. And also for stabilizer assignment or function calls, we also define corresponding syntax sugars. Okay, so the semantics are straightforward, so I think time is limited. I don't want to talk about here. And okay, the correctness of the PSQ are in the sense of partial correctness. Okay. And we select some important inference rules in our proof system. And there are two things to notice. The first, the comma separated rules in here, in those rules are performed at the same time. Okay, and okay. After talking about assertion logic and program logics, it's time to discuss how our framework can perform the efficient form of verification. The general procedure to prove a Hall triple PSQ in our framework is to first obtain the precondition by deriving the programs and using the inference rules. Okay, so you will see that the P prime is a derived precondition, and the P is what we want. Okay, so the next step is to prove the verification condition P entails P prime by the assertion logic. So thanks to the classical variables introduced, our framework possibly supports broader scenarios. Okay, in this image, you can see that the errors in our case quantum error correction programs, okay, it can happen before or during the error correction procedure, or it could emerge in the logical operations. Okay. Okay. So people may doubt that it is hard to verify the verification condition. Okay, because it is hybrid classical and quantum, and how to separate them is a difficult problem. But things get simpler if all the polys in P and P prime are commute. then all of the logical formulas generated by those stabilizers will degenerate to Boolean algebra. And if there exists non-commuting pairs, then some maybe heuristic proof rules in quantum logic may be required to further reduce those non-commuting pairs. Okay, and this is still open for exploration. Okay, when reading about the QEC program with unstabilizers, typically you obtain the following verification condition. In the left-hand side, PC is the classical condition of the errors. Okay, and the right-hand side is the derived precondition derived by the programs. Okay, from the post condition. So regarding this this verification condition, if all of the stabilizers commute, then we could generate the following classical conditions PC prime, and so P entails P prime is indeed equivalent with those purely classical logical formulas. Okay, and which can be further verified by introducing SMT solvers. Okay, at last I will introduce a example of the 7-qubit Sydney code. Okay, as to further illustrate the verification of our framework. Okay, the Sydney code is a good candidate for illustration because it is capable of correcting arbitrary single poly errors, and its asymmetry makes the implementation of logical automat C0 and poly gates transversal on these gates. Okay, so we choose to inject Y errors into the codes and perform correction and perform the error correction procedure by first measure syndrome, then call the decoders for Z and X stabilizers respectively, and finally perform the corrections. Okay, so use our program syntax. The programs we need to verify is defined as follows, and the correctness formula for this program can also be generated. Okay. Okay, so note here, we directly add a Boolean expression B on the logical operator bar Z, so that we can verify the logical 0 and 1 state at the same time. So that improves the efficiency. Okay, so assume a poly error, the VC will be generated like this. Okay, it is a little bit complicated, so I want to explain the details. But here we notice that the stabilizers bar Z from bar Z to G1 to G6, it doesn't change. It don't change. Okay, so the verification condition according to things beforehand. Okay, it is equal to the classical. It is according to the classical assertions PC entails PC prime. Okay, and the things stabilizers don't change, so PC prime can be generated, extracted naturally. Okay, and PC is the error conditions. So we could, in this case, we could prove the verification condition if the decoder's condition is already given. You can see that the PF is just the minimum weight perfect decoder. Okay, so our framework allows to consider some broader scenarios. For example, if PF is already given, so according to PC prime, we could simplify the PC prime and infer or just identify the form of PC, or at least generate some conditions that are equivalent with the PC. Okay, this is the first scenario. Or to design the decoder, given the verification condition PC entails PC prime. Okay, we could design a decoder and find the condition that the decoder must satisfy. Okay. So through this direction, there are still lots of works to do. Okay. First, we are developing tools. We're developing practical tools for automated verification. First, within the framework of CoQ, we are currently implementing the proof system and the program logic in the CoQ, and we are currently working on to try to prove the soundness, to make it a verified program verifier. And we also develop practical tools to annotate the program and to generate VCs automated. So it further providing interface for SMT solvers. So, but on the other hand, the thought experiments could go further. Okay, so for verifying the program with non-poly errors, okay, there is only example in our work to show the expressive power of quantum logic, but systematic methods still remains a challenge. Okay. Okay. And the last one. Okay. I'm surely I'll end. Okay. So and the last one is the verification for non-clifford logic gates and the implementation. Okay. In Rand's work, they already consider the additive predicates and the rules of T gates. Okay. So we are currently considered to use those theories to enlarge the objects that we can verify. Okay, so so to conclude, I think the design and verification framework for QAC programs is still a promising work, and I think I hope that my talk can throw out a miracle catch the whale. So thanks for listening, and I'm free to answer problems.
Thank you. Questions?
Very enjoyable talk. I have a question. You have this -1 to the b a lot of times.
Yes.
I was thinking you would need -I to the b to be able to get the whole Pauli group.
Okay.
How could you? I'm sure you can explain. I just want to get this right. Why is it -1 to the b the right thing to have there?
Okay, because to form a stabilizer group, the -I. The Pauli operator -I couldn't be included, because the stabilizer group cannot contain the states in 0. You know, the state of 0 cannot be contained at any stabilizer groups. So so it is a general concept that the phase I will not appear in any stabilizer groups and its generators. Okay, so that is the case. So we choose to only use -1, not -I. Yeah.
Hello.
Yeah.
I also thank you for this extremely insightful talk, and I would just like to know where, apart from the reference paper, one can find like this framework of yours.
Okay, it is this is still ongoing work. So we are currently working hard on to develop it, and I hope we can put it on the website to maybe put it in an archive in maybe half a year after. Okay, I'm not sure, but currently we haven't put it on the archive yet. Okay, so
interesting. Thank you.
All right. Thanks again.
Okay. Thanks.
Our final talk of the session will be about verifying quantum circuits in GAP, and that's by Scott Wesley.
All right, there we go. All right, cool. It seems to be working now. Perfect. All right, so I guess I'll just start by saying that based on some feedback from the reviewers when I submitted this, following up on that gap's kind of gone to the back burner, so I will mention it a bit, but there's going to be a lot more verification and a lot less on the actual implementation than before. So where this kind of comes from in the first place. So I'm sure most people here are familiar with equivalence checking, but just a motivating example that kind of will lead into what we're seeing later on. You might have like a controlled Z rotation, and you might have a decomposition like this, which is pretty common. That's some syntax with the semantic interpretations, for example, matrices. If you just compute this by expanding these out, you get some matrices that look very different, but if you do some algebraic manipulations, you can go from one to the other. And the problem of equivalence checking is, given the syntactic representation, the circuits representing the same operator. Whoops. So there's a lot of approaches to this and verification in general. I've just tried to group them together to kind of highlight where we are. So you have a lot of like rewriting based techniques that usually look at fragments of like, let's say the ZX calculus, for example, or like specific fragments of circuits. These fragments have decidable efficient procedures to figure out if circuits are equal. There's also some work with automata. Kind of in the middle, you have exact methods. The simplest example would be matrices or more sparse representations, for example, BDDs, binary decision diagrams, path sums, stuff like that. And then on the further side, you have more deductive methods. These can be automated, but they usually require, at the very least, automation. I'd put stuff over there like quantum Hall logic or the kind of work that people like Robert Wren do in Coq. So there's kind of like a trade-off between how much these techniques scale automatically and in terms of automation and the scope of what you can actually verify with them. Automation usually takes away some applicability. And in this talk, we're going to be focusing on this middle circle. Just for concreteness, I'll be looking at the case of matrices, but the techniques I'll be talking about are specific to matrices. You should be able to apply them to other techniques like BDDs, but I haven't actually explored that yet. And the kinds of problems that motivated us and why we started looking at matrices in the first place. So in some prior work, we ended up collecting a huge, I guess you could say like a compendium of circuit decompositions, most of them involving two, I think the biggest one had 8 qubits. There was 65 of them taken from a bunch of different papers, different notations. So there was just some question as to whether or not all of those decompositions, once we finally unified them and instantiated them, were actually correct. And there's also a lot of other examples of these small circuits that usually get overlooked in the verification work. For example, the rewriting rules in the equational theories I mentioned early on. And like I said, on this side, you have small number of qubits. And with these equational theories, you wouldn't want to use like these rewriting tools to verify them because that's kind of cyclic. You're using your rewriting systems to verify your rewriting system. So of course it's going to be correct because the rewriting system says it's correct. Of course you could try to like use a bunch of different ones, but still it would be good to just rely on something a bit more concrete for like the underlying verification methods when you verify them. So that's kind of like my justification for why I'm going back to matrices. But like I said, these techniques can be applied to other domains, like BDDs. And in this verification work, I guess 3 main challenges came up. The first one is if we're looking at things like matrices and we have rotations, you're going to get a lot of interesting matrix entries. And working with those exactly is one problem. In general, you see these decompositions coming up where you're going to like arbitrary sine and cosines. And if you actually want to verify rotation decompositions, you actually have universal instantiation. You want to prove it for all parameters. And I don't think I'll have too much time to talk about this, but there's some interesting things that come up with how you should actually specify ancilla qubits. Because every time you have like these like discards at the end, it's really some kind of an implicit assertion about the state of the qubit, but I don't think I'll have too much time to talk about that at the end. So yeah, the rest of this talk will really focus on these first 2 ones and maybe a bit about ancillas if I have time. So I'll talk about the exact matrix computation first. This is the underlying techniques here aren't too new, but the actual analysis we work through I've never really seen in the literature before. So, and this is kind of where I will talk about gap, but not too much. So when you want to do like matrix components exactly, there's usually 2 ways that's done. On one side, you have what's called algebraic extensions. You may have seen this diagram before. That's one of the papers that really explores this a lot. It was number theoretic characterizations of some gate sets, but the idea here is you can start with the rational numbers, and you can treat like other numbers like the square root of 2 or like pi as either like from a, I guess, an algebraic perspective, like adding extensions to the fields. And those can either be algebraic or transcendental, which I won't talk about transcendental extensions, and I'll explain algebraic a lot more in the next few slides. And on the other side, you have a more axiomatic approach where basically you just treat the real numbers as some axiomatic structure, completeness and all of that are axioms. Since I'm aiming for automation, I'm going to focus more on these algebraic extensions. Why that's automated will become clear in a few slides. So what exactly are algebraic extensions? You could spend an entire course just talking about that, but the idea is you start with some polynomial, you find the root of that polynomial, and you add it to your field. A standard example is if you want to add the square root of 2, that's a root of the polynomial x squared plus 2 equals 0. And once you add that in, if it's algebraic, you can prove that it actually gives you a finite dimensional vector space, so something that's not too bad to work with. The degree of the polynomial is the degree of your vector space. And it's not just a vector space, it's actually an algebra, so it's closed under all of the operations you need to do for matrix manipulations. And one important example are the roots of unity. Those are basically just the algebraic numbers on the unit circle, and they're also the solutions to x to the n minus 1. So those are just like the numbers that are like, well, basically like for example, the first root of unity would be I, because I to the power of 4 is 1. And when you look at like these roots of unity, we call these cyclotomic extensions for reasons I won't go into, but they have some nice properties. One is that they're closed under complex conjugation. Formally, it's an automorphism of that extension, but I'll come back to why that matters later on. I'm just kind of visualizing one example of what conjugation is doing there. These ones are fixed, and you're just kind of like switching these around, so you can do that and stay in your extension. And they're also dense on the unit circle, which we'll see why that matters later on. The simplest way to see that is if you think about like let's say the second roots of unity, like plus or minus 1, then I, and then going on and on, this dividing by 2. You're just kind of like cutting the unit circle into halves and quarters, and eventually you can approximate any point. But there's, I guess, fancier ways you could do it too, but the point is you can definitely do it. And even more importantly is you can do these computations efficiently. I still don't totally understand this work. I'm kind of looking into it more. But basically, there's this idea of a Zambros basis, which is like an efficient way to reason about arbitrary cyclotomic extensions. So it might be kind of hard to read with the lighting, I guess, but this is actually like a printout from GAP. If I want to add a 10th and 7th root of unity, you get this completely unreadable expression, but it's actually found in the smallest way you can decompose those two things. So like I can just pick arbitrary roots of unity and add them together, and all of that's being handled efficiently in the background. So that's why GAP is a nice choice for this kind of stuff. But I guess the takeaway here is you can add these roots of unity in prior work. For example, the Clifford plus T can be viewed as a cyclotomic extension. There's a lot of QDIT work that also shows that kind of stuff. So these kinds of extensions actually describe gauge sets we care about. And if you want more, you can extend other things like the square root of 2, which we won't really talk about here because you don't have all of these nice properties. But if you need more, you can do it. You just won't be able to do what I'm going to talk about in this next section, which is how we actually verify rotations. So I guess a good way to start is just kind of where the state of the art is. So two techniques that have looked at verifying parametrized circuits. One is in the Munich quantum toolkit that's been talked about a bit today. This technique, they start by using ZX reweighting rules, but the system's incomplete. And if the reweighting fails, then they fall back on a probabilistic sampling method. You just have to pick one point. And with probability 0, you'll get the wrong answer. And with another tool called Quartz, they do some symbolic rewriting. They basically look at the matrices with the sines and cosines, try to simplify them. Then they look at each matrix component, expand it out. So under the hood, it really is a matrix-based method. They encode all the equations that have to be satisfied, and then use SMT solving to try to find out if they're actually equal. That, of course, is going to involve nonlinear integer arithmetic. And so I guess given these explanations now, the limitations that we tried to address here with the MQT toolkit, the sampling theorem actually assumes you're just kind of sampling, but like you're actually doing uniform sampling over an interval, which is like hard to actually implement. So in practice, like that theorem is like an idealized case, but the sampling won't actually, you're rounding off somewhere, so it's more like an approximation of the actual theorem. And it would be nice to know what that error actually is. And with Quartz, Since they're just kind of throwing it at an SMT solver, which works great, it would still be nice to know what the theoretical bounds are and to actually say a bit more precisely. In this case, it would be double exponential on a number of parameters, and I don't have the complexity results written here because it's still ongoing work, but you can prove it's actually a bit better than that. So my work turns out to be an instantiation of the Miller-Bakewell framework. I didn't know about this, and it seems to have gone fairly overlooked in the literature. I actually found out about this 2 weeks before this conference right now when I was talking to Alex Kissinger. His student did this work, but the idea is you can take your gates and do a change of variable to get Laurent polynomials. Those are just like regular polynomials, but you can have negative powers. And then you can look at the degrees of those polynomials and try to give like compositional rules to over approximate those. And then if you know the degree of each of the variables, those variables are like your parameters, and that gives you an upper bound on the number of points you have to sample. And if you do like one more than those number of points, and you just check those instantiations, you actually get universal, you prove the universal case. So this is kind of similar to those many techniques that we used in more classical verification, where you compute a cutoff, check those finite cases, and then extend it to the parameterized setting. But the work that in our instantiation, we're looking at the sine and cosine terms, whereas in Miller-Bakewell's work, you're actually looking at like exponential, so you have to do a slightly different transformation, but it actually lets you compute better bounds on what the degrees actually are, it turns out. And we do add one assumption that these sines and cosines can just be rational linear sums of your angles, which is similar to prior work. Basically, a lot of these techniques it becomes way too complex if you can just put arbitrary things in there, and most of the real examples do look like this. In none of the prior work have they really identified examples where it didn't work, so I still want to look into a bit more about the applicability, but work so far does seem to suggest that that's a reasonable thing to do. And like I said, my goal was to find closed form expressions for these bounds. And since I kind of did this without knowing about Miller-Bakewell's work, it's interesting to compare the techniques, and it leads to an interesting result. The prior work was based on like polynomial interpolation. That's figures actually taken from the original paper. And the technique I was developing is based on combinatorial Nahr-Sullinstats. I'm not going to define that, but the simplest case is easy to explain. If you have a polynomial of, let's say, degree phi, then if I pick 4 points, at least one of them won't be a root. So that kind of tells you how many points you need to use to do polynomial checking, or like polynomial equivalence checking. And there's actually, from algebraic program checking, a probabilistic variant of this that you can apply as well, where if you pick a fixed number of points, you can calculate the probability that if you just sample one from that fixed set, that they would be equal or not. So this can actually give you more precise probabilistic bounds on that discrete sampling from the infinite space. And in my last few seconds, this looks like a lot, but it's all stuff that I'm sure everyone here has seen, just spelled out a bit differently. If you pick a point on the unit circle, you can write it like sine or cosine, and using complex conjugation, so you can actually get your sine and cosine from the roots of unity. So basically, picking a root of unity is the same as picking your sine and cosine values, and as I explained earlier, that's dense, so you can, up to some precision, get any angle you want. And if you fix some n, you can compute the nth roots of unity, and you get you can sample from those n points. So that also gives a way to do the sampling. And as I said, compared to the state of the art, there really isn't that finite analysis. I'll just skip over the ancilla stuff, but the idea is you have your initialization of ancillas is kind of like assumptions, and then your termination is like assertions. There's some patterns that make this more reasonable to do. For example, the scoped ancilla pattern, and you can kind of define these properties inductively, and they're not too hard to check, but I don't really have too much time to talk about that, so that brings me to the end of this presentation. So just to recap, this work looked at reasoning about this exactly, proving equivalence with rotations, and also some preliminary work on specifying, I guess you could say, qualitatively good ancillary usage.
All right, thank you. Questions? I'm not sure that this doesn't turn on. So.
Okay. Yeah, I'm one of the quartz authors. The reason why in solving these integer thingies works is because we only do small scale. Are you ready to do experiments? How is that standing?
So I was ready to do experiments. Then I ended up reading the feedback and developing this new stuff here. So I'm just still doing a bit, like the proof also gives me the bounds. I have a good idea what the bounds are, but I haven't quite completed the proof yet. So once that's done, I think I can use the implementation I was doing before and then start doing experiments. So I hope to be doing that probably within the next months.
Other questions? Quick question from me. I know there's a bunch of different algebraic structures that famously Giles and Sullinger, but a bunch of others in various verification papers have used to verify something like Clifford plus T or a subset of quantum computing. If you restrict yourself to these smaller algebraic groups, does that simplify things, and is that a strategy you've used?
So that definitely does simplify things. Where it doesn't work so well is if you, well, I guess once you have these parameterized, like these like cutoff theorems, maybe you could, depending on what you're trying to verify, but the problem in the beginning was we have these arbitrary rotations. Eventually you would probably approximate them with Clifford plus T, but if you want to prove it before doing any decompositions, you'd have to reason abstractly about the parameters. But once you have cutoff bounds, maybe you could prove that it's sufficient to look at the ones that can be realized in Clifford plus T if the cutoff bounds are low enough, for example. So that's an interesting point I hadn't thought about.
Yeah, I think that would be cool. Thank you. All right, let's thank the speaker again.
So now the session is over and we have a coffee break. Everything should be served. I think we come back at 4, right? Okay, good.
Okay, now it's working. We wait some minutes. Welcome back for our last session. We start with our keynote speaker. He is Nathan Shama, sorry, and he talk about MITQ, a toolbox for quantum error mitigation and error suppression.
Thank you, Nicola. Thank you, Professor Alessandra Di Piero and Karsten for the kind invitation. All of you for being here, and those that are remotely connected or maybe will watch later on. So my name is Nathan Shama, and I'm gonna tell you a bit more about this open source toolkit for error mitigation and error suppression that we developed at Unitary Fund with a broad community. But first, I'm gonna start with an overview of what Unitary Fund is. Since it's a kind of unique organization, and we run many programs that are of relevance to what has been said in the past, I will spend a few minutes there. Please, I'll also ask help from the organizers or chair. Tell me when it's like about 10 minutes or 15 minutes, because I should start already with the error resilience and MITIC part. By error resilience, I want to put everything together. So now we have different terms like error suppression, error mitigation, quantum error correction, but basically they all feed into the error budget that we want to remove or at least decrease. And we'll give you also some information about the specific software toolkit before having introduced error mitigation techniques and approaches. So actually, no, sorry. Part one is Unitary Fund. So you may recognize these logos, especially in this community. And these are amazing open source projects, very important, especially for the scientific community. And as you can see on the bottom part of the slide, they are supported by non-profit organizations. And this is what Unitary Fund does, and it does it for quantum software, or more generally, not only for quantum computing, for quantum technologies, open source software, and open communities. So the mission is to make quantum technologies as open as possible and to benefit as many people as possible. And in practice, we are a kind of a unique organization that is half devoted to research and half does community activities. And the way it started was with these fast, no strings attached, no bureaucracy involved microgrants. And we've given 100 microgrants to date. It's a milestone we just celebrated in 31 countries. I will tell you a bit more about this, although, and in this part of the talk, I'll speak about the many community programs we have and projects, but actually the part I am here for is for the research. This is the technical staff at Unitary Fund, which I lead. Here I'm joined by Farouk Labib, one of our technical staff members. And here you see the other folks, including some alumni, and also a summer intern, open source fellow Purva Thakre. I also want to acknowledge the directors that join Will, Zhang, and me on a voluntary basis to steer the organization, as well as thanking the supporters. So we are about to announce the 2024 members of Unitary Fund, which are those that help fund our community activities. So these are the 2023 members. 2024 members will not be too upset, hopefully. And also, as well as additional supporters, individuals, and of course, institutions such as US DOE, the NSF, the Wellcome Leap, that fund part of the work that we do. So speaking about the microgrants, I mentioned that we funded 100 projects to date. This is basically anything that fits is a misfit, or it used to be a misfit. Anything that is in between an idea for a venture-backed startup and purely academic research papers or research output. So what's in between? Usually you could apply for a Unitary Fund grant, especially if you're doing something that may help others. So what helps others in this phase, especially in where can you have an impact with a small amount of funding, is generally open source software. We'll speak a bit about hardware, we're getting there. But so far we funded more than 100 teams in 31 countries. And sometimes they ended up being venture-backed startups. But usually these are projects by researchers, explorers, professors, hobbyists. And sometimes this is the first thing that someone does in quantum, and then they start a journey, as I will show. And all of this has been funded basically with a little bit less than the cost of 2 fully funded PhD studentships for a US university for 4 or 5 years, whatever it is. So actually this is a nice example. This is actually before I joined Unitary Fund in 2020. The first quantum thing in Armenia, I think, was this Gate 42 collective that then led to the national initiative in that country. And after the first 2 talks today, in the first session, I could not avoid putting this slide, which is a slide that we put to give any information about the kind of network effects that we start to have. So PyZX is one of the first projects that was funded. It's a Python-based ZX calculus toolkit to help compile these quantum circuits using this diagrammatic approach. Another project that got funded by Unitary Fund was Yao.jl, so in Julia. And they got inspired, and so they decided to develop their own domain-specific language for ZX calculus. And this led to this Yaolang project that was funded also as part of this microgrant approach. And now this summer in Eindhoven, these folks are organizing, I think, the first quantum track at JuliaCon, where Unitary Fund is also supporting, which will be in Eindhoven in a couple of weeks, I believe. Another important project that we support is QTIP, which is actually how I got into quantum open source. I developed exactly some methods to go from a single qubit interacting with a cavity, which is a very powerful point of view for modeling what happens in quantum processing units also, but also beyond, to what happens when you have collective effects. So you have super radiance, many-body interactions in a dissipative setting. And QTIP is actually a project that started many years ago, even before I started working on it. And we've now reached 1 million downloads of the software. And Unitary Fund specifically helped establish a governance, because it started inside the research group, as it often happens at RIKEN, where I was a postdoc. And now we have an admin team, a charter, a board, and we just held the second workshop of QTIP developers earlier in April with 25 maintainers. So before the pandemic, I organized the first workshop of that kind. It was 5 people, roughly, 5 or 6 people. And this time we were about 30 people, because then we were also people from RIKEN joining in. So talking about events, Savika didn't mention is Unitary Fund is fully remote as an organization, so our team is a bit delocalized. But we started holding our in-person events. We did it last year with UnitaryCon, a bit with the JuliaCon, PyCon, UnitaryCon, which was held in Rome at Tecnocolo Tiburtino, thanks to our headline supporter Quantum Italia. And the next event will be this year in September at Aalto University in Finland. So if you're interested in participating, let me know. Another important program we run is the Quantum Open Source Software Survey. We are an independent organization, so we're well positioned to basically run this survey. we want to know what's going on, especially what developers in quantum software think and what they use. This is just an example with dumbbell plots year on year on what users of quantum cloud services said they're using as their most used provider, but you can delve in, there's information about salary, you can filter on startups, research institution, information on compilers, specific projects, and so on and so forth. And all the results, aggregated data, is available online, open source, and we'll run it also this year. I mentioned hardware. So what is the equivalent of Arduino or Raspberry Pi in quantum technology? Of course, at least for the qubit technology, it's generally not as simple as this. You need sometimes cryogenics, sometimes other kind of materials. So I led this review paper with many experts in the field that is now published in APL Quantum. That is the first report on what we could consider open hardware at large. So by open hardware, one means, for example, open blueprints available to everyone to build your own hardware. In this case, we include, I would say very loosely, for example, software to do exactly this, such as PyEPR or Qiskit Metal, but also software that is used to operate hardware in the lab. So KQ circuits and PyEPR are, I would say, like really orthodoxly, we could consider them open hardware, but more loosely, we can also include facilities such as foundries, and as I said, also tools that may be hardware or software operating on hardware or running on specific hardware, such as Kik, RTIC, Kibolab that has been mentioned. So the closer you get to hardware, the blurrier it becomes. So have a look at this review. If you are interested, we basically collected all the existing projects at the time that had some traction, and there's also some sort of like distinction by architecture. You will find that, for example, for photonics, there's not much in terms of projects and facilities. Now there's like Perceval is an example of a photonic quantum compiler. We funded, as Unitary Fund, a measurement-based quantum toolkit called Graphics. And so this is very insightful to learn more also about facilities. And when I mean facilities, I mean open test beds where someone could test their device, one could use them for characterization, or someone could send jobs similar to what is done on the cloud by industry providers. So it's very important that we start having also institutional frameworks where you can do this, and there's a lot of activity, especially here in the EU and the US, to tie this with HPC centers. And we're getting more and more into this open hardware support at Unitary Fund, where something we're learning, especially where I think there's almost no experimentalists in the team, or used to be some. So one example where we help, which can also be an example for other projects, is we host a community call for the KIC project, this quantum instrumentation control kit developed at Fermilab and other places. And it's been like the first time those maintainers could get in touch with a actually quite broad community of now about 100 labs worldwide using their software and sometimes using their FPGA. And we're also a member of the Open Quantum Design initiative based in Waterloo, which will be the first fully open source quantum computer from the scratch. And we also started funding some nice pioneering projects such as Open Quantum. They all have similar names, but very different. Open Quantum is a cold atom CAD project, and LabScript QC then evolved in a more general API to access cold atom experiments called Scular. Unitary Hack is our program that is based on supporting existing projects. So we're funding new projects with a microgrant program. Sometimes actually the microgrant program, it's even just like an idea that then ends up in being a pull request of a method in the QTIP ME solver that is used by thousands of users. But also, of course, we need to support existing projects. And this is what this hackathon does. Hackathons are great for talent sourcing, but sometimes the POC goes into the bin the day after the hackathon. It's not really used. It's actually, it's an overhead to think about a problem that someone could solve in the time of a hackathon. So Unity Hack is a bit of a contrary. We ask existing maintainers, this year of over 50 projects, what are their thorny issues and how the community can help. This year we have over 800 people signing up remotely to this program. It runs thanks to some automation with a YML file through GitHub, and 132 issues were closed with 10K claimed. So this is how it looks like for a couple of projects. This is the Cadence project at the beginning of event. This is the KubeRaid SDK, and you see that some bounties have been awarded during the event. We also had some in-person events. It's the first time this year, even if it's a fourth year we run the event. Happy to partner with folks here. If you want to do like a one-day meetup, it's very simple to do, and these are folks at the University of Mexico joining in. We had also University of Washington and at Aalto University. I added this slide for Bettina, but she's not here. But yeah, Q.Q is one of a project that benefit from Unity Hack. So it's also like a gamification kind of thing. So we have a hackathon leaderboard with the folks who's helped most projects. And so take, for example, this user, Golanor. He helped solve issues in 3 different projects. It's fantastic. And sometimes for these folks, it's the first time they contribute to Quantum. So an example is Davide Gessa, an open source freelancer based in Sardinia, where he also goes sailing, as he says. He started last year and was actually second in place in Unity Hack, the first time he did anything Quantum. Because, of course, in Unity Hack, there's also non-quantum issues. Like you may have a problem with some kind of decoder, you're not expert at web development, and so on and so forth. So later on, last year, we funded the class kit Python to Quantum sort of like compiler. And this year, he participated as maintainer to Unity Hack with over 4 bounties solved. And finally, I'm getting a bit over time because I should start with error mitigation. Let me mention that we also tackle something very important that has been mentioned here earlier, that is benchmarking of quantum computing metrics. And we do this with a project that is inspired by MLPerf and Papers with Code, projects coming from the HPC and machine learning community, where anyone can make a new submission, which is basically a hyperlink to generally archive paper, and then create a taxonomy using the tools of this web app, applications, compilation, error correction, mitigation, hardware, and simulation of high-level buckets, and then extract data from the papers. So part of it needs to be done manually, but then these charts, for example, get generated automatically. And there's a lot of, this is a very contentious issue, topic, benchmarking, but we need to make the field more transparent, and also for outsiders, but even for insiders alike. So it's a very nice plot on resource estimation. This is actually a plot we curate directly. And you see, for example, I will not get into the details, but these are like resource estimations on a log by log scale for number of logical operations and number of qubits. Either all resource estimates, classical intractable, or useful problems. And you can see that in some cases we're far, but in some other cases you see how, okay, we're improving on a kind of like resource estimation for specific tasks. As I said, this is a very important topic. You also need domain expertise. That's why we launched let's say, an open call for members to volunteer. And these are the members of the Open Quantum Benchmarks Committee that have met, have divided into these sort of subcommittees depending on task, and they're helping define what state-of-the-art metrics we should showcase on Metric. But please check out Metric if you have a new benchmark, a new data set, something you would like to showcase from Cubo to hardware metrics, T1, T2, please check it out. Okay, now I start with a real talk, and I hope I can go through it. I will have to skip something. But first of all, quantum error mitigation. So quantum error mitigation, it's a kind of a new jargon that actually contains a lot of new ideas, but that are also informed and benefit from fields that are in some cases much broader, adjacent, and that have been there for a while, that take some different names. So one of them is, of course, quantum characterization, verification, and validation, QCVV. Another field is quantum optimal control. And other fields are open quantum system and quantum error correction. But what are the specifics of quantum error mitigation? So let's make a sort of like a scorecard with respect to standard quantum error correction. So in quantum error correction, you encode logical qubits into many physical qubits, but then you have to apply intermediate measurements for syndrome detection and correction operations based on the measured syndrome. And this, if you are below some threshold, becomes scalable, but is not currently suitable for current quantum devices, at least the one you can access from cloud providers. Error mitigation, on the contrary, is based on the idea of sending multiple quantum programs to the device, collect the results, and then apply some further transformation based on these noisy results. And many results show that it's generally asymptotically unscalable, but in this near-term space, it may be very interesting, but also say add something to this because we can also relax these constraints. So how can we look at quantum error mitigation in a workflow point of view? So imagine you have a quantum program and you generally launch a single quantum circuit, simplest quantum program. You run on a backend, real or simulated result, and then you get a noisy result, or many noisy results of the same quantum circuit. Here what we're doing, we're generating many intermediate programs, we're exploring the quantum noise or noisy landscape, and then we apply some only classical post-processing technique that depends technique to technique. So these are the main techniques in quantum error mitigation. They're all supported by MITIC. The one I will speak more about is zero noise extrapolation. We also have probabilistic error cancellation. So I'll get more into the detail of zero noise extrapolation later on. But generally speaking, zero noise extrapolation works at the full quantum circuit level. Probabilistic error cancellation requires a characterization of a noise at the gate level, at the unitary level, and so you basically decompose your ideal operation in terms of a linear combination of a noisy operation. Then you have learning-based methods where you basically generate training data that is easy to be simulated on classical resources. You learn how to correct, and then you apply to a different distribution with all the caveats that this leads you to incur in. Now you have symmetry-based techniques. These are the most similar to standard quantum error correction, but you don't have active feedback. So what you do is actually a projection, generally, into a subspace that is invariant under these symmetry operators for your density matrix raw. And then you have what technically are just called error suppression techniques, which don't add generally even no overhead in terms of shots, such as dynamical decoupling, in which you insert, for example, sequences when you have your qubit that is a bit idle to decouple it from the environment noise, or polytrilling, in which you actually modify the gates to insert noise in a way such that you can map the existing noise. You tailor the noise into some noise that is more amenable to be mitigated. And then there is a lot of other research. So this is like just a selection of the work on the topic. You can find all the references on mitic.readthedocs.io. And to make things even more interesting, let me say that definitely quantum error mitigation, quantum error correction stand on two sides of overhead, where on one side you have sampling overhead for error mitigation, and qubit overhead for quantum error correction, but the two things can be hybridized. So these are some recent papers, including some from our group with the University of Chicago, where we lowered the threshold for quantum error correction to apply approximate protocols implementing some ideas from quantum error mitigation, such as approximate T-gadget gates in these other papers, and in this case, the error mitigation inference and scaling is applied in the logical qubit space. So let me check on time. Yeah, we can make it. So zero noise extrapolation. How many of you are familiar with this technique? No one. Okay. Oh, some. Okay. So let's try to review it quickly, because I think it's easy and it's satisfying to understand what it is. So generally, when you have a Schrödinger equation, it's just the unitary. Here in this von Neumann formalism, we add a term that we don't control, which is the noise operator. And we can assume that it adds linearly with something that is a noise scale factor that is dimensionless. So what you could do is actually, so you cannot get rid of this, but actually, if you make things slower, your pulses, your instructions are slower, you can make these relatively count more with respect to actually the noiseless part, which is the one containing the actual quantum program. And one way of doing this is to stretch your pulse. So you're making things worse, which doesn't make sense at first. And let me show you why it makes sense. So if you were not to do anything, you run things in this noise scale factor parameter space at one level, let's call it 1, because it's base noise. And as you make your stretch your pulses, you get things get worse and worse. And of course, the fidelity of whatever test benchmark you're running deteriorates. But then if you extrapolate, if you're lucky, you get to the zero noise limit. So that's zero noise extrapolation. And it's based of 2 steps, noise scaling and inference method. And this is actually some real results from MITIC on IBM Q Armonk on a randomized benchmarking experiment. This is actually the first paper, I think, impactful, showing it by IBM, by their group, Kandala and others, showing how you could actually, you see here in this case and also this case, you could gain more in terms of fidelity, even if you make your quantum program deeper and deeper by applying this zero noise extrapolation protocol. But what is the problem here? Is that if you're not IBM or if you don't have your own lab, that generally when you interact with a quantum device, this is a Lego version, you get bit strings. So you don't have pulse level access. In some cases, actually, IBM now implements pulse level access with Qiskit Pulse, but you need some expertise to compile pulses. So what can we do if we just stay at the digital level? Well, actually, if you look at the workflow in this way, if you generate many noise-scale quantum circuits, you don't need control at the pulse level, which is what we do with MITIC. So the pulse stretching is shown here, and what we do, we implement local and global folding. So imagine that you have a unitary G with a set of gates. We actually can apply G dagger G, which gives you identity, but makes the program longer. So in presence of noise, this program is worse than that one. Actually, when you compile, you do the opposite, right? And then there's many degrees of freedom when you do this sort of like folding, because you can fold things in different ways, and I'll get in a minute what this entails in real cases. So let me show you just a bit of code. So imagine that you import Qiskit, you have your quantum circuit, and then you apply global folding, and what you obtain from your initial quantum circuit here is this other quantum circuit. And when you extrapolate, this is also data from IBM and Rigetti from real devices. What happens is that you can apply some, this is curve fitting. So you can apply what we call linear fitting, linear factory. We define like a Python object, which are factories. You can apply Richardson extrapolation, which is this polynomial kind of fitting, or you can apply exponential fitting. So this is actually the way we envision MITIC and how MITIC works. And now we have added more techniques than zero noise extrapolation, but they all happen at this level. Many intermediate circuits and many noisy results that are mitigated. So it's basically a compiler. What does it work with? A lot of front ends. So the internals are taken care of by Circ, but then we have some conversions. We also accept, for example, Penny Lane and Kibo programs. And then it's completely backend agnostic, thanks to this design choice. This is a sort of like outdated graph of what is the MITIC library. So we have many techniques, and they're divided in submodules. CDR is a Clifford data regression. Two important utils are these ones, which I will mention briefly. I mentioned the conversions, so the interface, and then we have benchmarks. So benchmarks are fundamental, benchmark quantum circuit for your execution. This is another example of a full program with defining this execute function. Just 5 minutes, okay. And here you ZNE.execute. ZNE is just the different line that you apply instead of just executing the circuit, and you see how the error has been reduced. Okay, I don't have too much. I mentioned the front ends. It's very, very simple to look at, and the back ends are also agnostic. Let me skip this. Okay, these are the currently supported techniques. In MITIC, we have probabilistic error cancellation, Clifford data regression, digital dynamical decoupling, readout error mitigation, polytrilling, quantum subspace expansion, and robust shadow estimation, which is based on classical shadows. This is some of the research we performed based on MITIC with collaborators. You find everything on the MITIC documentation. I will just speak briefly, if I can, about this, and these projects. So let me get there in a second. So we said that you can do different kinds of folding, but what is the change in terms of like real noise? And this is what we did in this project, where you see different kind of like folding and what happens to your system when you have a white noise. When you have a white noise, it doesn't change, nothing changes. So if your color, your spectrum of a noise, it's flat, all the techniques are equivalent. But as soon as you start to have some sort of like color, some frequency dependence, they all change broadly. And we found the global folding is the one that is most robust to this kind of like pink noise or 1/f noise. And another way to think about it is if you look at the sort of like the frequency response of your quantum circuit that you plot here, what you want to happen is you would like, as it is in this case of global unitary folding, you would like that for the scaled quantum circuits, your sort of like harmonics, like in this way, in a proper way, they don't change. If they're modified, you actually are applying a low pass or high pass filter, and you're modifying the response of a control circuit. Briefly, let me mention, maybe I have a couple of minutes more.
Yes.
Yeah.
2 minutes, 2 or 3 minutes.
Yeah, okay. So one other work we worked on is hybridizing zero noise extrapolation with probabilistic error cancellation. So one way of looking at zero noise extrapolation is that you're actually applying the same circuit at different noise scale factors, whereas in probabilistic error cancellation, you have a single noise scale factor, but you always change a bit your quantum circuit because you want to modify, you want to explore the noise space that way. And in NEPEC, noise extended probabilistic error cancellation, you actually play with these 2 degrees of freedoms at the same time. And what you can do is the equation I showed previously. Instead of decomposing at a fixed noise level the ideal operations in terms of noise operations or gates, you add this other degree of freedom. So it's very simple. And hybridizing error correction with error mitigation, this is an example in which we performed the zero noise extrapolation with respect to the code distance, so in the logical space. So here you go from distance equal 5 surface code to something that is a distance equal 9, and then you extrapolate. And the benefit of doing this is also that you can reuse more qubits at the same time, so you also save up something in compilation. And here we have some experiments with Steam simulator going to thousands of depth for many qubits. And finally, let's say, yeah, benchmarks are fundamental. You have many tools to run your benchmarks. So even if you use Mythic just for this, I think it's very useful. And let me skip through this paper about results. Okay, let me just say this to conclude these two slides. So these are recently added techniques. We add new techniques thanks to the support of the community. And so as you can see here, it's thanks to a network of collaborators. So I really encourage you to collaborate to this project. These are some of the statistics of the project. We have, you know, it's distributed on PyPy. You have everything to read or up on the Read the Docs. We have a Discord channel with weekly meetings, and we have a white paper. Only this. So what's next? The 2024 roadmap, resource estimation tools for error mitigation, closer integration with a wider compiler stack. So we heard about MLIR and other techniques now that the field becomes more complex, hybridizing techniques, and hardware-aware mitigation, and also composing existing techniques. So what we're playing with is, for example, how much benefit you can get if you apply polytrilling with ZNE or dynamical decoupling with ZNE. And yeah, coming up in August, there's this in-person workshop at University of Massachusetts Amherst. So if you're around and want to join, check out the website. Registration is still open. That's all.
Thank you for the talk. Are there some questions?
That's a lot of wonderful stuff. Do you have benchmarks on Hamiltonian simulation?
Could you clarify what you mean by Hamiltonian simulator simulation?
Some circuits that encode directly some Hamiltonian simulation problem, and so I can execute the circuit and get Hamiltonian simulation.
We would have to check. I'm not sure, but it would be great to add. I saw this sort of like a HamLib project. It would be great to integrate it with metric. So you see, the way to check, we go to task. I think this is a sort of like, the application is so simulation is actually classical simulation. So application is Hamiltonian simulation. This is a bug. So ground state energy is not what you mean. Max cut, finance, amplitude phase estimation, touches. So I guess, so for example, this solid state material simulation may have, yeah. And in this case, yes, this is some of the results that we have. You can then explore the results. For example, you click here, in this case a VQE, then you go to the submission, you find, so it's also great to navigate the literature. But yeah, this is one example. But yeah, it would be great to add more stuff here.
Yeah, I had just two questions. One was currently how easy it is to combine like different techniques for noise mitigation, like for example polyturning or like along with zero noise extrapolation. And the second was on your error correction example, like what particular portions of the error correction code are like you're applying zero noise extrapolation on just for that particular case? Just curious about it.
What portion?
So like the simulation of the Steam code that you were doing,
yeah.
Like is it just like all operations also have zero noise extrapolation for noise mitigation, or was it just like certain sets of it, like for example applying like some non-transversal operations or something like that? Like so what exactly were you doing there for the Steam simulation? Was just curious.
So let me answer this first. So zero noise extrapolation is applied at the level of a quantum circuit. So in this case, I think we're plotting, I think very simple randomized benchmarking or mirror quantum circuit. And we assume that they're already in the logical space. So we're applying to every logical operation in that case, yeah. Hope that answered your question.
Yeah.
And the first part is, so our current effort is to make these techniques as modular as possible. And we also have some internal refactoring regarding this. So if you go here to these are all tutorials of Mythic. And some of them are, the last ones are about composing techniques. So this one is actually very nice. It's composed by Jordan Sullivan, just added. It composes dynamical decoupling with zero noise extrapolation, and then at the end should get a better result than by applying simply dynamical decoupling or zero noise extrapolation. So in some cases it's easy. In some cases the techniques are not compatible by definition. So
There are many questions. So many, okay.
Yeah, thank you so much, Nathan. It was very great to see everything. Actually, I really enjoyed it. And I have many questions, so we can take that offline. I just wanted to ask right now if there is any applicability or connection with data encoding or this quantum state preparation with Mythic, because that is, you prepare the state and then you do the algorithm. Does it make sense to apply these methods here?
Yeah, for sure. They're really agnostic with this respect, and even if I was skimming through it a bit quickly, the benchmarks we use many times are basically they're quantum circuits, but they're states. So GHZ states are an example, W states, and so on and so forth. So definitely we can apply error mitigation to these states if that's also the goal. Yeah.
One last question.
Yeah, one more question, which is like, I remember like IBM, I think had some work on like how different noise mitigation techniques like interact with each other and how certain techniques together like sort of hurt performance overall for the compiler or like on their hardware. Did you guys like see something similar for your experiments or like whatever like you guys have done up till now for like combining different techniques together?
Yeah, so combining techniques, these tutorials are the part where you see it. One way of combining techniques is even that framework that I mentioned about noise extended probabilistic error cancellation. We have a couple of papers on this. This is a theory paper, but then we have a paper with Peter Orth and Ben McDonough on these, on actual specific problems. So this is, for example, a way to think about combining zero noise extrapolation, probabilistic error cancellation. NEPEC is the high-level formalism. Then what you obtain, it's something that takes the flavor of these, I think it's called PEA, the folks like this probabilistic error amplification or probabilistic error reduction or virtual probabilistic error correction. So there's many flavors to it. Yes, so I would say with respect to combination, that's the answer.
Thank you again. Our next speaker is Raphael Seidel. Yes, okay. Seidel. And he speaks about quantum backtracking in CRISP applied to Sudoku problems.
All right, so yeah. Hi everyone, I'm Raphael from Berlin. And today I want to talk to you about basically 3 different things. So first of all, the quantum backtracking algorithm, which is a quantum algorithm which is quite old actually already, almost a decade. But it's for whatever reason not that popular. I don't know why. I think it's super awesome. Second thing I want to talk about is CRISP. And the third thing I want to talk about is how we apply it to Sudoku problems. So let's get to it. Basically, this work is based on a paper that we published earlier this year. You can find it on arXiv. And there's also a really nice tutorial on our website, which basically lets you recreate all the things that we do. There's also like a lot of like practical advice how you do it and what is done. And together with the paper, I think it can give you a really good overview over what we do and why we do it. Okay, so first of all, let me explain the quantum backtracking algorithm. What this algorithm does is basically it gives you a quantum version of an arbitrary backtracking algorithm. What is backtracking? It's a very like general procedure, kind of similar to brute force searching, but a bit more into leveraging problem structure. Basically, what you're giving is two functions. It's the reject and the complete function. And the rest of the talk I'm going to call the complete function accept function, but it doesn't matter. And you're basically traversing this kind of backtracking tree, and you go down and down and down until you had a node where it has reject, and then you go to the sibling node, and if that is rejected too, then you go to the on node, basically, and at some point you end up with a node where the assignment is complete. And yeah, why is this useful compared to brute force search? You have this reject function, and with this reject function you can basically discard large parts of the problem by simply not considering it anymore. And yeah, how does these accept and reject functions look for Sudoku? Well, it's not that complicated. If you have an entry that is contradicting the rules of Sudoku, it's rejected. And if you have a full assignment where none of the assignments before got rejected, then you have an accepted node. Okay, so, but how does this look in the quantum realm? It's an algorithm proposed by Ashley Montanaro, and gives you quadratic speedup over arbitrary classical backtracking problems. But it's, I would say, challenging to implement, not only because the unitary is a bit weird, to say the least. It's also software engineering-wise not so easy, because you have to, of course, if you want to have like a reusable implementation, you have to deal with a lot of things, especially if you have a unitary like this. You have, compared to Grover's algorithm, you have two oracles that you need to manage. So it's not that easy, and so far there is really no open source implementation at all, apart from what we put online now. And here you can see a little visualization how this algorithm works. This backtracking tree here is basically what you saw before, a bit rearranged, but it's basically the same. And we can now see how the quantum algorithm explores this backtracking tree. And yeah, what you can really see is that these branches here, they're never explored. So there's a really restricted search space, so to say, which is why this algorithm really allows you to leverage problem structure and not brute force like Grover's algorithm would do it. Okay, so next part of this talk is CRISP. CRISP is an open source quantum programming language. It's probably the only really high level language that's actually compilable. And we take a bit of a different approach compared to circuit-based approaches like Qiskit or Cirq or you name it, because we don't center the center of attention around quantum circuits, but around quantum variables and functions. And this allows you to significantly enhance many development aspects. For instance, it's much easier to produce some prototypes. The code size is significantly reduced. You can maintain it much better because you can look into the code much better. The state vector representation is much more structured. You can basically fix your code much better. So there's really a lot of aspects that are improved if you program with Crisp. It's open source and you can install it with this command. And I give you a little code example here for quantum phase estimation to give you an idea how Crisp code looks like. And yeah, basically this code implements quantum phase estimation as a higher order quantum function, and we receive a quantum variable psi, Python function u, and classical integer called precision. And then we allocate a quantum float that will store the result. This signature here says that the quantum float can represent values between 0 and 1 with the granularity of 2 to the minus precision. And then we just do the quantum phase estimation algorithm. That is, we initialize the gate in the uniform superposition state, and then we loop over the precision qubits. And yeah, this one basically says that anything that happens inside the indented area is controlled on this qubit. So it's really the quantum phase estimation algorithm you see there. Shouldn't forget the quantum Fourier transform. And what's probably already visible to you is that here we don't have a quantum circuit. We have really a Python function there. So you can actually really easily exchange what is actually happening here. If you have, for instance, a function that is using 10 ancilla, you can simply exchange it. If you have a function that uses 20, you can also easily exchange it. If you would do that kind of thing in Qiskit, you would have to rewrite your whole code because you would have to allocate 20 new qubits and think about where are they coming from, where are they going, all this kind of business. Actually, we even published a paper that went online literally today, so go check it out. There is a lot more details on the software engineering aspects of Crisp, but also many examples and an overview over the programming abstractions that we introduce with Crisp. But the talk is not about Crisp, but backtracking, so let's get back to it. Yeah, we have a dead simple interface to backtracking within Crisp, and basically it works like this. You specify a maximum recursion depth. You specify a quantum variable that is basically specifying the branches that the backtracking algorithm can take. And then you give the accept and the reject function, and you're basically done. All this backtracking logic is completely hidden from the user. And yeah, here there's some more details. The backtracking basically works by the backtracking tree is specified by two variables. It's one hot encoded quantum variable h, which stands for height, and a quantum array called branch QA, which specifies which kind of branches have been taken by the quantum algorithm. And here you see the little example. This is the path that you take from the node, and it has height 2. One hot encoded is this bit string, and then the node is this kind of quantum state. And then, yeah, basically the accept and the reject function take in this quantum state here, and then they return a quantum bool. It's a one hot encoding. I think unary is something even different, but it also goes in the direction. Okay, then. Okay. Okay. And yeah, basically here you see an overview over how this would work in practice. It's a really stupid example. It's not Sudoku. We define an accept function. We define a reject function. And by the way, here you see this auto uncompute decorator, which does basically this automatic uncomputation that we already talked about in your talk. And yeah, then you basically just plug in all the stuff into this class here, quantum backtracking tree. You give the depth, the branch QV, the accept function, the reject function, and you initialize the node. You perform a quantum step, for instance, and then you call the visualize state vector, and then you will get some plot like this, depending on how many steps you actually performed. And if you want to find a solution, you can also do that by calling the find solution method. Yeah, so let me say a few words about the accept and the reject function. Accept function is really simple. It's simply if the tree reached a height of 0, then you are already done. Your solution is correct. Reject function is a bit more complicated. Out of scope here, we reformulate it as a graph coloring problem. Then we, every edge is a comparison, and then we compare, and at the end, we apply a multi-controlled X-gate and return newly allocated quantum bool. But yeah, it's out of scope. It's interesting though, so take a look at the paper, how we do it, but I can't talk about it here. Yeah, so this is a benchmark. As I told you, there's no real implementation of this algorithm, so there's not anything that we could compare to. So this graph doesn't really say anything, but give you an idea that this is actually compilable to a quantum circuit. But we think it's rather performant because we managed to solve instances with 9 empty fields on a simulator, which is, I think, impressive. And yeah, the best Grover-based Sudoku solvers that we could find, they do 2x2 Sudokus with 2 empty fields. So yeah, I don't know, there's just ones and zeros, so I would say not that cool. And yeah, so here's a summary. We gave the first fully compilable, fully general implementation of Montanaro's backtracking algorithm. We completely separated the backtracking logic from the problem specifics. So far, there were only Grover-based solvers for Sudoku, and we already have some more useful problems planned, and that would be train scheduling. And yeah, our solution is fully open source. It is ready to be explored. I told you in the beginning that there's a tutorial, and if you want to improve it, you are of course also welcome. Yeah, little ad break here. We're having a similar workshop like this one in September in Berlin. Please submit a paper, and that's it. Thank you.
Thank you for the talk. Are there any questions?
Just a quick question about the quantum backtracking algorithm. So you said it's a quadratic speedup? So quadratic doesn't sound so great.
Yeah, the speedup is in fact not that overwhelming, I would say, but it's certainly a very interesting algorithm, so yeah.
Okay, thanks.
So the compilation problem itself for CRISP, is that, what's the complexity of that? Is that a linear time problem, or is there something smart going on that makes the complexity of compilation be higher?
There is a lot of smart things going on, I would say, especially memory management and so on. But yeah, it should be linear in the amount of allocations times the amount of gates. So yeah, but to be honest, we didn't really measure it that much in this regard. But compiling the 9 open field instance, it took like, I don't know, maybe like 10 seconds or something. So it's,
Did you try the scale, like whatever big needs in your setting?
you mean like, I mean 3 by 3 is again, it's way more complicated because you cannot encode it that nicely anymore because your branch QV then needs 4 qubits instead of 3. But to answer your question, we didn't try it for 3 by 3.
9 by 9, that should be the goal.
Okay. Maybe I can even give some more details regarding that. We're actually trying to move CRISP in the direction of what was Bettina was telling earlier. We want to basically compile CRISP to MLIR and then have this unfolding of the actual quantum circuit done by some established compilation infrastructure. So we hope that with that we can eventually compile circuits with millions or maybe even billions of gates. But of course, executing them is a different story. But yeah, I'm positive that eventually it's going to scale.
Very nice talk, thanks. When you were showing this quantum float, it reminded me that the project I was briefly speaking about, ClassKit, I think we may have a kind of like similar approach because it's very, also what you showed, it's very Pythonic, and may you take care of the quantum resources unbeknownst to the user. So maybe check out that also project, I can put you in touch.
Yeah, I know it.
And after backtracking, what's next? I mean, do you want to populate your toolkit with algorithm, or that's left to the user?
Yeah, actually we have a bunch of more algorithms. We also have an implementation of Shor's algorithm, which is also pretty interesting and also very performant. We also have a Quava module, and yeah, basically I already said that we want to go into the direction of working on the infrastructure to make it like really scalable. But algorithm-wise, we want to move into the direction of Hamiltonian simulation because I think that there's a lot of like exponential algorithms that are coupled to this kind of topic. So that would be our next step, so to say.
Great. And sorry, and can you also define qubit connectivity?
So with this qubit connectivity kind of business, we're not really dealing that much, but what we can do is basically specify the kind of logic you have to submit a circuit. So basically what you can do is create a custom backend, so to say, and with this custom backend, in the backend before you submit the circuit somewhere, you can apply whatever logic you want, for instance, mapping it to a certain topology.
Thank you very much.
Hi, just one quick question. I think I might have missed it. What is like the I would like to say the overhead of like having the backtracking algorithm itself, like in the number of qubits, basically, in terms of like the height or whatever for the tree that you need?
Yeah, so that is really depending on how you encode. So we have the height encoded as 1-hot encoded. So basically the amount of qubits scales linearly with the height. You could also encode it binary, then you have a log scaling. But then the circuit is also going to be more expensive, so to say, because you need to like identify certain states and the binary encoding, and operating on the 1-hot encoding is cheaper. So.
Just one comment. It is probably not very surprising that Grover is performing not very well, right? Because you need to run it on very large instances or numbers if you want to get a good advantage. So maybe should be compared. I don't know how. I mean, I don't know how it scales the backtracking algorithm and. To be compared to the, in the asymptotic.
Yeah, so basically the problem of Grover is that it cannot discard the like invalid solution space, so to say. So in cases where you have barely any way to discard the solution space, you better run Grover. because it simply searches everything. If you have a problem that is like super structured and you can immediately reject a lot of solutions, then this one is better.
Thank you again. Okay, we can go on. The next talk is made by Gabriel Pontolillo. Okay, and is about a classical shadow for property-based testing of quantum programs.
Hello, is it working? Okay, I think it is. Yeah, so what we've been working on, what our research is, what we're currently working on is applying classical shadows to property-based testing to try and get some kind of advantage over just doing like tomography. So in this presentation, I'm going to go over basically what inspired us to look into this. I'll go into what classical shadows are, how we can construct classical shadows, what property-based testing is, why we think that classical shadows will be useful for this application, and we're going to go explain what we're going to basically research in the future and give an example of something that we could efficiently evaluate using property-based testing using classical shadow-based assertions. Okay, so just as some small introduction is, quantum computing, I'm sure we're well aware, but we have many challenges that come with quantum computing. You know, we have superposition, entanglement, no cloning theorems stopping us from being able to clone quantum states and move them to other registers. And so basically it's pretty much agreed that we need software engineering tools to be brought into the quantum computing context. And so that's basically the main topic of our research. Okay, so yeah, so the software engineering tools that we're looking at to try and that we've been focusing on is looking at testing and debugging. So you have these quantum systems, they can be quite not like reliable, and so we're looking at testing, so finding faults in software, debugging to find the location of faults and then removing from software. And our main focusing is adapting classical testing methodologies and bringing them to quantum programs. So in our previous research, what we've been looking at is a methodology called delta debugging. And essentially how it works is, I don't need to go into too much detail on delta debugging, but essentially the classical version is you have this set of deltas that's passed to this delta debugging loop, and you essentially create a test case that you evaluate using a test function, and it will recursively check applying different subsets of deltas to create new test cases and evaluate them. And the way we got it to work was by applying this thing called a property-based test oracle. So we applied this set of property-based tests in this application, and we found out that actually it was quite effective. Now, just to explain exactly what's going on here. So by applying this property-based test oracle, the faults identified graph line is basically the percentage of times that we are able to identify a fault within the quantum program. So we had these three examples here: teleportation, Fourier transform, and phase estimation. And so we increased the strength of the property-based test oracle by increasing the number of properties we evaluated, and we found some quite a nice correlation with how effective the property-based, the delta debugging algorithm was working. And so we thought this was quite interesting, kind of good indication that property-based testing might be quite effective at testing quantum programs. And so that's what really inspired us to look into it further. So currently we're working on just a fully fledged, because the way we implemented property-based testing was kind of like an ad hoc basis to work with delta debugging. So now we're focusing on implementing a proper framework for property-based testing in quantum programs. And so this is just kind of like the general idea. We're still quite earlier in the stage. But essentially, the main general idea with property-based testing is you specify a set of input generators that essentially generate an input, preconditions that the input must satisfy, and then operations what to execute, and then we need to check something, some kind of invariant about this program that we're interested in. Okay, but to give a more straight example, if we have like quantum teleportation, what we'd expect to see is if we create an arbitrary quantum state psi and provide it, precondition true means that there's no precondition for this property, and we provide slide 0, 0 to quantum teleportation, we would expect that after teleportation has been performed, that the qubit, the second qubit, would be equal to the input state that we initialized. So this is one simple example we can think of for quantum teleportation. But essentially, the main general idea is that you have many of these properties of this quantum program that in conjunction cover a lot of the semantics. Yeah. Okay. And specifically what we're looking at here is how do we check this post condition? Right, that's the main challenge that we've got going on. Okay, so this is some code, and yeah, we would be looking at down here, we would apply some kind of statistical assertion currently, and so it's fine to do this for like a simple property like this, where you're just looking at one single qubit in your algorithm. But what if your invariant that you're checking at the end involves a long chain of qubits? Obviously, performing some kind of tomography would not be feasible in this situation. And so that's why we're interested in classical shadows. So what's nice about classical shadows is that essentially they say in the paper that you can efficiently evaluate and estimate properties about a quantum state, but not necessarily like be able to retrieve a state, but you can efficiently estimate certain properties of a quantum state, and that's exactly what we're interested in. We, in property-based testing, we're not necessarily interested in knowing the exact output, but only some characteristics of the output that we can test. You know, when you, in conjunction, test many of these characteristics, can cover a lot of the semantics. Okay, so just to give an example of how classical shadows works, if you're not if you've not come across it yet. So this is imagine you have a quantum Fourier transform circuit here, and this is just a state row. And the first thing we would do to create the classical shadows is we would apply a unitary, and we would randomly sample it from a specific unitary set. I'll go into which kinds of set you would sample it from in a second. And then you perform a measurement in the Z basis, and you're left with a classical bit string. And then what you do is you classically store this bit string with the inverse of the unitary, and this can be done efficiently because of some properties of the unitaries you choose that we have chosen. Okay, and so this action here of inverting and storing the bit string can be seen as a quantum channel, and we can invert this quantum channel by applying some classical operations and essentially having a set of these snapshots of this quantum state. So this will store a snapshot of the quantum state, some information of the quantum state. And if you have a set of n of these snapshots, that's what we call a classical shadow. And how do we use it is we essentially, whenever we need to predict something like fidelity of a quantum state, we can just replace the quantum state with the classical shadow of its state to perform your calculations. Okay? And so how many measurements do we need to do this kind of operation is this very fun equation right here. But it's this log m. So if we have m things we want to estimate, so we can create we could estimate the fidelity of m with m observables. But also you have the second part, which is the shadow norm, and that depends on the unitary that you chose to create the classical shadow from. So if we're looking at Clifford circuits, so global Clifford circuits, the way we would invert the channel here is I explained it a second ago. M-1 channel, you do this, 2 to the n. I wonder if I can use this. Oh, okay, yeah. So you do this to invert the channel, and you'd use this value here. Okay, and this is the number of measurements we would need, plus the multiplied by the previous thing that I showed. And yeah, so this right here is the observable squared, and you'd find a trace of it. So this method here, using these global Clifford circuits, is good for estimating the fidelity of a state, because this value here will always be 1. The trace of a state is always 1. Okay, and then you also have this other unitary ensemble, which they describe in the paper, and that will scale with the locality of the observable you're estimating. So locality is how many qubits this observable is affecting. And so when you start estimating observables that affect many qubits, this becomes infeasible very quickly because it is exponential. But as you may notice, that there's no exponential number here. And so using this methodology here, we can estimate enormous circuits, provided certain conditions are met. Again, I'll explain that in a second. Okay, so one way we could construct an assertion that we could use for property-based testing, so asserting the equality of two circuits. So suppose we have these two quantum circuits. So you have, and this is the shadow of these circuits, rho and rho prime. One way we could check is by estimating a set of these matrices and checking that the expectation value is the same across all of the ones that we estimate. Okay, but the problem is that you're limited to these kinds of Hermitian matrices, right? And so these kinds of assertions wouldn't be fully general. You'd have to pick and choose what types of properties you can estimate using this methodology efficiently. And so what we're looking at to do in the future is we want to essentially use this classical shadow methodology to think of many of these properties that we could efficiently use for property-based testing. And that's using a lot of these functions that they said you can efficiently estimate, so fidelity, entanglement, wetnesses, create like a large set of these assertions we could utilize for property-based testing, and then use that to evaluate and see how well the property-based testing methodology works using these new assertions that you can make using classical shadows. Okay, and to give an example of something we could estimate efficiently using this, these kinds of assertions is, so assume we have this linear combination of unitary circuit, and all of these unitaries, let's say that these unitaries are initialized to a with a stabilizer. So these are stabilizer circuits, and they're very, very long, hundreds of qubits. You couldn't estimate them using tomography. We could efficiently calculate this using some kinds of assertions we could make with classical shadows. And that's pretty much it for me. Thank you.
Any questions?
Okay, so I have a point of confusion. So a couple of slides back, you had the formula of how many. Yeah, there we go. So you're
this one.
So on this slide, you're dividing on the left there. You're dividing by 2 to the n, and then just on the previous slide, you are dividing by epsilon squared. Were those two things related, or is that
this one here?
No, a little bit further back. You are there. You see, you have this number there that has divided by epsilon squared. Where did that go?
Yeah, no, sorry. I was just saying this is this component here.
Oh, so you're drawing that out on the next slide.
Yeah, sorry, it's too much, yeah. And again, yeah, this would still require a lot of measurements, because obviously if you want a good error.
Yeah, that's, I would say.
Yeah.
Okay.
Can I ask a quick question, though? So I was just wondering, this is a collaboration between computer scientists and physicists. So
Yes.
How did that work?
It doesn't work. It doesn't work. I mean, that's one thing that we found is quite interesting is physicists and computer scientists tend to talk about these concepts very differently, right? We have different names for the same things. And so there is quite a lot of confusion when we're trying to get our points across with each other. But we've now been collaborating with them for a while, and we're kind of starting to speak the same language. Yeah.
So in property-based testing, then making the generators is actually often one of the hard problems. How do you approach that, or is there any difference to doing it for normal programs?
So far, what I've got working right now is I don't know if there's anything that's too much different to how you would do it classically. I mean, it still is challenging, but I don't think it's especially challenging so far.
So do you do anything to ensure coverage of your tests, or that's usually what you want to do with the test generators?
Yeah, I know you would want to do this, but so far what we've got is just we essentially. So if we're generating a random state, we would just use like a Qiskit function to do that, because the way we've got it working right now is we're using Qiskit.
Right. Thank you.
Right, thank you.
Our next talk is from Alexander Kozel-Pipe, and it's about hybrid quantum classical machine learning with string diagrams.
Okay, is this working? Yep, sounds like it. Okay, thank you everyone, and thank you for the wonderful talks we've had so far. I'm Alex Kozel-Pipe, a PhD student at the University of Oxford, and today I'm going to talk to you from almost a pure mathematics perspective on hybrid classical quantum machine learning algorithms with string diagrams. So to set the scene, we're in the NISQ era of quantum computing, where quantum computers aren't yet sufficiently large nor sufficiently fault tolerant for practical uses of things like Shor and Grover's algorithm. And hybrid quantum classical algorithms, where there's an interplay between classical and quantum computations, offer a pragmatic solution to this. In fact, quantum machine learning algorithms such as the variational quantum eigensolver are hybrid algorithms. And in our work, we formalize these hybrid algorithms in terms of symmetric monoidal categories. What this gives us is some really nice, but completely rigorous formal mathematical diagrams to describe these algorithms. The formalization gives us a rigorous mathematical framework in which to describe these algorithms. Furthermore, we find that the maths captures some important characteristics of these quantum classical algorithms. And we can also integrate them with ZX diagrams, which allows us to do a sort of in-place quantum circuit optimization, where we can optimize these hybrid algorithms without having to separate out the quantum and classical parts. So just for anyone who's not familiar, the ZX calculus is a graphical language for reasoning about quantum computations and circuits. Applications include quantum circuit optimization, quantum error correction, and measurement-based quantum computing, just to name a few. And these diagrams are generated by Z spiders, the green ones you see on top, and X spiders, the red ones you see on the bottom. And they correspond to the quantum processes shown. We also have some syntactic sugar for the Hadamard gate, which we can express in terms of these Z&X spiders, as you can see here. Familiar quantum gates and quantum states are all expressible in terms of the ZX calculus. And we also get rewrite rules, allowing us to transform one ZX diagram into another. This is where applications like quantum circuit optimization are useful, because we can take one ZX diagram representing a quantum circuit and rewrite it into a smaller diagram, which is more computationally efficient. Now I'll move on to category theory. So category theory studies mathematical structures and the relationships between them. It's a high-level approach, and it focuses on the general patterns of how these mathematical universes connect and interact. And in our context, when we apply it to hybrid algorithms, we're interested in the mathematical universe of quantum systems and the mathematical universe of classical systems and how they interact. We'll see that actually, I've drawn in terms of diagrams, we get interesting things like quantum measurements producing a single classical value corresponding to the measurement probability. So what is a category? At its bare bones, a category is made up of objects and morphisms. These objects we can think of as systems, and we draw as wires. These morphisms we can think of as processes, and we draw as boxes. These systems can be a number of things. They could, for example, be vectors of real numbers, and these processes could be something like arithmetic operations, computing the loss function from a neural network, or if our systems are pairs of complex numbers corresponding to a single qubit system, our morphisms could be quantum circuits, like the one you see here. So we have a way of defining a classical universe and a quantum universe, but we need a way of going between them. This is done by a functor. So a functor is a structure-preserving map between two categories, or two mathematical universes. For example, we could take one that turns the ZX diagram into the complex matrix or vector that it represents. The fact that the functor is structure-preserving means that if I break this diagram down into small pieces, apply the functor to each piece, and then multiply together the resulting vectors and matrices, I get the same thing had I just applied the functor to the entire diagram. In terms of string diagrams, we can actually draw the application of a functor as a box. What this means is that I'm applying the functor to this red spider, and on the outside of the box, we have our classical category. This allows us to show that we're mapping this red spider into our classical category and nest it inside an entire diagram for classical systems. For anyone more familiar with category theory, our quantum system is actually the category of completely positive superoperators on two-dimensional Hilbert spaces. This category is compact closed, which intuitively means that it captures things we want in quantum information, like no cloning and no deleting. For the classical system, we define the Cartesian category of smooth maps between Euclidean spaces. The Cartesian fact means that we can copy and delete information freely, as we would expect in classical systems. And the fact that we're using smooth maps allows us for differentiating things, which we want in our machine learning applications. So we've got two things to do. We've got to go from this no cloning, no deleting kind of universe to a freely copying, free deleting kind of universe. And we also want to be able to differentiate things. So we do this by going through an intermediate step. First, we define a category of real matrices, and we map from our real matrices, our quantum system, to these real matrices, using a functor which I've shown the definition of here. Intuitively, and as some concrete examples, it expresses these quantum superoperations in terms of a Pauli basis. So what we get is that our Z state gets mapped to this vector, our X state gets mapped to this vector, Z and X rotations get mapped to these matrices, how do mod gates get mapped to this matrix, and a C0 gate gets mapped to this matrix here. So we've now been able to go from our complex amplitudes to our real matrices. The next step is going from real matrices to smooth maps. Now, because matrices represent linear maps, which are smooth, that part is fairly straightforward. However, there's a subtle difference between compact closed and Cartesian in category theory. So when we define a functor going from these matrices to smooth maps, and then compose it with our previous functor, we get a functor from our quantum system to our classical machine learning system that has a special property which we call lax-monoidal. In terms of diagrams, what this means is that if we apply a functor to a system with our functor box, we can have multiple wires entering the box being preserved as multiple wires. However, when multiple wires leave the box, they always get bundled into a single wire. Looking at our hybrid algorithms, what that means is that when we encode classical data onto the quantum system, the wires are preserved. However, even when no wires are leaving the box, we get a single wire out. This is quite nice for measurement because it means that if we have a diagram here which corresponds to a measurement, we still get a single wire out, which feeds a classical measurement probability into our from our quantum system. To show this concretely, I applied this framework to a quantum machine learning paper from 2018 where a parameterized quantum circuit is used for MNIST classification. The diagram here I've shown is slightly simplified for clarity. So at the moment, this diagram is just purely a quantum system. However, what we want to do is clearly delineate which parts of this are quantum, which parts of these are classical, and actually include some diagrammatic representation of things like computing expectation values and having a loss function. So the first thing we do is we put a functor box around our diagram. We then do some classical prose processing, where we compute an expectation value, we compute a loss function, and then we pull out the parts of our quantum system that actually correspond to classical data being encoded onto the quantum system, and parameters that we're going to optimize with the classical optimizer. So what we're left with is a fully formal mathematical description of this hybrid algorithm. So in summary, we took a diagram like this, where we have the interplay between different quantum and classical computations feeding information between each other, and provided a rigorous mathematical description of this. This description is also amenable to ZX-based optimization methods. What we want to do in further directions is there is in fact some category theoretic work as applied to classical machine learning, which allows you to express reverse derivatives and gradients and parameter updates. So we'd like to extend our work with this kind of formalism. What that means, though, is that because we're computing the gradients of quantum circuits, we have to use techniques like gradient recipes in order to calculate these gradients. It turns out that there's actually some existing work using an extension of the ZX calculus called ZXW that allows you to express these gradients as a diagram. So with these two future directions, we aim to try and formalize the entire hybrid quantum machine learning algorithm with our forward pass and backward pass in terms of all these diagrams. Another fun sort of side project would be to start implementing this in software where your high-level API is all in terms of these boxes and wires and these functor boxes and trying to wire things together. Okay, well that's it. So thank you very much.
Thank you for the talk. Questions? Okay.
I've got a slightly provocative question. So we just heard, I mean, so quantum, as you started by saying that in the current era of quantum computing, we're still sort of not there yet with big enough systems. And yet these ML methods are, you know, they deal with enormous, I mean, you know, that, you know, billion parameter systems that operate on petabytes of data. So are these, this field of combining ML with quantum, is it more than just taking two great buzzwords and making them coexist, or is there something real in this, or is it something that's going to be real in the future?
Well, I think that question is definitely beyond my level of expertise now, having not even done my thesis. However, one of the things I think is nice about this framework is that although I did it in terms of trying to, with the intention of looking at smooth maps, derivatives, that sort of thing, one thing I found actually while doing this is that it seems like one of the although this hybrid paradigm we talk of as like, while we wait for the bigger quantum computers to come along, it seems to me that there might be a situation in which we actually, and actually I think Bettina's talk earlier speaks to this, and we're actually interested in having CPUs, GPUs, and QPUs, just all our different processing units working alongside each other for the tasks that they're good at. In terms of the parameters and having lots of parameters in the machine learning model, I suppose what this also allows you to do, which I haven't illustrated in diagrams, is that these functor boxes actually have fusion rules. So if we then try to describe something slightly bigger like this, where you have lots of quantum systems and classical systems all over the place, you could actually have billions of parameters all pulled out, feeding into different parts of the algorithms that are quantum, and effectively have some interplay between these sorts of things. In terms of scalability, we'll have to see how things go with the future developments. Thank you.
So just a comment and a point. So the comment is DARPA has a project going on at the moment on building the benchmarks we should be working on the next 10 years. And the first thing they did was to get rid of quantum machine learning, because that's just not for the next 10 years. Anyway, on this thing with building the gradients, I very much recommend Xiaodi Wu's paper from PLDI'24 2020. It shows how to build the gradient circuit essentially by taking pieces up of the circuit that you want to differentiate. It's very neat. And so yeah, I've been teaching that paper in my class many times and it's very neat.
I'll grab that reference from you. Thank you.
Very nice talk. Thanks. One question. Now especially with quantum error correction, we start to have these sort of like feedback loops and mid-circuit measurements. Would they be amenable to be cast in this formalism? Like, is that still everything is quantum, or some parts are like sort of like classical subroutines? And the other question is, it's just a naive maybe comment from my point of view. When you were sort of like expanding into bigger matrices, those operations, and also the fact that you mentioned super operators, it reminded me of the treatment of certain kind of compact noisy operations, where you expand your matrix into, thanks to a super operator, into a bigger object. So I don't know if can noise be represented, simulated here, or maybe it's beyond this because it's more a tool for compilation.
So I think at the moment there's no noise model. I think that's the limitation of the categories I'm using, which are the smooth is the classical category is deterministic. I'm sure there's work on using more probabilistic categories and things like that to try and simulate noise. In terms addressing the previous point, there is, in terms of intermediate measurements, there is work in using the ZX calculus for expressing intermediate measurements. They do that by actually placing sort of parameters in the ZX diagram. I suppose what you could have is you could have I would expect that you can have measurements feeding out of your boxes and feeding into other boxes. In terms of measurements in the actual diagram, I haven't looked at that enough to know whether you'd be able to have kind of measurements within the same diagram feeding out of the box and coming back in somewhere.
Thanks.
Yeah, I actually have another comment to the quantum machine learning question. There's this theorem called Aronson-Ambainis conjecture, which basically says that quantum algorithms in general work better on problems where you have only a tiny amount of data, but a lot of structure. So Shor's algorithm obviously is a very nice example of that. And as it turns out, actually the same also applies to quantum machine learning. There has been a paper where they made a quantum machine learning model learn a discrete logarithm function, which also seems to be classically hard. So like if you want a classical neural network to learn discrete logarithm, this also seems to be exponentially expensive. For quantum machine learning, that seems to work.
Is there any other question? So about the quantum machine learning, just take your comment. So the model you are modeling here is quantum neural network, so to say. So this is a hybrid. You have the quantum part, and the optimization is completely classical, okay? But there are purely quantum machine learning model, okay, which are based on the implementation of a quantum kernel. Those methods are much more promising because they are completely quantum, okay? So they, from that kind of model, one of these is exactly what he was saying, is based on quantum algorithms that are exponentially faster, okay? And therefore not implementable on this NISC, but they require a fault-tolerant quantum computer, but they are provable. I mean, their advantage is provable, okay? So, it would be nice to see how these kernel models can be, you know,
yeah, I'm familiar with this work, I think. It's by Maria Schuld is one of the authors with the quantum support vector machines.
Exactly.
That's actually what's got me started thinking about this, because they do a lot on encoding data on quantum computers.
Yeah.
So originally this problem came about because I was thinking about, okay, well, we draw a quantum circuit and then we put all these numbers on it, but actually those numbers come from classical data that we've then put on the quantum computer. So that's almost exactly what you see here. In fact, what I was doing is this is basis embedding, where you've got a binary, there's x1, x2, x3, x4, that's a binary string, and then you're trying to turn it into a qubit system.
Mm-hmm.
Yeah.
Okay, I can introduce the final talk. Thank you again. Our final speaker is Sinan Pelivanoglu, and his talk is about a classical simulation of quantum circuit with partial inference effect.
Try to be quick so those of you who are heading to the reception can get there before the others finish all the wine. Yes, apparently.
I think that it is tomorrow.
No, I think they sent an email for today, no? Is it tomorrow? Anyway, we can check
okay.
afterwards. Okay, so I'll be talking about our work with Amr on partial interference effects. But before we get into what partial interference effects are, let's talk about quantum interference first. So quantum interference is one of the first things that many quantum textbooks and classes start with, the famous double slit experiment, not only because it is a very interesting thing, but it is also one of the core ideas that power the quantum algorithms, the ones at least that we know of so far. So quantum state and superposition can either build up constructively through interference. So if I have the same state psi, I have alpha and beta as the amplitudes, they will add up constructively. But if they're of opposite signs, then they will diminish through destructive interference. And if the magnitudes are the same, this will cancel out. So we have a basic Dosh-Josa circuit here, and at the bottom I have the vector formalism of how the state evolves throughout the circuit. You know, the first Hadamard on the first qubit, second Hadamard on the second qubit, and so on. But where is the interference here? Well, turns out in this formalism, the interference is almost implicit. It is buried. and it is buried in matrix multiplication. So if we look at the application of the second Hadamard gate on the first qubit, the interference technically happens when you multiply all the columns and the rows and add things up. So here, for example, in the first part, I have 2 amplitudes of opposite sign, and this cancels out. Let's look at another example. This is a Simon circuit for n equals 2 and a equals 3. And I have a total of 4 Hadamard gates, so 2 to the 4, I will have 16 intermediate states. And 4 of these are the outcomes that I will accept to some extent. 0, 0, 0, 0, 0, 0, 1, 1, and so on, and where depending on the measurement of B0 and B1, getting 0, 0 on the first 2 qubits will mean that the circuit will need to be restarted because 0 has a specific meaning in Simon's problem. And if I get 1, 1 on both qubits, then that is the answer that I'm looking for, and I'm happy. But instead of using the vector representation, that is the classical textbook way of doing this, let's look at this problem through like an execution tree. So what is happening here is essentially I have the circuit on the right, I am applying the first Hadamard on the first qubit, and I'm branching the execution out. Same thing for the first Hadamard on the second qubit, and I have the black box oracle that encodes the function itself, and finally the final 2 Hadamards. The states that I've underlined blue here are the ones that I mentioned early on that are somewhat acceptable for us. All those zeros means, again, the circuit needs to be restarted. And these will go through either constructive interference or destructive interference. The blue arrows here signify constructive, and the red ones signify destructive. For a moment, let's focus on destructive interference. So I have the state 0, 1, 1, 1 here. It appears twice, exactly twice in my tree. And the 2 occurrences are of same magnitude but opposite sign. So when these 2 states interfere, this state will basically disappear. It will not appear in my probability distribution. There will not be a way for me to sample this. That is, of course, theoretical. In practice, if you have noise, things can be a little bit different. But there's no way for me to sample this in theory. If this thing is going to disappear anyway, what if I didn't have to compute that anyway? Because it just seems like wasted work, right? I mean, it's going to disappear from my probability distribution. It is of no use to me, so why am I doing all this work? One, it is a computational step that adds some amount of complexity to my program, and 2, it is something that I have to store in memory. And here, it's not too bad, but there are problems where less than 10% of these intermediate states actually are the things that I care about, that will be building up constructively, and there will be hundreds of millions of intermediate states as my circuits grow larger. So maybe I can save a little bit of work if I'm clever. But of course, I don't know the answer ahead of time, so there's no way for me to sort of handpick these things. But perhaps we can do something a little bit clever to turn tides in our favor. So the question we're asking is, how much computation can we actually save on if we were truncating the branches that we didn't need? There are 3 crucial observations. One, as I stated earlier, the cancellation of amplitudes through interference is essentially the same as not doing that work in the first place. 2, again, the majority of the interference computations will be worked towards destructive interference, and very, very little in most cases is interference that I care about. And 3, many quantum algorithms function by manipulating the amplitudes to favor the correct results. And this is because, of course, were you going to take a picture? This is, of course, because our quantum algorithms are probabilistic, and this execution of Shor, we still have a chance of getting the incorrect result and rerunning the circuit. The way I like to visualize this is through a membrane model. So going back to our tree, we're going to make everything concurrent. So all of these new branches will spawn a new thread of control, and everything will be executing concurrently. So here, T1 through Tk are different threads of control. The half-filled circles mean that it is still doing some computation. There's still more gates in my circuit to apply to the local state. And the red ones, which are in majority, are the states that will disappear through destructive interference that I don't care about. And the green ones are the actual results that I would love to sample. And as these threads finish their work, they will push these results through this membrane, into this box. And as they enter this box, they will randomly start interfering. So if I have A and B on the state 1, it will become A plus B. And similarly, if I have A minus A, this state will completely disappear through interference. And if this was completely synchronized and we waited for everything to finish, this would be exactly the same thing as a textbook vector formalism of this kind of computation. But the fact that this is a concurrent operation and things can happen in randomized orders give us a new degree of freedom. So what I'm going to do is I'm going to pick some threshold x for my amplitude, 0.25, 0.1, depending on the problem. You have to be careful on how you pick this. And as soon as any state that makes it into this membrane reaches that threshold, I'm going to halt all the other ongoing terminations. There will be threads that haven't finished their work, that haven't pushed their state into this membrane yet, but I'll say, okay, I don't care about this. I'm going to stop here. And of course, whatever has made it in, the amplitude square will not add up to 1, so I'll have to rescale, and I'll sample from this subset that I have here. Going back to the observations that I've stated, per observation 3, which as a reminder is the one about most quantum algorithms manipulating amplitudes to favor correct results, a correct state that is a green state will have a higher probability of triggering a membrane shutdown than an incorrect one. So think of Grover, the amplitude of the correct result is much higher than the incorrect one. So if my threshold is high enough, then a correct state will trigger the shutdown. Per observation 2, when the membrane shuts down, because the ratio of states, the undesirable states that will disappear is much higher than the correct ones, a lot more of the states that I don't care about will be left out, and I will only lose very little of the states that I care about. And per what I stated above, again, if the threshold is high enough, we can guarantee enough correct states can get through for us to sample the correct outcome. Turns out this is very similar to a model of concurrency that already exists called chemical abstract machines. This original paper dates back to the 80s. It is a classical reversible model of concurrency. And chemical abstract machines model computation as the global evolution of a collection of atomic states that randomly interact with each other. So these molecules can essentially collide, like think of an actual chemical solution where molecules hit each other and go into a reaction or not based on compatibility. If they're not compatible, the molecules will just return to the pool. And if they're compatible, they can combine to create a new one with higher amplitude, or they can, molecule can decompose to create multiple smaller ones, which isn't all that applicable here. So here's the algorithm. We start a solution with our input state to the circuit. We place special step molecules into the solution. And when the input state hits the first one, it applies the next gate in line, which, if it's a Hadamard, then we will return 2 new molecules to our solution. And if there are no more gates to apply to that local state, then it is marked specifically to be ready for interference. And when 2 marked states that come into contact, if they are compatible, they will interfere to build up constructively, or they will diminish destructively, and no molecules will be returned. And after a specific reaction, if the molecule that is being returned to the solution has an amplitude that is greater than the threshold that I've determined, I will stop everything else. I will rescale my amplitudes, and I will sample from this subset. So we tested this on Grover for searching text states as well as different instances of three-side problem at up to 8 qubits. We were able to get 86% accuracy for 0.7 threshold. That is, we didn't do 30% of the work, and we still got good results. And again, I'd like to remind you that maybe not so much for Grover, but the quantum algorithm itself is also probabilistic, so it doesn't give you the correct result 100% of the time. So in comparison, 86% is pretty good. And even for something absurdly low, right, 0.1 threshold, we were able to get 30% accuracy. This isn't all that surprising for Grover. because Grover specifically has a very, very large difference between the correct state and the incorrect outcomes. And when we leave a lot of these incorrect outcomes outside the solution and don't allow them to build up too much, this difference grows even larger. And for something, a 8-qubit 3-sat problem, we were able to save up to 200,000 computations for low thresholds and 60,000 for high thresholds like 0.9. We also tested this on Simon and Shor. Our accuracy here is a little bit lower than Grover because the results are much closer to each other. We tested this for Simon with k equals 3 and k equals 4, and Shor for n equals 15 and n equals 21. Shor is probably the more interesting one since it has a lot of watermark gates. We were able to save up to 10 million interference computations for lower thresholds and 1 million for higher thresholds. That's the accuracy. That's the percentage of the result being returned, being the result that you're actually looking for. That's the threshold. So I'm going to, as soon as I get a molecule in my solution, for example, that has amplitude 0.5, I'm going to stop my computation. So as the threshold increase, the more interference patterns you calculate, and the more molecules make it inside, and understandably your accuracy of picking the right solution increases as more of them disappear. But this is a really question of how much efficiency can we gain by sacrificing how much accuracy. So in conclusion, we're presenting a novel technique for simulating quantum circuits that uses concurrent trains of control to expose a fine-grained control over the interference computations. As opposed to well-established simulation methods like Feynman's sum-over-pat integral method, we can greedily and concurrently build up these histories and eagerly terminate when we feel confident enough that our results will be fine. And we noted a good increase in efficiency of these simulations, again, up to millions of computational steps saved by sacrificing very little accuracy. For future work, we want to try to apply this to something like boson sampling, which is known not to be simulatable classically. We also hope to investigate the role of noise in a model like this, in a simulation model like this. We hope to explore the physicality of this model. Nature is concurrent itself, but our quantum computers require a high level of synchrony. So I think it's an important conversation to have. We hope to consider probabilistic reaction rules, and we also want to consider algorithm-specific optimizations. This method is as generalized as it can be. You can just download the code, put in whatever circuit you want, but perhaps there are further optimizations that can leverage the specifics of these algorithms. For example, Grover's algorithm requires multiple iterations, and this is because we rotate every time slowly, and each iteration puts a larger gap between the amplitudes of incorrect states and correct states. Well, another way of increasing this gap is essentially by omitting some of these undesirable states. So we hope to investigate, for example, can we skip some of the iterations by using this simulation method, because that would be huge, and that would save us a lot of computational power. That is all I have. Thank you.
Okay, so I'm very interested in what you said about let's decrease all the way down to 0.1 and we get a low success rate. However, we can do it again, and we can do it some more times. That could increase the success rate back up to like 50%. So do you have any, assuming that it's independent tries, right?
Mm-hmm.
Did you do any sort of calculation of that if we are going for 50% success rate, we decrease the initial success rate and then we repeat? How does it compare at that point?
So the stats that I presented are mean over multiple runs. Obviously, one trial is insignificant, so we did multiple times. But unfortunately, I do not have the data for the variance of those things, because I think that's what you're trying to get at. That is, if we run the 0.1 multiple times, can we get it? Yeah. We haven't done that, but it is an interesting point.
It could be that you will still come out way ahead.
That is true.
How much does the amount of computation scale with the threshold? Is it linear? That is t equals 0.1 10 times faster than t equals 1, or?
So it is it is very difficult to formalize that, and I'll say why. Because of the randomized nature, it is. I think it would be interesting to figure that out. But what can happen is, like, even let's say for 0.8, it is completely possible that the first 2 or 3 intermediate states that make it into the solution are the green ones, and that will immediately build up to your threshold. If that's the case, you will save, that's the best case scenario, you will save a lot of work. But it is also possible for low thresholds that the first few that makes it in are the red ones, then you will have to do a lot more interference patterns. I don't have a direct answer on how it scales mathematically, but the point I'm trying to make is it's kind of hard to formalize that because of the randomized nature of what makes it into the solution first and later.
Yeah, I guess you could try to run it and see what happens in expectation.
Yes.
Have you tried that, or?
No, we haven't.
Okay, thank you.
I just have a question on this, again, threshold thingy here. Since we're talking about the amount of work being done given the number of inputs that come here, for example, for like 0.8, they're using like T1, T2, T3 are such that it hits like the 0.8 threshold that you wanted. But wouldn't the work you would, like, what would you classify as work here? Would it also be the multiplications that are being done to get to that stage, right? And when all the threads are being run in parallel, so I was just confused because, like, I was thinking, like, oh, wouldn't the other thread still be doing the multiplicative work even though the addition work is
so,
the one being saved?
One thing I think it is important to clarify is here, the truncation specifically happens in the last nodes. We're not, obviously cutting off the entire path because those paths also lead to the states that we care about. So the work that we specify here is in terms of how many interference calculations that you have to do. The paper itself has a more detailed table on the total number of interference, the intermediate states, the number of states that you care about, and the number of states on average that our simulation method used. So if you're curious, you can check that table for more detail.
And just one follow-up on that, is it possible then, like, for certain algorithms that you might have seen, like, where this kind of an approach can be used intermediately because there might be multiple case places where destructive interference takes place in particular? Maybe for, like, multiple growers, algorithm runs itself, but, like, that's
that is entirely possible. As I said, it is one of the things that we want to look at on leveraging the structure of specific algorithms to further improve these results. And as you said, Grover is the prime candidate for for that.
Yeah, thank you for the talk. In many simulators, they do something, some pre-processing that is called gate fusion, which basically means that you collect certain gates together into one unitary that is like not super huge, but also not super small. And by that, you basically reduce the amount of unitary applications that you have. And actually, I think in many algorithms, not only in Grover, you have unitaries that basically only permute the amplitudes, so they neither introduce superposition or destroy superposition. So maybe that could also be a way for you to like have a specified gate fusion, basically by looking for this kind of gates and then executing them first, and then if you really have to, then you do your interference logic.
Right. That is something I would have to look into. It sounds great. Intuitively, one thing I would say is I think when you're doing that kind of gate fusion, where you're multiplied the matrices of the gates themselves, perhaps the metric for work might need to change because you're adding a different kind of work. So the what kind of computation you saved, that definition might need to be altered a little bit to account for that extra step. We haven't put it up anywhere, but it will go up. Yes, I mean, there's obviously something that was submitted, so yes. it has better result, more detailed results.
No? Okay, then thank you.
Thank you.
And I think that's all, folk. We are at the end. It was a very long and interesting and instructive days. And yeah, I thank you all. And I also want to thank the program committee for the work of reviewing and the careful selection. So, I mean, that has been very, very good. So, thank you, everybody, and I hope to see you next time. See you all next time. Bye then, enjoy the rest of the conference.